Didi sir, good morning.
Good morning. Can you hear me?
Yes, sir, I can hear you. Yes,
Okay.
sir. I will ask, make you as a co-host, so you can.
Sure. I'm just trying to see if my camera would work. Oh, my camera is not working. Just a moment. Let me
No problem.
sign out and come back.
Sure, sir. We have. Okay, sir.
Good morning, Nimai.
Yes, sir. Good morning, sir. How are you, sir?
I'm fine.
Okay,
Morning,
thank you.
Sarmaji.
Morning. कैसे हैं आप?
I'm fine.
Yes.
Nice to see you.
Same here.
Yes. So, sir, as you mentioned that we organized this symposium to celebrate this year Nobel Prize in Chemistry, which is gone to for invention and development of quantum dots. And so we thought that bring all the stalwarts in the quantum dot community in India to celebrate these moments. And
Indeed.
that's why we have invited Didi Sharma sir, who is one of the pioneer of quantum dot research in India.
I know, I'm aware of that. That's why I think he's the opening batsman. I think he's going to start that with a
Yes.
6, I'm sure.
Right. We will, I think, wait, couple of
Yeah,
more.
we'll wait. I know I am a bit early.
Sure,
Since
no
I was
problem.
available, I thought of just joining anyway.
Yeah.
I think Professor Bhatia has also joined.
Yeah. Good morning to all of you.
Good morning,
Professor
Bhalage
Sharma,
sir.
Good morning.
Hi. Nice seeing you, Professor Bhange.
Nice to see you, sir.
Yes. There are actually almost close to 250 plus people registered across India, Miss PhD student faculties.
That's very impressive.
And I don't know how many will join, but at least people have registered across India and they have shown interest, so hopefully we have good scientific discussions. So Didi sir, we'll wait for a few minutes, then we start.
Yeah, absolutely. Not a problem.
Yeah, you just take your time. You can turn off the video and just whatever, as you feel, sir. Okay, sir.
Yeah, thank you.
This is at Pandit sir, same for you. You also can be relaxed and I will call you in 5-10 minutes. Okay, sir. Yes. Bhavya sir, good morning. Yeah.
Sir, good morning.
Yes. Pandit sir is here and Professor Didi Sharma sir also here. Yeah. Dusman, can you make co-host Professor Angshuman Nag? Is here.
पास करने में बेटे से 3
I think we should start. Meanwhile, let's other people also join. Is it okay, sir?
Yes,
Yes.
Yeah, sure.
So I think very good morning to all of you. A very warm welcome from behalf of Institute of Chemical Technology, Mumbai, IUC Bhubaneswar campus. We welcome all of you for this one-day online symposium on Nobel Prize of Quantum Dots in Chemistry 2023. The reason all of us gathered here to celebrate this year Chemistry Nobel Prize. As all of you are aware, the Nobel Prize was declared on 4th of October, where the three pioneers in this area, Professor Munji Bawandi and Alexei Kimov and Professor
Louis Bruce.
Professor Bruce, from Columbia. All three of them awarded Nobel Prize for the inventions of groundbreaking work they have been doing in 80s and 90s. And we thought to utilize these occasions to bring a get-together on the colloidal quantum dust community in India to have a scientific discussions that what's going on in Indian context. We have stalwarts and pioneers in this area in India. We have very fortunate to have Professor D.D. Sharma and then Professor Narayan Pradhan Rajni Viswanathan, Professor Samir Sabra, Professor Anshuman Nag, Professor Ayan Datta. Okay, and we have Professor Sai Bhattacharya, Professor Bholanath Pal, and then I missed anyone. Yes, Professor Prasun K. Mondal. So we got people across whole India who have been doing pioneer works in this area of quantum dots. And hopefully, and this is also one good thing to note, this is kind of first time, I think, have a colloidal quantum dots community symposium. Maybe DD sir can correct me, where all the colloidal quantum dot people are coming together. So again, once again, warm welcome to all of you on behalf of Institute of Chemical Technology, Bhubaneswar IISc, Mumbai IISc Bhubaneswar campus. And we look forward to have a very fruitful scientific discussion. The main goal of this symposium in order to have idea what's going on in the area of quantum dot, so that young researcher, PhD student can be beneficial and they can think about and they can plan their future research in this direction. So with this, I like to request our beloved Vice Chancellor, Professor A.B. Pandit sir, to give his welcome address.
Thank you, Nimai, for this introduction to the workshop which you are planning to carry out. And I'm very happy to see the stalwarts in the area of quantum dots who have decided to share their experience and share their knowledge with the community. And now I see already 102 people have joined. So that just shows the correct choice of the topic as well as the recognized experts who are going to speak for it or speak in it. Uh, the theme which you have chosen, though the quantum dot as a theme is excellent because the future of computing is going to be in quantum computing as has already been decided. And when you want to have a popularization of computing as is currently done, quantum dot technology needs to come out of the lab and needs to go into manufacturing or needs to go into fabrication on a larger scale. Now, this is only possible if science and technologies come together and decide and identify the areas where the scale up strategies needs to be decided, the scale up criteria need to be looked at, and engineers and scientists can combine and can collaborate to solve these particular problems and issues which are likely to be faced by it. Now, the Nobel Prize, which went this year for this, it's indeed a recognition of the efforts which have been in existence maybe for the past decade or so. But now we can say that it is finally people are able to see the end of the tunnel and the possibility of actually employing quantum dots in activities which are either computing or analytics or detections or sensors, so on and so forth, including the design of catalysis. Because ultimately everything is happening at a quantum level, and if we are able to manipulate that scale of operation at a quantum level, we will have practically a control over the minutest of the activities which are happening. Slowly, I am sure this concept will also have started entering into the area of biotechnology, where the medicinal delivery in terms of quantum dots is likely to be again looked into. But since we are talking about biology and quantum dots is a realm of physics, it is going to be take a bit more effort for physicists to convince the biologists in terms of the utility of the quantum dot. But I am sure there are sufficiently enlightened scientists which see the commonality between biology and physics, and the people who have been looking into these aspects for the past several years will definitely start contributing. Now, I'm very happy to be associated with this. I will listen to some of the lectures as and when time permits me. But I would like to compliment Nimai as well as Professor Bhavia, director, for encouraging Nimai to, to initiate this particular seminar, because this is going to be a big motivation for the students as well as faculty. It may open up areas not directly involved with computing or quantum dot manufacturing or fabrication, but I'm sure it will involve the technological aspects of quantum dot synthesis or quantum dot fabrication, which can result into a number of new applications. Because whenever you present something to a person who is not at all initiated, the kind of questions which that person raises makes you think differently, because that fellow is completely unaware of the field. So the questions which are likely to be asked by that person are going to be very basic fundamental questions, and if you are in a position to answer those fundamental questions, it also makes you think along those lines and see what sort of efforts are required to popularize this new branch of science, which is finding its way in the proper realm of science. Recognition through a Nobel Prize itself clearly indicates the future as well as a definitive acceptance of this particular technology and its utility for the mankind, and compliments to the team who have put in an excellent array of speakers in today's seminar. And I wish all the very best to the listeners, to the audience, as well as I'm sure what they learn, what they take at the end of the day will definitely make them think and make them promote this particular area, explore this particular area within the constraints which are currently available to them, as well as the constraints which currently we are facing in the country. But nevertheless, getting initiated in this particular area itself, according to me, is a big step, a first step towards future succession as well as future sustainability. So thank you very much for giving me an opportunity to say a few words on this occasion, and I wish you all a very best of the seminar for today. Thank you.
Thank you, sir.
Thank you. Thank you so much, sir. Thank you so much. It is our pleasure to have you here, and very happy to hear your welcome address. Thank you so much. And now I request our director, Professor Bhavya, to welcome address to the dignitaries and all the participants on this national online symposium on quantum dot. Sir, over to you.
Dr. Nimai, thank you very much. Um, well, firstly, I would like to welcome all the distinguished speakers and the delegates on behalf of Institute of Chemical Technology. Indian Institute of Chemical Technology is a new in Bhubaneswar. In fact, we started in 2018, and it is an off-campus of Institute of Chemical Technology, Mumbai. And we do have a chemistry as a subject here. And I compliment Dr. Nimai that you have taken an initiative in organizing this national level symposia on creating an awareness on basically a Nobel Prize in chemistry, as well the area of quantum dots. And I'm sure in ICT Bhubaneswar, there will be many researchers who will be taking initiative in doing their research in the area of quantum dots. So not only I see chemistry, as our Honorable Vice Chancellor already mentioned about the quantum dots, the future of quantum dots, basically the scaling up. I'm sure other than chemistry, there are many other branches which can take a lead in the area of quantum dots. Especially, I look at the pharmaceutical field where the quantum dot nanocrystals can be of use. In future, I see there will be a replacement of some of the radio pharmaceuticals, basically which are used in the biological sciences. Basically, when we talk in terms of drugs analysis, quantum dots are basically of an interest where people can try and understand the cell biology. So, particularly a biological relevant property of quantum dots, and one can label the cellular structures and the receptors by using the quantum dots, and where the receptor mapping or receptor monitoring or the markers, can be of a quantum dots. I see there is a lot of future in the area of pharmaceuticals also, and of course there are many other branches where the quantum dot can be of use to all of us. But then, as Honorable Vice Chancellor mentioned, that we need to understand the further scaling up of this particular quantum dots and whether we can bring this to the market. So I'm sure there will be a deliberation in today's national symposium, and basically all those delegates, budding PhD as well MSc students who have joined, they will have a very informative talk from the speakers. So I once again thank all the distinguished speakers who have given their valuable time, have joined this conference, and this is of the first online symposia which our chemistry department is arranging, and I'm sure there are many more symposia and the international conferences will be organized. So once again, I thank you all of you for joining, and I once again welcome all of you on behalf of Institute of Chemical Technology, Bhubaneswar campus. Thank you.
Thank you so much, sir, for your kind words. So, now without further delay, we should proceed to the scientific sessions. As we have exciting talks, there are 8 speakers going to give a talk, and there are panel discussion at the end to answer the queries for the young researchers in the what could be the prospect and future of quantum dots. So we have tried to make it truly a scientific discussions that could be beneficial for a young researcher. And I just request all our invited speakers to be on time. I'll be, and as I said in the email, the talks are 30 minutes, so that includes 25 minutes your talk and followed by 5 minutes question answer. So I'll be giving you a signage, prior hand of 2 minutes. So I request to be on time because we have more to cover. Okay. And so, sir, let us start this symposium in order to celebrate this year colloidal quantum dot Nobel Prizes. And to start with, as our VC sir rightly said, that the opener is none other than Professor D.D. Sharma, the senior professor of Indian Institute of Science, Bangalore, who is one of the pioneer in QD research in India. And sir is going to talk about, and share his experience and talk about his title of sir's talk is Brighter Side of Semiconductor Nanocrystals, How to Make Defects Useful. So I'm not going to make the introductions of Professor D.D. Sharma is elaborate. That will be taking too much of time. Everybody aware of him. So just over to you, sir. So you can start the session. Thank you, sir.
Thank you very much. Do you see my...
Yes, sir.
Okay.
Yes,
Wonderful.
we can see. Yeah.
Let me move this one. Is there a way to move it? I'm not too sure. Okay. All
Yes.
right. Okay. Thank you, Dr. Mishra. I'm used to calling you Nimai.
Yes.
For this brilliant idea. I think it's absolutely appropriate to celebrate this fantastic success of synthetic chemistry in bringing about semiconductor quantum dots and really revolutionizing many, many different aspects of science as we know it. And to do it in India is particularly apt because, as may not be known to many in the audience, the scientific output in this particular area from India ranks 3rd in the world today, behind US and China. So India really has a very large footprint. Let me get started. It's really wonderful to see Professor Pandit, Professor Vaiva, and many other senior professors present here, lending their support to this field and the youngsters to excite them. And there's a large number of co-conspirators, speakers in this conference who are also participating in this. And I hope that the youngsters would gain a lot from their participation. Let me get started. Let me pick up the laser pointer. So I'm going to talk about mainly the luminescent, and that's what refers to brighter side of semiconductor nanocrystals. And I'll define what I'm going to talk about. And I'll point out how defects can be actually engineered to make them very useful and bringing about properties that would be otherwise impossible, bringing these quantum dots as semiconductor nanocrystals closer to application. Before I start, it's my pleasure to acknowledge the support and funding of many, many different organizations, particularly ACRB, Nanomission, and DST, through various project funding that they have done over the years, and J.C. Bose Fellowship, that was for several cycles that I was privileged to be supported by, and presently I'm supported by the CSIR Bhatnagar Fellowship. And a little while ago, we were also very generously supported by Jamshedji Tata Trust. The fascination of semiconductor nanomaterials are plenty. As soon as we talk about semiconductor nanomaterials, what comes to mind today, of course, are these three gentlemen that Nimai talked about, Bowendi, Bruce, and Akimov, who actually discovered that these two gentlemen, Akimov is the first one who discovered the fact that if we make semiconductor nanoparticles into very, very small size, and that was with copper chloride, they changed their optical properties. And quite independently, Bruce also established the very same fact using certain other semiconductors. But it took about 10 more years before Bowendi established with his co-workers, students, and postdocs how to controllably create these materials stable and how to tune the properties by controlling their sizes. And once that was introduced, after that, that was around early 90s, in the first half of 90s. And after that, there was no looking back, and people really jumped into it. And whenever we talk about these three people, we always think of what comes to our mind is the fact that we have this very ordinary looking vials containing some dull solutions. And in this case, it's cadmium sulfide selenide nanoparticles are there. And if you switch on the UV light, they give out these bright colors. These bright colors can range the entire spectrum of visible light, as you can see, from blue to red. And also they have enormous quantum efficiencies. And that was presumed to, at that time, revolutionize the display technology, which it is having an impact. There are commercial products today using various kinds of nanoparticles and quantum dots to brighten up the displays significantly. And this is very popular belief that this is what quantum dot is all about. And today's seminar also would reflect to the largest extent to these optical properties of quantum dots. But quantum dots are actually fascinating in all aspects, not just in terms of luminescence aspects. And I thought I'll touch upon that for a moment before I get on to the luminescent aspect only, because there are a lot of students who might miss the fact that these nanoparticles defies chemical and physical common sense in almost every respect. And this was realized very early. If you try to follow different fields in this area, and this is what I have plotted here. This is going to appear as an editorial article in ACS Energy Letters between Prashant and myself. Before, as you can see, before 1990, there was absolutely hardly any publication in these areas. What I'm plotting here as a function of the time, the percentage of contribution from quantum dot-based research in a given field. For example, if you talk about photoluminescence, I'm sorry. There were a lot of publications in photoluminescence before 1990, but none of them had quantum dot in it. But as time passed, and as told you, by the beginning, first half of 1990, about 7 or 8% of the papers were containing quantum dots, based on quantum dots. And that kept rising very rapidly. And about 50% of the papers published in the first half of 2010 to 2015 in that era was being published on the basis of quantum dots. But quantum dot is not the only thing. If you look at photocatalysis, and this is the one that's tracked by this red line, and you can see that this red line is shifted with respect to the black line showing photoluminescence by about 5 years. It also has been tremendously influenced, and in fact, even more influence in terms of percentage of paper that come out on photocatalysis based on semiconductor quantum dots. Electroluminescence peaked around the same time when photoluminescence did, but if you look at the sensor activity, you can see that it is hugely shifted with respect to the original photoluminescence that we thought quantum dots are only useful for. It took us 10 or 15 or 20 years to realize its usefulness as sensors, and it keeps on growing, and the use of quantum dot in the general area of sensors. Having given you that perspective, the wide spectrum of applications. And in fact, both Professor Pandit and Professor Vaiva talked about biology. Biology is another place which is a new frontier where quantum dots are having a tremendous impact. And there's already quite a few things out there in various stages of clinical trials, both in therapeutics and in diagnostics, based on semiconductor quantum dots. But we'll not be talking about that today. So I come back to their extraordinary luminescent property, which I'm going to talk about today. There are two types of luminescence possible. One is from the band gap of the semiconductor, and the other is the defect emission. And this is the defect emission that I'll be talking about, but I'll motivate you why you need to talk about defect emission and what is the problem of the band gap emission. To do so, let us first look at where the luminescence comes from. In any semiconductor, you have these levels, the valence band, which are all occupied, and these are the conduction bands, which are unoccupied. There are electrons here, no electron there. If I bring in some kind of an energy and excite an electron from this level to up that level, up there, very quickly, both electron and hole will decay and come. The hole will come to the top of the valence band and electron will come to the bottom of the conduction band before they recombine by a radiative recombination, giving out photon. This photon is the photoluminescence. And as you can see, this photoluminescence energy will be exactly equal to the band gap energy. So if we could change the band gap somehow, then we can change the photoluminescence energy. And this is the crux of the matter in quantum dots. Because this photoluminescence carrying the band gap is nothing new about nanomaterials. That happens in every material. So what is great about quantum dot is the tunability, that you can change the band gap by changing the size of the quantum dot at will. And that I show very quickly. Let me just illustrate with one particular example here of zinc oxide, where I'm showing you the absorption curve, and where this curve from flat begins to rise, measures the band gap. You can see the energy given here. And zinc oxide, by changing the size of the particle, nano quantum dot, you can change the band gap from all the way from 3.4 electron volt to about 4 electron volts. So you have this spectacular ability to change the band gap, and therefore the photoluminescence changes, and that gives rise to the spectacular change in the color that I talked about earlier. And it's fairly easy to understand this in terms of quantum mechanics, very elementary quantum mechanics. For example, particle in a box. You remember the energy level of the particle in a box is given by the quantum number n squared divided by the box size a squared, such that if I have a transition between these two levels and I then expand only these two levels here, this level will be denoted by n j plus 1, and this is the jth level. Because this is the jth level, this is the next level, so j plus 1. So the energy difference between them, you can see just by taking the difference between them, is proportional to 1 over a squared. So if I now decrease the size of the quantum dot or the box, what would happen as A becomes smaller, delta E becomes larger. And this is exactly what you saw in the zinc oxide case, that the band gap was increasing continuously as I made the quantum dot size smaller. So that tunability is fantastic. Now, with that knowledge in hand, we went ahead to do experiments of cadmium sulfide. This is very long back in middle of 1990s and 1995, these experiments were done, where cadmium sulfide 4.5 nanometer and cadmium sulfide 2.2 nanometer particles were made. And we were expecting to see the luminescence, which is shown over here, to appear at the absorption edge. But the absorption edge was here, because I told you the luminescence should carry the absorption energy, but instead they were shifted very strongly to the longer wavelength, red shifted. The reason for this is surface state. So basically, I said that you make this excitation and you expect the de-excitation to take place across this, carrying the band gap energy. But if you have other defect states in the band gap region, instead of coming back this way, first the excitation goes there, and then you have a lower energy or red-shifted excitation, de-excitation. So the photoluminescence now has energy that is smaller than the band gap energy shown over here, exactly the way you're seeing in this experiment. So the bulk band gap has this tremendous sensitivity because of surface states or defect states that can be there in the quantum dots. There's another aspect which is known as self-absorption, and let me explain what that means. Suppose I have made an quantum dot which is absolutely free of defects. So what would happen there? I would have an excitation which will go there. it will de-excite. The photoluminescence will carry the band gap energy such that now this one can be again absorbed by another quantum dot on its path and get excited. This is called self-absorption. By itself, it is not a problem. But imagine actual real life situation where I have many, many quantum dots. And the quantum efficiency is not always one. It can never be exactly one because there will be one defect or the other. So some quantum dots may absorb. So let us say on an average, the quantum efficiency of these quantum dots is very high. Let us say if I bring in one photon, that will give out another photon that can be absorbed by this one. And this process will continue till this process will give me out one photon out. If each of these steps would be 100% efficient, then for every photon in after self-absorption also, I'll get one photon out. There'll be no problem. But actually imagine that I have a 90% efficiency. But in 90% efficiency, every time multiplied will go on reducing. And after these many self-absorption, it will have only 17% quantum efficiency. In real life, there'll be many more absorption and re-emission. And if there are 100 steps with a 90% quantum efficiency, you'll end up with 0.003% quantum efficiency. And that's why in real systems, self-absorption becomes a very huge problem. So how defects can be helpful? So this is a quantum, it's an array of atoms, not quantum dots now. And in order to make a defect, so quantum dot, let's say this square is the quantum dot, and I have these atoms arranged in a periodic array, like in a crystalline material. Now, if I replace one of them with another material, then I have created a dopant or a defect, which is a point defect, which has a different property than the rest of the material. And this particular point defect is going to be manganese. So if looking at zinc sulfide, and there's the work from Professor Samir Sapra a long time ago in 2003. In zinc sulfide, if you look at it, it has a band gap which is somewhere up here, around 3.4, 3.5 electron volts. But you see that the photoluminescence that you saw is a much lower energy because these are dominated by surface states. But when you put in manganese into that, this very sharp level emanated. It is from manganese emission, and you can see manganese emission competes with the surface state emission such that the surface state emission almost becomes zero. So I beat the surface states and transfer all the energy into the manganese emission. So what happens is that these defect states that were there in pure zinc sulfide was killing all the band gap emission and was giving me a broad surface state emission. But then I put in a very well-defined manganese dopant level, which is at lower energy than this one, and almost all the energy got transferred into the manganese, and I started getting all quantum efficiency, very high quantum efficiency out of the manganese emission, and you can see surface state emission becomes much smaller. And using this kind of technique, this is a slide from Professor Narayan Pradhan. He could make manganese emit with 60% or more than 60% efficiency, very bright, which was amazing in those days. So what I'm plotting over here, the absolute quantum yield, if you talk about cadmium selenide coated with zinc sulfide, which is very good, at very dilute limit where the self-absorption is weak, you have, let's say, 20% quantum efficiency. But as you increase the concentration of the solution, this is basically the concentration of the nanoparticles in the solution. You can see that the quantum efficiency in a log scale is falling off. Here it becomes almost 100 of the efficiencies that we had. But if I dope the system with manganese, you can see that the manganese emission, despite changing the concentration of the quantum dot, remains almost constant. And this is the consequence of the Stokes shift. The manganese energy that I'm finally harvesting is much smaller than the band gap, and therefore this emission cannot be reabsorbed by the quantum dot. So there is no self-absorption. I avoid the self-absorption. So defect allows me to solve the surface state problem, as I have shown you, and defect allows me to avoid the self-absorption problem by manganese doping, as I have shown you. There was a lot of challenges in the synthesis of these manganese doped materials, and Anshuman Nag, who will be talking again later, Professor Nag, had solved this problem in 2 papers long time back, showing how manganese can be very effectively doped in these quantum dots for very bright applications. But is there any other problem with the manganese doped quantum dots? It turns out that I'm actually not telling you one aspect, which is this, that manganese, you dope into any of these nano crystals, quantum dots, or any size of the quantum dots, it gives photoluminescence, which is almost identical. You can see that the emission energy or wavelength is hardly shifting around. And I told you what excited us in semiconductor quantum dot is the tunability. The fact that we can at will change the manganese position, the emission, photoluminescence position anywhere. And also it was very broad, as you can see this particular plot. So the tunability and the width are seriously compromised in these manganese doped samples, and that is something that we had to address. So these are the two major problems of manganese emission: lack of substantial tunability and broad emission. And this is a summary that in an early work with Narayan Pradhan that we had written, that if we compare between bandgap emission and dopant emission, bandgap emission is very good because it is tunable emission. Dopant emission has a fixed emission, almost completely fixed. You cannot change it. So bad things are written in red and good things are written in blue here. And you can see that bandgap emission I can tune by changing the composition and the size over the entire range of the visible spectrum and beyond. Whereas emission from manganese at the time when we are writing this paper were constant only over this very narrow range of wavelengths, giving me essentially orange color. And I can get very narrow emission width from bandgap emission, but large emission width, as I have shown you, from manganese emission. But bandgap has very serious problem for self-absorption. There's negligible self-absorption, I've already shown you. And it's very sensitive surface degradation bandgap, whereas manganese is insensitive to surface degradation. So what one would like to do is to actually have manganese emission extended over the entire length, entire wavelength regime, combine the blue part of the bandgap tunable emission and narrow emission width with negligible self-absorption and insensitivity to the surface degradation. This is the challenge that another student, Avijit Hazarika, with Professor Nag, had taken up. What we're looking at here, and this is in collaboration with the group of Arindam Chaudhuri and Priya Mahadevan from SN Bose and IIT Bombay, we are looking at, under a microscope, these are individual quantum dots. How do we know that these are individual quantum dots? If we monitor their photoluminescence in time, we see them blinking, and the blinking shows that they are one or very few quantum dots separately. Then what we did was to look at the individual spectrum coming out of each of these nanoparticles. And when we did, what we found that the individual particles gave out very narrow emission. And depending on which quantum dot I was looking at, which specific quantum dot I was looking at, the emission from manganese was drastically different. It was actually covering from 530 nanometer to 630 nanometer over this entire range. And to give you a comparison, this is the range that we knew manganese would emit over different systems, but we found that in this system, it was going from green all the way to deeper red. And we understood what is the reason that was happening. So the orange red that we saw all the time was actually a consequence of ensemble averaging of these different colors that was always red. When you look at the individual quantum dots, it had different colors. So the question was, can we give ensemble amount of quantum dot which emits only one of these colors and tune that color across so that I can have macroscopic amount of quantum dots of manganese emission, so no self-absorption, no problem of surface state, and yet I'm being able to tune them. And this is the question, and that was addressed by, again, Avijit Hazarika in collaboration with my colleague, Professor Anshu Pandey, in this particular paper, where they could show that by doing crystal field engineering, which essentially meant creating a core shell structure of zinc selenide, cadmium sulfide, zinc selenide, and placing manganese ions, dopants at different points in this shell. Controlling that, we can change the crystal field effect on manganese and therefore change the details of the manganese energy levels and get transitions that can be ranging across from blue to red. And these are the macroscopic ensemble average of manganese emission from such crystal field engineered system. And what I've talked about so far is point defect. And I have, I think, just about 5 minutes of speaking. So I quickly tell you about another kind of defect that you can have. where I have not changed one of the atoms here, but I've shifted an entire line of atoms, and this got a line defect. And if I'm looking at the perpendicularly at a three-dimensional object, you can think of this line actually as a plane perpendicular to the screen that you're looking at. So that will be a planar defect. And we can, what would be the question is, what would be the properties of such a planar defect? Can we create it? Can we control it? And if we can, what kind of defects properties can we expect from those defects? And there's a question that we asked. Shamasish Das actually addressed this problem, and there's unpublished results together with Ranjani Vishwanatha. And what we am showing you is actually the TM, high resolution TM data of quantum dots, where you can see these line defects, which are actually planar defects because of intergrowth defect between woodsite and zinc blende type. An extensive amount of defects exist in these quantum dots. And if you look at the photoluminescence properties of these quantum dots, then you'd see that the absorption curve defines a very narrow absorption edge, telling you that's a very narrow distribution of sizes of quantum dots we have, despite these defects. But the photoluminescence, the emission from the band gap is very small, and you have very large defect-induced emission, which presumably come from these planar defects. In fact, that we can prove by annealing these quantum dots at a temperature, high temperature in a solvent, such that we anneal out all these defects, and those you can see then after annealing, you get no defects in the quantum dots. And then this photoluminescence, there's hardly any change in the absorption edge, but you can see what happens. This defect emission almost vanishes, and the band edge emission goes up enormously, showing that I've converted this these defects, planar defects that were giving this photoluminescence, and removing them, I've suppressed the photoluminescence of the defects and converted the efficiency back into the band gap. And this you can do controllably. And not only that, I told you the main problem of the point defect was that we couldn't control its energy. We had to do crystal field engineering, which is a very difficult one. As I told you, we had to put the manganese at different points. Here, the idea was these planar defects are extended objects that go all the way up to the crystal surface, as you can see. So if I change now the size of the quantum dots, the size of the planar defects extension in the lateral direction is going to change. And so that should influence its energy levels, unlike point defect, which does not sense changing the size of the quantum dot. So the question is, can we change the energy of this defect emission by simply changing the quantum dot size, because we have the infrastructure and tremendous chemical wisdom of how to control the quantum dot size. And this is exactly what Shamasish did. And this is to show you in this panel. If you look at, he made this defect containing quantum dots with different sizes, and this is the absorption. This you can see photoluminescence considerably shifted with respect to absorption edge. But first, looking at the absorption edge, you can see that the absorption edge, as we make the quantum dot size smaller, systematically shifts to higher energy. And tracking that energy shift of the absorption edge, the planar defects emission energy also continuously shifts. So we have the beautiful tunability of emission, because we have created planar defects whose wave function extends all the way up to the quantum dot size. So now when we change the quantum dot size, the quantum confinement of the planar defects also change, giving rise to this tuning. And it turns out that you have enormous quantum efficiency. And in one particular case, we created white light by making this quantum dot emission rather broad. And the quantum efficiency is close to 90%, as shown over here, compared to the defect-free sample, which had only about 20% quantum efficiency. And as we increased the optical density or the concentration, you can see that the quantum efficiency of the defect-free sample drops catastrophically, simply because of the self-absorption problem that I talked about. But self-absorption is minimal for these defect control, because of a huge Stokes shift. The emission carries energy that's much smaller than the band gap of the host, and so self-absorption problem is minimized. And you can create, it's just to show that you can get bright white light out of these materials. And with that, let me end my talk, because I've finished my 25 minutes. summarizing this part of that engineering such planar defects, we can have tunable emission with high quantum efficiency and little self-absorption. And let me thank you for your attention. Thank you very much.
Dear sir, thank you. Thank you so much. You are precisely on time. As we told all of you, discussed that many things we need to learn from you, that you shows us how to be very much on time. It is very exciting talk, and I think all young people are new to this community, they need to understand many things. Now we have many questions popped up in the chat box. Definitely difficult to get everything. I'm going to take it as a few. There are, I think, few people. I think I'm going to take a few which are more. Looks like more interesting. Like I think your colleague, my friend also Rajamani from ISC, I think she has asked these questions. Why emission broader in the presence of manganese?
Yeah, as I pointed out, if you look at the individual quantum dot, it is not broad. Individual quantum dots are all very, very narrow, but they emit different ones emit at different places. So when you look at the ensemble, it's a heterogeneous broadening, inhomogeneous broadening, different quantum dots emitting narrow but at different energy levels, and you see the envelope of that. But if you now take and make the way we have made to give single colors, you can narrow down the emission significantly. Yeah. Okay. And under the microscope, of course, you see very, very narrow ones because you're looking at only one quantum dot. So intrinsically, the manganese emission is actually very narrow because what are involved are the atomic energy levels, essentially.
Thank you, sir. Thank you. So one more question we definitely like to take. Suparna Viswas, one of our PhD student, asks that optical transition in Mn2 plus is forbidden, actually, the delayed transitions. But why it is not maintained in this case? What is the physical basis of it?
Yeah. The physical basis is actually simple. Optical transitions are not allowed in a dipolar sense. And as you know that none of the states if you are away from hydrogen atom, no state is of pure parity. Only hydrogen has the pure parity because this has only one electron. And then you take an atom, put it in a solid, and so basically L is not a good quantum number, but it's a dominant quantum number, still approximate quantum number, but dominant. And what that means is that normally the transition probability of a DD transition would be very, very small. So if there's a competing transition, that would always win, and you'll always see decay from other levels, which are dipole allowed. But imagine a situation where your dipole not allowed transition has the lowest energy. So very quickly, the excited energy comes down looking for the lowest energy and goes to the lowest energy level. And then it realizes, oh my God, I am in a level which is actually DD transition, and so it's dipole forbidden. What do I do? There is no other way. Now it figures out that, well, it's dipole forbidden, but I'm not exactly an L quantum number state, which implies that I have finite transition probability, which is much smaller. To give you an idea, the band gap emission that I talked about has a lifetime or a time scale of transition in 1 to 10 nanoseconds. Whereas the manganese emission that I'm talking about is in hundreds of milliseconds. So you can see that how many orders of magnitude reduction in the transition probability has taken place because it's a manganese DD transition. But the fact that it still emits from there is simply because it has no level below that. It's very localized. It cannot go out to other levels. So there is no transition probability to, even if I have another defect site with lower energy, that these will have no transition probability once it comes into the manganese. And then it has no other choice because I give it enough time, 100 millisecond compared to the nanosecond scale, and it will then emit, going through that very small probability, transition probability event.
Thank you so much, sir. Thank you so much. Is there any questions? I can see that Professor Rangarao sir also there from IIT Madras is here. Professor Bhanagi is there. So is there any questions from our distinguished guest? Good to see you, Rangarao. Yeah.
Namaskar to DD, first of all. DD, one small, see, a lot of youngsters here, they may have a question of how do you define quantum dot?
Yeah, it's a very important question. The point is that the definition of a quantum dot, a practical definition of quantum dot, normally quantum dot is used in the context of semiconductors. And then a quantum dot emphasizes the quantum part of it, which means that some quantum phenomena is manifest in its properties. One of the early ways of defining that we had agreed upon was to say that if the change in the size of the particle has a non-trivial change in its any physical property, we'll call it a quantum dot or a quantum nanoparticle. Now, that means depending on which particular aspect I'm looking at, the size of the quantum dot can be very different. Because if I'm talking about magnetism, that gets affected by a much larger size regime if you vary the size. But when you talk about very small, like if you talk about titanium dioxide, which has an excitonic binding and the Bohr radius, very, very small, you really have to go to very small size before you see quantum effects. So good way of thinking about it is that if I have a non-trivial dependence of chemical or physical properties on size, then I call it a quantum dot, or the material being in the quantum dot regime.
But if you see carbon quantum dots,
Because there are properties that are very different. Because carbon normally is not photoluminescent, but carbon dots can be made extremely luminescent materials. So it's a platform for many, many such technological applications, including biological.
Thank you.
Thank you.
I know there are many questions that people have already texted, but due to paucity of time, not possible for us. But as the participant, as we mentioned, there are actually panel discussion at the end where I will take up all those questions to our experts to get some idea. But I think let us thank Professor D.D. Sharma once again for your valuable time, sir. Within a short period of time, I contacted you and you have agreed kindly. I know you have busy schedule. I think tomorrow you're flying to Korea. So, still you have accepted our invitations on behalf of the Institute of Chemical Technology, Mumbai Bhubaneswar campus. I would like to thank you, sir, to enlighten all of us of the exciting your journey and your research on quantum.
I compliment you, Nimai, for organizing it. It would have been a shame if in India we did not celebrate this event, such a big event, and so close to the activity of so many of us.
Yes, sir. Yes, sir. Okay.
Thank
you so much, sir. Thank you for
for giving me the opportunity.
Nice seeing you, Didi.
Nice seeing you, Ranga. Always nice seeing you.
Thank you, Professor Sharma, for accepting our invitation. Thank you.
Thank you, Professor Pandit, for the kind.
Thank you very much, sir.
Thank you.
So we'll move to our next talk. Our next speaker is from ISAR Kolkata, Indian Institute of Science, Education and Research, Professor Prasun K. Mandal. And Professor Prasun K. Mandal also going to talk about in different aspects of this colloidal semiconductor nanocrystals. He's going to talk about on perovskite nanocrystal, which is very recently got popular, which is also a quantum confined material. So his title of Professor Prasun K. Mandal's talk is Exciton Dynamics in Perovskite Nanocrystal. With these short introductions, it's over to you, Professor Mandal. Is Dushman, have you made him co-host so he can share the screen? Dushman?
Yes, sir.
Yeah. So Professor Mandal, you are co-host now. You can share your slides.
Yeah, can you see it now?
Yeah, it's coming up. As I requested to Professor Sharma, also same request to all of you, please try to maintain the time. We have lots of speakers to speak. You have 25 minutes to speak about, and then we have 5 minutes on question and answer. Now is over to you, Professor Mandal.
Yeah, just a minute.
Sure.
Can you see the screen?
Yes.
Okay, I cannot see part of it.
Oh, okay. Your screen is, yeah, now it's gone actually.
Yeah, just a minute.
Sure.
Can you see now?
Yes, it's visible again.
Okay. Okay, so let me start. I have 25 minutes, right?
Yes.
Okay, good.
Yeah.
Okay, so first of all, I'd like to thank Dr. Mishra for having this kind of conference, online conference, and it would be good. I believe this is the first of its kind in India. So it would be good to celebrate by the talks of the people who are actively engaged in the quantum dots or perovskites for several years. So in our group, we work on both on quantum dots and perovskites. So since this is this conference has been organized to celebrate the the Nobel Prize for quantum dots, so I'll talk a little bit on the quantum dots, and then I'll show you some of the unpublished results regarding the perovskites. Okay, so if I say before I start, I'd like to say a few words about the kind of research that we do in our laboratory. We do make the probes. That probes could be bioorganic or quantum dot or perovskites. And then we do say the ensemble to single molecule fluorescence experimentation that includes the spectroscopy and microscopy. And say we can do say from spectral to dynamical. The dynamical could go from say femtosecond to minutes. And as I will show you in the next few slides that we have a home-built confocal or say the TURF microscopes. So what do we do? Actually, we make our say the quantum dots and perovskites. We do not say buy it from the commercial vendors. That's because say the kind of quantum dots that the say the vendors do provide, they might be good for the ensemble behavior or say the ensemble kind of experimentation, but at the particle level, as I will show you, that they're pretty worse. And then we have developed the kind of instruments that we need mostly, and we ask the hitherto unanswered questions, which are sometimes uncomfortable. And we do a lot of experimentation as well as we perform a lot of statistical analysis, and that's because we have a group of quite brilliant students here. So, there will be different kinds of talks over here. Let me emphasize that why photoluminescence is important. Say, other than photoluminescence being beautiful, it's like, say, it can measure the distance, say, at a 1 nanometer time scale, and that is in a non-invasive manner. You can do it in the live cell. You can, say, track any cellular events. You can do photoluminescence, say, starting from the solid to liquid to the gas phase, from temperature like, say, 4K to 500K, and say from room temperature to gigapascal. So that only tells that, say, the photoluminescence is a really versatile technique. And as I will talk about, say, this is the very basic Jablonski diagram that you will see. And why am I showing this particular diagram? That most of the people involved in this conference, they know it. That's because that the dynamics actually dictates that how it can be used, right? Professor Didi Sharma gave a very nice introduction, and he also talks about the importance of the trap states. Now, I'll show you that trap states could be beneficial, trap states could be detrimental as well, depending on what kind of applications you are actually looking at. So the presence of the trap states as well as the dynamics. So only the presence of trap states may or may not help, but at the same time, so the dynamics will tell that what kind of applications you can have for a particular type of quantum dots that you have synthesized in your laboratory. So this is the kind of the confocal microscope that we have built in our setup. This is the kind of the total internal reflection fluorescence microscope that we have built. And in our setup, you can, as I have said, that you can say do ensemble to single particle, say from picosecond to minutes time scales. Okay, so this is a brief overview, and we can record their emission spectrum. We can monitor their, say, the single particle behavior. We can record their ensemble behavior. So such is the versatility of the setup that is there in our laboratory. So since I believe not many people would be talking about say single particle spectroscopy, so it would be good to give an overview. Say generally when we do the cuvette spectroscopy, so say you generally work with the micromolar concentration. This means that 10 to the power 18 molecules at a time, or say on the average. Now, when you move from, say, 10 to the power 18 to 1 molecule, if you cannot visualize such difference, the difference can be translated into, say, if I throw a 1 liter water bottle in the Bay of Bengal, And then if I ask you to find it out, such is the difficulty of say seeing a single molecule. But fortunately, there are means to do it. And say using the photoluminescence, it is quite possible to say eliminate the background fluorescence, and that's how we could see the single particles. So now say here is a movie, if it plays. Yeah, so here you can see that say the single particles are moving say in a 2D plane, or they are say static within the polymer matrix. So here what you can see that you can say in our setup, you can actually see the single particles which having a size of 5 nanometer. Now say we do some other work, but I try to skip all these due to the paucity of times. And say these are the more or less the publications during last few years. So I would like to emphasize upon say 3 publications that have come. So the first JPCLators, that is on your left-hand side. So that is based on the say the quantum dots. And say the second one is also on the in PCCP, that is also on the quantum dots. I will touch upon all these. So now let me come to the main topic. So why say the quantum dots and the perovskites? Now, say several years before, people who are mostly working with the say the fluorophores. Now, if you look at the say the base of the fluorophores in the left-hand side plot, so then you will see that even at the ensemble level, the fluorescence intensity goes down to 50% within a minute. Now, in comparison, you can see that the quantum dots, they are alive for at least say 20 minutes without any problem. But say as well as say if you want to cover the all the UV to visible range, then you need say 10 dyes. But for example, you can cover the entire UV visible NIR range with a say 1, 2, or 3 kind of quantum dots, and that is because, as Professor Dilisham also mentioned, that that is because of the size-dependent emission properties. So although the chemical composition remains more or less the same, but by varying the size, you can actually tune the color, or say the emission color. And that is why, say, based on all these good properties, say, for example, broad absorption spectrum. So this means that if you have a laser, then you can actually excite. So that could be a problem for fluorophores. Now, say these quantum dots, depending on what kind of quantum dot you choose, it can have, say, very narrow or the size tunable emission. It can have quantum yield, and as I have mentioned, that it has a superior photostability. So that's why you have a lot of applications for these kind of quantum dots. Now let me talk about a few problems. So although core shell nanoparticles are very good at the ensemble level, and I believe in this conference many people would talk about, but when you bring these, say these core shell quantum dots, the so-called the robust quantum dots at the single particle level, so then what you see actually that the say the emission maximum actually shifts towards the blue, and the intensity falls down to a background level within a couple of minutes. So then people thought that, okay, maybe if I put another shell, so then the core shell kind of quantum dots can. But instead, say instead of having this kind of say core shell kind of quantum dot, what we as well as say a few other groups in the world, they proposed that instead of having a core shell or say core shell kind of quantum dots, if you have an alloy shell kind of thing, so then the crystalline property as well as the electronic property change very smoothly, which was not the case for core shell or core shell quantum dots. And as a result, say you can see that this is the result from our lab. So what you can see that say the single quantum dots are alive for almost 1 hour without any change in the, or say without any significant change in the intensity, or say without any change in the emission maximum. Okay, so if you want a detail of these, you can go through this perspective article that we wrote last year. So then, say many of the people, as you will see in the quantum dot community, they will talk about the photoluminescence quantum yield. But we, as well as say a few other groups, have showed that the quantum yield of a quantum dot, or say even the perovskites, they do depend on the excitation wavelength. So that's why I would like to put a caution that whenever you want to mention the value of a quantum yield, I mean the photoluminescence quantum yield of a quantum dot or perovskite system, please mention the excitation wavelength, because say the photoluminescence quantum yield of quantum dot do significantly depend on the excitation wavelength. And say the reason behind it, we have say recently described in this perspective article last year. So now, say so far, mostly say the popular ones, the popular quantum dots are based on cadmium or lead. Okay, but as you can understand, that the sustainable applications demand that say it should not have any lead or say cadmium, because those are toxic. So then there are actually two tongues of approaches. So then people either talk about the indium phosphide base or copper indium sulfide based quantum dots, and say these indium phosphide as well as copper indium sulfide based quantum dots, as you can see. So these are the results from our laboratory, and we could actually make say 96% quantum yield of say copper indium sulfide base, again core alloy shell quantum dots. Now, those who are working with the quantum dots, you know that there is a problem of the stability, right? I mean, so far perovskites do possess, say, serious threat regarding the stability. So barring a few groups, most of the groups that synthesize the perovskites, you know that there is a difficulty regarding the stability. But in case of, say, the copper indium sulfide quantum dots, as you can see, that the photoluminescence quantum yield for these copper indium sulfide-based quantum dots, or say the core alloy shell quantum dots, is close to 96%, or say it remains above 90% for almost 400 days. So this means, and this is the same batch kept in the ambient light without any protection of, say, inert atmosphere or, say, protection from light, etc. So now, say, people actually talk about the electron trapping, right? Mostly you will see that the people talk about electron trapping, and as I will also show you that why electron trapping is so important. But that doesn't mean that you can leave aside the hole trapping. Okay, so hole trapping is actually quite beneficial. And as I will show you that although electron trapping is detrimental, but hole trapping could be beneficial. So now, say the starting the hole trapping could be a bit. Some noise is coming. So as you will see that, say the hole trapping is actually difficult to monitor. Why people could do it in case of cadmium selenide? That is because there was a suitable position of the energy levels. But such a luxury is not present for other quantum dots. Okay. But what you can say actually do is like you can perform the single particle spectroscopy and say see the nature as well as the extent as well as the consequences of the hole trapping. Okay, so here say what I show that as you can see that the hole trapping increases as you increase the excitation wavelength. And say the ratio of the say the hole trapping to the detrapping, and as you will see in the right hand side plot, that the relative amplitude of the hole trapping can be correlated with the say the increase in the PLQI, and this increase in the PLQI is based on say the increase in the excitation wavelength. We have proposed say certain models as you will see, but just for the sake of time, I will try not to explain. If anybody is interested, we can explain that. Now, this is a very special case, say, when both electron and hole can be trapped. Say, as you see in the upper left-hand side corner, say, what you see, what is known as the blinking of the quantum dot. Now, as I will show you in the next slide, that blinking actually causes some problem. There are many problems. One of the problems could be that, say, for example, if you want to track a drug, how it goes inside a cell, so then it could be problematic because, say, sometimes it is on and sometimes it is off. So then it would be very difficult to actually track the drug where it goes inside the cell if you tag it with the, say, the this kind of quantum dot. Now, if you look at, say, these literature reports of, say, the single quantum dot being in the on in comparison to, say, the blinking. So the highest quantum, or say the highest on time, as you can see, are definitely less than, say 100 seconds. But what we could achieve, say, in case of this kind of copper indium sulfide core alloy shell quantum dot, so the highest value that is reported is 130 seconds. So this means that for more than 2 minutes, this kind of quantum dot, they do not blink, which means that it would be much easier to track, say, a drug if it is tagged with the say this kind of quantum dot. So I want to put another concern here that, say, whenever people say synthesize one kind of quantum dot in a single batch, they believe that all the quantum dots within a single batch is of identical nature. Okay, so in that concern, I just put forward this slide. As you'll see that the previous generation, or say even nowadays, say people just test 1 or 2 rices when they boil, and if 1 or 2 rices boil, then they can make sure that the rice in the entire container is boiled. But that is not the case. So as you will see in this PRL paper, say for this cadmium selenide-based quantum dots, they have shown that the quantum dots synthesized in a single batch may not be identical. However, so when we are working with these cesium-lead bromide perovskites, then we could show that unlike, say, the cad selenide-based quantum dots, and these are core shell quantum dots, say this CSPB-BR3-based perovskites do actually, or say the variation is much less than it was in case of cadmium selenide. And we could do it based on a very serious, very detailed kind of statistical analysis, as has been mentioned over here. So now, why perovskites? So perovskites, as say many people would be talking about, so I'd like to make it as brief as possible, that they don't have say the mid-gap states. And those mid-gap states, I mean, not having the mid-gap states actually is quite helpful. Okay. So, and as you can see, or as I had showed you earlier, that say covering the say from the blue to the red, you can do it with say 1, 2, 3 kind of perovskites by varying the halides. And these perovskites, they do have say defect tolerant nature. They have a high PL quantum yield, and say generally when people try to make the or say increase the brightness, they generally increase the PLQY. But as I will show you, so these are some of the unpublished results that I will show in next, say 5 minutes or so. So that then you will see that, there is another approach of enhancing the epsilon. As you know that the brightness is a multiplication of the epsilon, the molar extinction coefficient, and the PLQY. So say from the PLQY side, you can maximum go up to 100% generally, okay? But say there is, in general, no such restriction if you can increase the epsilon. Okay, so epsilon talks about the feasibility, and that feasibility in say different terminologies can be enhanced very significantly. Okay, so say as I have mentioned that say perovskite synthesis is I mean you can do it in the Slank line, and some of the perovskites with not near unity, but at least 80% quantum yield, you can actually synthesize at a room temperature in an say normal ambient air atmosphere, and with cheap, I mean not so expensive starting materials like the HI, HCl, and HBr. So now that brings me to this particular slide. Say, for example, Professor Didi Sharma talked about the trap states, right? So trap states beyond the conduction band will always be present. Although perovskites are known not to have the, or say perovskites are known as a defect tolerant, but the defect tolerance comes from the fact that there is no mid-gap states between the valence band and the conduction band. That does not necessarily say that there is no trap states beyond the conduction band. So what I mean that say above the conduction band, even the perovskites, and we have experimentally shown that the perovskites do have significant extent of the trap states above the conduction band. So now, say for example, when electron or hole are separated, so then if you can say capture the electron and the hole separately, so then it would be good for electrical properties. Okay, and say if you can by different means combine these electron and the hole in a better manner, so then it would be good for optical applications. So depending on, let's say, how do you explore the trap states, or say how is the density of the trap states, at the same time how is the say the dynamics of the say the electron trapping or hole trapping in comparison to the electron and coming back to the bandage. So that particular, say the relative dynamics actually will tell you that whether the quantum dot that you have synthesized would be good for electrical or good for optical. So we have, say, done some work on cesium-lead bromide. So that's what I do not want to show it over here. So now, say if I want to compare the cesium lead bromide and cesium lead iodide, so as has been shown over here, say if you just let me take the pointer. Yeah. So say if you look at the say the absorption spectrum of the cesium lead bromide and cesium lead iodide, and say this one is say the solar spectrum, so you can see that the cesium lead iodide can actually absorb significant portion of the solar spectrum much better than that of the cesium lead bromide. But then, say there are other problems of cesium lead iodide perovskites, and I believe, say, other speakers would talk about it. So I'd like to skip these slides. So now, say for cesium lead iodide perovskites, say again, say as the lead is present, so then that might cause a significant problem from the say the sustainable use of these kind of perovskites. So then what we thought that, okay, is it possible to replace the lead in cesium lead iodide perovskites? And I mean, these are some of the unpublished results that I'll show. So say indeed, we could replace very significantly, say about 40% of the lead in the cesium lead iodide perovskites. And but we cannot tell you for sure that all these say zinc are within the perovskite crystals itself. There are possibility of non-specific binding of the, say, as we know that lead can non-specifically bind on the quantum the perovskite cubes. So similarly, zinc can also. But the good part about it is that, say, the molar extinction coefficient of say such a perovskite is actually in the order of say 10 to the power 8 molar inverse centimeter inverse, and the quantum yield is in the say close to unity. So that makes the brightness in molar inverse centimeter inverse scale in the order of 10 to the power 8. So to our belief, that's the highest brightness that anybody could report for any kind of quantum dots or perovskites. But now we wanted to show that, or we wanted to investigate that, say, although we tell that, okay, there are sunlights, and then say, is it like that the all parts of the sunlights behave in an identical manner towards the exciton dynamics? Okay, so say for example, as you can see, that the say the solar spectrum is actually quite broad. So is it like that the different regions of the solar spectrum would affect in an identical manner to the exciton dynamics or not? So that's the question that we asked. And we say use 3 different techniques, say the ultra-fast transient absorption, the fast PL, the TCSPC, as well as the, say, the ultrasensitive single particle spectroscopy. So as you will see that we have used, say, several of these wavelengths in order to know whether the different regions of the solar spectrum behave in an identical manner. So let me go to the results slide. So as you will see that, say, for example, the tau rise. So the tau rise, as you can see in this particular column, so the tau rise actually depend on the excitation wavelength. So this means that where you excite, depending on that, so this tau rise is nothing but the exciton cooling. So how much, or say, what is the extent and how much time the exciton needs to come back to the, say, the conduction band minimum. Okay, so that is what is meant by the tau rise. Now, as you can see that as the, say, the excitation wavelength increases, this means that as we are exciting more closer towards the band edge, so then this tau rise actually decreases. So reduction in the tau rise is good. That is because this means that the exciton is actually spending much less time before coming to the conduction band, or say the conduction band minimum. And that actually gets reflected in the extent of the exciton coming back to the band edge. So the absolute values are not important, but rather the relative values are important. So as you can see that as the excitation wavelength increases, so this means that as we are exciting closer and closer to the band edge, so then, say, the population that coming back to the band edge is actually 3 times in comparison to when, say, it was excited much above the band edge. And so, say, this has been shown as a plot. So what you can see is that as the rise time decreases in this green plot, so is the enhancement in the, say, the population, and so is the enhancement of the PLQI. And we could measure say the trapping time to be nearly about 1.3 picosecond. So from the transient absorption, we could show that the hot exciton cooling time depends on the excitation wavelength, population depends on the excitation wavelength, and both these properties actually can dictate the PLQI. So now try to understand that we are actually trying to correlate, say, some ultrafast properties to some steady state properties. And say here, I just show, some of the TCSBC data. So if I can conclude.
Professor Mondal, you have last 2 minutes.
Yes, I'll finish within 2 minutes. So as you can see, say from this particular slide, that the radiative decay rate actually increases and the non-radiative decay rate actually decreases. So that tells that, say, the extent of the trap states. And since we are talking about the optical properties, so in the optical properties point of view, you will see that, say, the trap state can, especially the electron trap states, can actually, say, cause a detrimental effect. So then if I would like to show you, say, the results of the single particle spectroscopy. So we have used even more wavelengths than what we could use for the transient absorption. And as you can see that the on fraction actually increases. Okay, on fraction means what? The on fraction means that the time, or say the time that the particle stays in the on state. So on state means it will give you the photon, off state means that it will not give you photon. So as we increase, say, the excitation wavelength, say, from 405 to 647, so as you can see that the on fraction increases, say, from 64% to 90%. And as you can see, say, the peak maximum of the off fraction decreases and that of the on fraction increases, and so is the PLQI. So these are some of the, say, the complicated analysis I'd like to skip for this particular audience. But say if I try to show you, say, the results over here, as you can see that the M on is actually lesser than that of the M off, which actually tells that the quantum dots, or say the perovskites, stay in the on state much more than it is in the off state. And say if I want to talk about, say, the truncation time, which actually talks about the electron trapping, or say the hole trapping. So in the upper plot, you can see that the electron trapping, and the lower plot, you can see that the hole trapping. So what it actually shows that the electron trapping is detrimental, but the hole trapping could be beneficial. So if I want to conclude that, say, the magnitude of on fraction actually increases as we increase the, say, the excitation wavelength, the magnitude of M on is always less than M off. So that's that talks about the good property. This means that it is mostly on the on state. Say the on truncation time, which talks about the electron trapping. So the detrapping actually gets enhanced as we increase the excitation wavelength. The whole trapping time gets enhanced if I increase the excitation wavelength. And all these properties talk about, say, the enhanced PLQI. So that brings me to the end of this talk. So what I could show you that, both from the transient absorption as well as, say, from the single particle spectroscopic studies, that, say, the behavior would depend on the excitation wavelength, and, say, the different regions of the solar spectrum does not affect the exciton dynamics in an identical manner. So these are my students who have graduated in the upper portion and who are currently working. The work that I have showed is from, say, Chayan, Saptarshi, and Swarnali, and the unpublished result is from Shoman. I thank the funding agencies, and I thank you for your kind attention.
Thank you so much for your very interesting, exciting talks that discuss about the dynamics about the both in quantum dots and as well as in perovskite nanocrystals. There are many questions actually. There are people have posted, but like to we take a couple of them. Dr. Rahul Singh has posted, can PLQE affect the anti-stroke photoluminescence as well as the blinking phenomena in the PNC?
Yeah, so actually what you can see that, say, as the PLQI, which is an ensemble level property, as the PLQI increases, so we can actually assume that most of the quantum dots or perovskites is giving you the photon once it is excited. Now that is from the, say, the steady state and, say, the ensemble behavior. Now, if we go to the single particle behavior, so if I would say, I think I have shown you in this particular slide, yes. So as you can see that the say as I go from say 405 to 647, the quantum yield increases. This is say that of the ensemble behavior. And at the same time, say if you can see this particular plot. So here, say these data are from the single particle behavior. And say from the single particle behavior, we could see that the truncation time, say the on truncation time and off truncation time, which is nothing but the electron detrapping rate by the trapping rate. So as you see that, that particular ratio increases as the excitation wavelength increases, and so is the PLQI. So the PLQI increases with excitation wavelength, and say this particular single particle property also increases with excitation wavelength. So this is from the electron trapping. And as I have shown you from the single particle behavior, say from the hole trapping point of view, and in that particular say model, as I had showed you that although electron trapping is detrimental, but hole trapping is actually beneficial. So here also you can see that the longer the hole remaining trapped, say higher is the PLQI. Okay, so this means that both at the say ensemble level, when I see that the with excitation wavelength, the quantum yield, the PLQI increases. So say from the single particle behavior also, we could show that say the say more than one single particle level physical parameters also gets enhanced as we increase the excitation wavelength. So the PLQI at the ensemble level and say different other parameters at the single particle level do correlate with each other very nicely.
Thank you. Thank you so much. There are one more question, a couple of more actually that we're going to take. Last one, which is also Professor Shomokanti Khatua from IIT Gandhinagar. So Professor Khatua has asked that for highly stable crystals, not blinking, how do you make sure that you are looking at single nanocrystals?
Okay, so then as Somo knows also quite well that say you can do what is known as the G2 measurement, and that G2 measurement, deep in the G2 measurement, can show or say can confirm for sure that it is indeed single particle and not say more than one single particle. That's what we are reporting. So I have not shown you any data over here, but a G2 measurement can be done, and a dip at 0 time would tell you that indeed you are measuring at the single particle and not more than one single particle.
Thank you. Thank you so much. And there are many more questions. There are some general questions people have posted. As I mentioned to the participant, those we're going to talk about, discuss all those questions in the panel discussion. Those are general questions. So due to positive time, let us, let us thank our second speaker, Professor Mandal from ISAR Kolkata, for his exciting talk on different dynamics on quantum dot and perovskite nanocrystal. Thank you so much. Thank you so much, Professor Mandal.
Thank you, Nimai, for hosting this one. It was nice.
Yeah, it's a pleasure. Okay, now we move forward our third talk of the morning, and that from Professor Somi Safra from Indian Institute of Technology, Delhi, IIT Delhi. So Professor Safra is going to talk about, he's a professor at Department of Chemistry in IIT Delhi, and going to discuss about confinement in one-dimensional 2D materials. So I request Dushman, can you make him co-host to Professor Safra? Oh yeah, he's already there. We can see your slide, Professor Sabra. So as I've been requesting to the other speakers, you have 25 minutes to talk and there are 5 minutes to question answer. So over to you. Over to you.
Good morning. Good morning, Professor Nimai. Am I audible to you all?
Yes, yes, you are. Yeah.
Okay. Very nice organization of this very timely event, as Professor D.D. Sharma and Professor Prasoon Mandal have already mentioned. We are really thankful to you, Nimai.
No, it's my pleasure to have all this.
We are also thankful to the ICT team and the director. Thank you so much for organizing this event, which is such an important one. My slides are visible, right?
Yes, yes.
I'll just use the laser pointer if it's required. Okay. So I'm going to talk about quantum dots and materials that are derived from these quantum dots. And while quantum dots, as you've seen in the previous two talks, they have confinement in all 3 dimensions. I'm going to talk about confinement in just 1 dimension. So these are 2D materials which I'm going to talk of today. In fact, let me first acknowledge all Is there anything that is troubling you on the screen?
No, we can see it is completely visible, clear.
Okay. Yeah, so let me thank all the people who've done this work, and that's my group. And in fact, the people whose work I'm going to share today, they're all, Sushma is here. She's now a professor, assistant professor in Hindu College. And Shamim is doing his postdoc. He's not in the picture. And Swati is about to complete her PhD. And also my collaborators, Praveen, Pralay, Sashwata, Dibyajyoti, and Professor Samit Ray from IIT KGP, who helped us make a lot of devices. And the funding agencies, of course, DSTDR, DOS, CRB. And since we started making devices a few years back, roughly about 4 or 5 years back, we also started getting a lot of industry projects. So Marmon Holdings and Analinear are the two industries that are funding quite a bit of our projects over here. And without the Central Research Facility at IIT Delhi and also the recently added Sathi program from DST, all these studies would never have been possible. They have all the high-end facilities. By the way, all these central research facilities and the Sathi facilities are open to everybody, and it is through online booking. So all the listeners over here may make use of these facilities anytime they wish to. And in case there's a problem, please do write to me. I've shared my email address over here. All right. So we've already listened to these things, but just to sum it up, we have these nanomaterials which can be classified as 0, 1, 2, and 3-dimensional structures. Of course, the 3-dimensional structures are bulk. And when we say 0, they are confined in all 3 dimensions. 1-dimensional materials are confined in 2 dimensions. And the 2-dimensional materials are confined in 1 dimension. Yeah, sometimes it can get a bit tricky to understand, but you can think of these sheets like the palm of my hand. Okay, so they are confined in this, let's say call this the Z direction, right? And in the lateral X and Y direction, they're free to grow. And a lot of applications have been envisaged and have been realized by the use of these quantum dots, as we've already seen. 2014 is when we saw the first quantum dot television come into the market with Sony, and now we have a lot more companies pitching into the quantum dot televisions. Okay, so I'll not go into so many applications, but just tell you about these various 2D, 1D, and 0D. We know that the exciton Bohr radius of these semiconductors is typically on the order of a few nanometers, let's say about 5 nanometers. And if the quantum dot diameter radius is less than this exciton Bohr radius, then we see a lot of quantum confinement effect. Okay, and this is schematically shown, also explained by Professor D.D. Sharma, and Prasoon also touched upon all these aspects. The thing that I want to show you over here is on the bottom right, and these are the absorbance data for 2-dimensional nanoplatelets, so as to call them, okay, or nanodiscs, if you wish to call them. These are 3.5 monolayers thick. So the way we see is 1 monolayer of selenium, then cadmium, then selenium, then cadmium, and count each anion or cation layer as half. So the way these are made is by using a shorter chain fatty acid like myristic acid along with cadmium acetate. You just heat it to about 200, 240 degrees, and these will form with the shorter chains. Now, this is for 3.5 monolayers, that's 4.5 monolayers, that's 5.5. And with some very great efforts, people also managed to make 6.5 monolayers. But beyond that, the thickness is so much that you cannot distinguish it from a quantum dot. So then the properties emerge more as a quantum dot. Okay, so it's possible to make, these three are much easier to make. This is all cadmium selenide, by the way. Okay, one can make for other semiconductors too, and I'll show you some results from other semiconductors. The very interesting thing is that the lateral dimensions of these materials are typically on the order of tens of nanometers, which is much beyond the Bohr exciton radius. So it is not confined along the lateral dimension. You can grow this in size. You can make it from 10 to 20. There'll be a small change, but that'll be very hardly observable in the luminescence or absorption peaks. Okay. But the moment you change one monolayer from 3.5, you go to 4.5, you see these sudden shifts. Okay. So this is because of the confinement that is along the thickness of these nanoplatelets. Another very interesting thing is that you see very, very narrow full width at half maxima of the emission peaks. You must have seen some of the FWHMs from the quantum dots, the 3D confined quantum dots. In those cases, the FWHMs are on the order of, let's say, well, 30 nanometers. I shouldn't be talking in terms of nanometers because that's not a very good scale for the FWHM. I should be talking in terms of energy. But still, 30 nanometers, well, if you're talking at the same wavelength, doesn't matter. So let's say 30 nanometers over here. And in these cases, this is about 10 nanometers. Okay. So very, very narrow. And why it's narrow is because all of these platelets are exactly the same thickness, right? And that is the confinement direction. Okay. The lateral dimension does not contribute to confinement. So you can get very sharp excitonic features in all of these nanoplatelets and very, very sharp. So when one talks about quantum dot television or some such application, everybody talks of color purity. And if you can use nanoplatelets, then of course they are much, much more color pure. Okay, so we did a lot of things with these two-dimensional or well, these are not really two-dimensional. These are confined in one dimension, so as to say. Okay, and I'll come to two-dimensional materials in a while. We did a bit of things with it. So one of those research works I'm just showing you over here. Now, our idea is to make a lot of heterostructures. Okay. So one of those heterostructures, so Sushma worked a lot on these two-dimensional nanoplatelets, and she worked on cadmium selenide, zinc sulfide, cadmium selenide, cadmium sulfide. And the one that I'm showing you is cadmium sulfide, zinc selenide. And this is not a core shell structure. This is called a core crown nanoplatelet, where you have cadmium selenide in the center, and in the lateral direction, you grow zinc selenide. Okay. Now with this, what you're doing, you're actually not changing this confinement, but you're changing the lateral dimension, right? And because you're making it of a different material, you're making, let's say, take the band edges of these materials. So cadmium sulfide and zinc selenide over here. This tends to form a type 2 kind of a heterostructure. And whenever you are forming a type 2 kind of a heterostructure, although remember I have told you in lateral dimensions, it does not matter, right? The energy does not change. The confinement does not change. But when you make a type 2 heterostructure, then immediately what you see, there's a transfer of so the electron happens to be in one of the materials, cadmium sulfide, where the valence band is lower, and the whole goes, where the conduction band is lower energy, and the whole goes over to zinc selenide, where the valence band is of lower energy for the whole. Okay, and the recombination is also across the interface, and that's the type 2 kind of heterostructure. You can tune this by just varying the thickness of zinc selenide that you've put over here. Okay. In fact, this is the absorption and fluorescence, and there are a lot of defect states over here, which actually you see in the fluorescence. So cadmium sulfide fluorescence. This you can see, and this is cadmium sulfide zinc selenide. The very interesting thing with these kind of materials is you look at the fluorescence lifetime decay. This is on the order of average lifetime decay is typically 1.5 nanosecond. Over here, it goes to about 100 nanoseconds. I'll just show you. Okay, so 40 nanoseconds in this case. But if you can actually do it through, then you can vary it between 2 to about 100 nanoseconds. It really depends on the thickness and the charge carrier confinement. And what you can do is, because you've separated the electron and hole and made it long-lived, because they are on two different materials and they are spread out over the entire area of these nanoplatelets, you can extract these electrons and holes and use them for photocatalytic applications. And in this case, you're shown methylene blue dye degradation and rhodamine B dye degradation. And both of them, one requires the electron, the other requires the hole. And both of them work when you're using these kind of heterostructures. Okay, so I was telling you that, look, these are 2D materials, or these are really nanoplatelets, and let's call them something like quasi 2D materials. A 2D material would be even more spread out in the X and Y direction. And one such class of 2D materials, since we are working on these chalcogenides, if you look at the transition metal dichalcogenides, then these are a class of these 2D materials. If you're looking at these transition metal dichalcogenides, then here in the center, you can think of the transition metal ion. Could be molybdenum, titanium, vanadium, niobium, so loads and loads of them. And you can have these 6 chalcogens, the red ones, coordinated. So it could be a trigonal prismatic coordination. It could be an octahedral coordination. So that's just a rotation by about 60 degrees between trigonal prismatic and octahedron. And these continue. So what you form is these kind of sheets, right? And these sheets are held together by van der Waals forces of interaction between the layers. Now, since these forces of interaction are weak, one can actually exfoliate these sheets. And what you do, when you exfoliate these sheets, you are essentially doing the same thing as you were doing when you were making the quantum dots. By reducing the size, you're increasing the band gap, right? So there's a tunable energy band gap. There's a lot of physics over here because of these involvement of the sulfur selenium d orbitals over here. Those orbital interactions no longer exist when you exfoliate them. And because of that, the direction of the conduction band minimum changes, and it goes from an indirect to a direct band gap crossover, because now you have only the sp orbitals involved in bonding. And the excitons are very strongly bound because they happen to be in this plane. And also because you have a plane, you have very high mobility of charge carriers. And because you have a lot of surface area, you have a good catalytic activity. And these kind of activities are actually divided into 2. One is the catalytic activities, which are known as edge site applications, because edges are the ones where you find a lot of defects. Okay, these are the unsatisfied valencies or defects, as Professor Didi was talking about, right? So you can get counter electrodes or electrocatalysis, even other photocatalysis. So people have done a lot of things over here. Photocatalysis actually is both edge site and basal. So the other one is the optoelectronic or the basal plane applications, where you use them for the optoelectronic applications, or the electron and hole conductivities. So lithium-ion batteries, supercapacitors, spintronics, so on and so forth. So there are a lot of applications that people have reported. And we jumped into this bus in a bit late, because molybdenum sulfide was heavily researched upon at that time. We did start with molybdenum sulfide, But I'm going to show you this work, which is on molybdenum selenide, which was which had a lot of scope over there. So Shamim, what he did was he took the precursor of molybdenum, ACAC, and since we were making all these using the hot injection colloidal synthesis method that has been discussed, we took these selenium precursor, which is nothing but selenium in olyl amine, and heated it to about 240 degrees. And what we got is these molybdenum selenide nanosheets. Now, if anybody has looked at any of these photographs of transition metal dichalcogenides, then these would look like perfect crystalline samples to you. And you would see these very regular arrangement of atoms. But when we look at these, we see these horrible looking sheets. If you look at the TEM images, with all these defects in them. Well, of course, the defects do correspond to the layer thicknesses, and all that matches with molybdenum selenide. But why do we get these kind of crumpled up sheets? And that is because... Sorry?
No, there's someone background music. You continue. I request all participants kindly mute yourselves.
I thought there was a question. Okay. Yeah. So why we get these kind of defects is because using these hot colloidal injection methods, you do tend to get a lot of defects. That's inherent in the synthesis method. And there's a defect where you have much less amount of selenium, which we've measured using ICP. And because of that, the molybdenum atoms underneath, they tend to attract the next nearest neighbor selenium. So these bonds get shortened, right? They are trying to attract the selenium. So these sheets kind of fold. And that's why you're seeing these kind of crumpled sheets like behavior. And that's what gives stability to the defect-laden sheets. Okay, but if you have a lot of defects, then you also have a lot of applications, as we've seen, right? And one of those applications, as I had told you earlier, was the edge site application, which is dependent on these unsatisfied valencies, right? So one of those applications is electrocatalysis. All you do is to put the paste of your material along with some conducting polymer naphthalene and a binder, right? And put it on a glassy carbon electrode. On the other hand, take a platinum electrode, apply some voltage, and then you start seeing bubbles coming out of this. Okay, so this is some acidic solution. And these bubbles start to come out when you, instead of on glassy carbon, if you just have platinum, the bubbles start to come out at about 50 millivolts. So minus 10 amperes is the standard. And when you have molybdenum selenide, then the bubbles start to come out at about 170 millivolts, which is a very good system because the fact that molybdenum selenide happens to be 70 times cheaper than platinum, one could give a slightly higher over potential. And still, you get very good Tafel slopes, which tell that the bubbles are coming out at a very good rate as you increase the potential. See? This goes to, by the way, this green curve is for 6 monolayers, and this one is for bulk molybdenum selenide, indicating that bulk is not so good. You need about 500 millivolts to achieve 10 milliamperes of current. And that is because the more the number of monolayers you have, the electron has to hop across all these layers. Whereas in a single monolayer, it's conduction only in the plane. Okay, these devices happen to be quite stable with time, and the same electron hopping mechanism can also be seen in these impedance studies, that you have very high impedance in case of bulk materials, lower for 6 monolayers, and lowest for the single monolayer material. Okay, all right. So having done this, Shamim thought of why not make some heterostructures with these materials. And the first heterostructure that he thought of was about cuprous sulfide, because it has a good lattice match, 0.329 and 0.379. Both are hexagonal. And it has a 0 EV band gap. So it's kind of metallic, semi-metallic in nature. And this fellow, molybdenum selenide, is first a semiconductor. Okay. So how could he make that? He made use of the defects that you see over here. These defect-rich molybdenum selenide are actually hungry. They need to be passivated, and they are passivated with a thiol, dodecane thiol chain. And the moment you put cuprous iodide, copper having a high affinity for sulfur, forms these cuprous sulfide nanoislands on top of the molybdenum selenide, as you can also see in the TEM image over here. Okay, these are washed about 4 to 5 times before the TEM image has been taken. So using the high resolution TEM image, we do verify that this indeed is cuprous sulfide. In fact, it's not Cu2s, but it's Cu1.97s, which gives a slight metallic character because of the deficiency of these copper, and which induces hole doping. Using the Raman, we can see that, while this is the A1G and the E2G modes in the 2D materials, this mode is not observed when you take a pure 2D material, which is grown using CVD techniques or exfoliation. But this is observed when you look at the colloidal grown molybdenum selenide sheets. And the moment you put dodecane thiol on top of it, the intensity of this mode goes down drastically. And this mode is actually because of the defects in the system. And so you can actually passivate the defects by using DDT, and also by then growing cuprous sulfide on top of it. Remember this, that we have passivated the defects. It will be useful to see what happens. X-ray photoemission tells us the structure that we've been proposing. So you see molybdenum is bonded to 2 species, selenium to 1, copper to 1, and sulfur to 2 species, which essentially tells us that molybdenum is bonded both to selenium and sulfur, so molybdenum selenide, and the sulfur that is coming from DDT and later taken up by copper. Copper is bonded only to 1 because it's just cuprous sulfide. Selenium is bonded to 1 because it's just molybdenum selenide, and sulfur is bonded to both copper and molybdenum. This XPS essentially tells you that selenium happens to be in 2- state, copper happens to be in roughly 2+ state, 1+ state, and later on we'll see what happens to this. Okay, so doing the same thing, Shashwata also helped us understand the band structure of these materials. I'll just present the DOS and partial DOS, telling you that the top of the valence band is green, so copper sulfide, and the bottom of the conduction band is red, which is molybdenum selenide. Okay, so it again forms a type 2 kind of a heterostructure. And when we aligned it with the NHE, then we see that a very small amount of overpotential is required to achieve both oxygen evolution and hydrogen evolution reactions. And we went ahead further and did the same experiment as I showed you. And we could get very efficient oxygen evolution reactions shown in the blue using these heterostructures. And this is from iridium oxide, which is the standard for oxygen evolution reaction. Okay, so at some point of time, let's say about 1.6 volts, 1.23 is the minimum, right? You need for oxygen evolution, but 1.6 volts, the material surpasses the results from iridium oxide. So one can get very good stable results from these. And this is the calculation of the electrochemical surface area, which shows that it's the maximum for the material and not for the individual components. And again, the impedance curves, which supports that our material happens to be pretty good. But after doing the OER, we again run the XPS, and let's just focus on copper. Copper is now both in +1 and +2 oxidation states, whereas it was only in +1. And that allows us to elucidate one mechanism for this. So think of copper 2 and copper 1. The hydroxide comes and attacks the copper 1. Okay, another hydroxide, now it can attack either of the sites. Okay, and it takes away the H+. Another hydroxide makes the peroxo linkage, and then another hydroxide takes the H plus, and then the oxygen is given out using the water molecule, and we are recovering back the catalyst in +1 state. So initially, when you do oxygen evolution or hydrogen evolution, you need to tune the catalyst, okay, or precondition the catalyst. The XRD does not change, right? It's only at the surface that the catalyst changes a bit. What more could be done was to make...
Professor Sabra, 2 more minutes.
2 more minutes. Yeah, thanks. I'm almost done. We could make photodetectors out of these materials. And this photodetector actually can sense in the near infrared. And this is what got us the industry projects, because near infrared is very, very important for both defense and space applications. And this is because of cuprous sulfide, which has the hole, and this is a plasmonic band from cuprous sulfide, which can be also detected. Okay, since I have another 2 minutes, I'll just quickly tell you that Shamim also went ahead and made cesium-lead bromide heterostructures. Now, cesium-lead bromide is not hexagonal, it's cubic in nature, and one could not make heterostructures of these. But Shamim did, and by using a linker technique. So he used aminothiophene. One end, so the thiol end could link on molybdenum selenide, and the amino end links with the perovskite. You know, all the perovskite linkers or passivating ligands are amines. And again, washing, and we can see all these things in the TEM. This is the theoretical considerations making a type 2 heterostructures. The good thing about these photodetectors is that you get a response even at 0 voltage, and that's because cesium-lead bromide happens to be a photovoltaic material, right? Okay, without a linker, Swati started this work, and it so turns out that the molybdenum selenide gets disintegrated, but at the same time, it forms very, very stable and highly efficient cesium-lead bromide. I'll not get into the details of this work, but you can see, or perhaps you cannot see, there are lead selenide islands, and you can definitely see over here the presence of selenium. There are lead selenide islands that get deposited on top of the cesium-lead bromide, and these are the ones that do not allow the halide ion vacancies. So halide ions do not migrate, they plug the vacancies. And this leads to very, very high luminescence efficiencies, roughly about 3 times, 2.7 times over here, and also a very good stability in terms of time. So PL stability with time and the structural stability with time. So we recorded when we published for about 5 months, but now it's more than 1 year, and they're still the same. Okay, so these are very much stable. And the reason is, of course, because of the presence of these surface states which have been removed because of the addition of lead selenide. And that was Dibyajyoti's contribution for the theoretical understanding. This also works for cesium-lead iodide, by the way, and also for the iodide bromide. Okay. And well, so since I don't have much time, I'll just summarize that, you know, I've shown you something about these 2D materials and how these 2D quantum dots and other 2D materials are now gaining so much importance and why they are so interesting to study. And we need to understand a lot of things in these 2D materials. But let me just thank you so much for your kind attention. I'm happy to answer some questions.
Thank you so much. Thank you so much for such an informative talks, Professor Sapra. And there are many questions, of course, there. I'd like to take, I think, few of them. The first questions, asked by Susila. I think she's asked, we always compare 2D material better than 3D. Are these also better than 1D material? Some general questions.
Now, if I have to sell something, I'll put what I'm doing on the top, but each materials have values of their own, right? Okay, so 1D materials are also very important, with such a large, if you're thinking of electron and holes, they just move around in the 1D material too, right? And if you wish to make kind of pillars, then 1D materials are good. If you want to have orientation, then 2D materials are definitely very good because they're flat, right? So you can put them on a surface and you can orient in one direction. Orienting 1D materials, the colloidally grown 1D materials is a bit of a challenge, but orienting 2D materials is definitely much easier. So no, please, let's not compete.
Yeah. Right. So yeah, one more question is there from Gautam. He's asked that if you prepare a monolayer of MoSe2 and prepare a hybrid structure with cesium lead bromide, will the hybrid system will show valley degree of freedom as well? Valley degree of freedom means I do not understand.
Yeah, I think he's talking more in terms of spintronics.
Yeah.
But
Okay.
I don't really. I'm not an expert with that, but I don't think molybdenum selenide does show any valley degree of freedom. But sorry, let me not answer that. Better.
Okay. So I have a question on your last part when you put the lead selenide on top of cesium lead bromide. So, is there any charge transfers or anything you have observed, or you have observed the enhancement of the PL property? Am I right? So that's through the satisfaction of the vacancies, fulfilling the vacancies through lead selenide.
Yes.
So is there any charge transfer from cesium lead bromide, which is supposed to be green band gap, right? Green emission, and lead selenide will be near IR or IR. Is something like that is happened or not?
Absolutely. So you just got me there. So if you look at this, you'll see that the cesium lead bromide, which is red, does not have any absorption. But if you do cesium lead bromide with lead selenide, and the blue one is small amount of lead selenide, the green is a larger amount of lead selenide. Okay. Two different methods of putting lead selenide. You see this background starts to increase, and that is because of the emission, the absorption from lead selenide, right?
Okay.
Emission somehow we do not observe because emission is a different ball game, right? But absorption, and as you increase the amount of lead selenide on top of this, you'll also notice that there is indeed a lot of charge transfer because this is a small amount of lead selenide, and that's the one happens to be the larger amount of lead selenide. Okay, so the larger islands, they tend to form their own band structure, which is, as you said correctly, has a smaller band gap and lies between the band edge region of cesium lead bromide. Okay, a small amount of lead selenide cleans up the band gap, but a larger amount forms its own bands. And because it forms its own bands, and it's not a type 2 heterostructure, it's a type 1 or a reverse type 1, if you want to call it. So it takes over both the electron and the hole to lead selenide, and most of it is on the surface. It interacts with the environment and it is lost.
Okay. Perfect. Thank you. I think there are a couple more questions, but due to positive time, I'd like to stop here. Once again, thank you so much, Professor Sapra, for your time. All of you actually, confirmed with a very short notice and agreed. So you have given a very
much. Thank you so much for organizing this, Nimai.
Thanks.
Have to meet in person.
Sure, definitely. Whenever I think my request to you and Professor Mandal, and of course Didi sir, whenever you are, and next is I think Rajini, whenever you are here, you people are here visiting this part of the country, Kolkata, Bhubaneswar, do let me know. We're happy to have you guys on in person. Our students will be happy to interact. Okay, once again, thank you. We should move on. And our next speaker, which is the last speaker of the morning sessions, Professor Rajni Vishwanath from Jawaharlal Nehru Center for Advanced Scientific Research, JNCSR, Bangalore. And Professor Vishwanath is going to talk about, which is also Didi sir, a little bit discuss about the doping. So Professor Vishwanath will discuss about manganese doping in colloidal quantum dots. So with this short introductions, is over to you, Professor Vishwanath. Yes, we can see your slides. As I told the other speakers, you have 25 minutes to speak and then followed by 5 minutes of question answer. Over to you.
Thank you, Nimai. Can you hear me?
Yes, you are clearly audible.
Okay, and you can see my slides.
Yes, we do.
Okay, thank you, Nimai, for the very nice idea of having this symposium on quantum dots. And today I'm going to talk to you about manganese doping in nanocrystals. In fact, I think DD has made my life a lot simpler by giving all the necessary introduction. So it would help me in actually proceeding with the talk.
Yes.
Okay. Let me just get the laser pointer out here. Yeah. Before getting started with the talk itself, I would like to give a brief overview of what we do in our group. We are interested in surface and bulk electronic structure of these quantum dots, and we largely look at it from the perspective of using dopants as kind of a nanoprobe to look at the electronic structure of the host. We have been working extensively on the dopant emission mechanism, which is what I'm going to discuss today. We have also worked on defects chemistry, perovskites, magnetism, and more recently, magneto-optics in these systems. Okay, so with this, I will, yeah. So, as you're all aware, there's been extensively covered very good talks in the morning, which showed the various promises of quantum dots. And they've shown very great promises for optoelectronic devices and photovoltaics. And perovskites have also played a very important role in that. So today what I'm going to discuss is how do we transition from these quantum dots to perovskites, and what is it we are going to harness from it using manganese as a dopant. And I'm not going to spend much time on this because DD has spent extensive amount of time on this, where you see that there is a nice variation of the conduction band and the valence band, leading to this rainbow colors. And this is taken from the internet. And this is a very famous picture in the internet. And you would all assume that this is how you would look at it. But that is essentially not the case, as was pointed out by Prasoon and DD, that there are a lot of defects which would decay the emission from these systems, and they don't essentially look so bright. And our challenge is to make them look so bright. So that is what we're going to discuss today. So one of the tools which, everybody has discussed various different tools of trying to make them more brighter, but one tool that has also been discussed but not in detail is to use dopant emission, which as Didi already pointed out, we see that very localized states, and you see a transition from this state to this state in this manganese emission, which is what has been extensively observed. So let me now list out the positives and the negatives, as was already highlighted in Didi's talk. The transition metal dope quantum dots shows a lot of advantages, like large Stokes shift, which minimizes the self-absorption. It has higher excited state lifetime, which makes it more stable, thermally and environmentally robust. They also have long PL lifetimes and intense emission peaks. This kind of helps them to reduce the non-radiative losses because they are very efficient in capturing the electron as soon as it's excited. It doesn't allow it to go either to the radiative or the non-radiative pathways of the excitonic decay. However, this was actually, this is an image from Narayan Pradhan's paper, which showed that very nicely, that with putting in copper, he could see that you could see a green emission, but with manganese, yellow emission or orange emission. This is largely the range that is well known for manganese emission, which is basically that the manganese emission is not tunable. And as you have all understood from morning's talks, that tunability is one of the major advantages of these quantum dots, because of which they are attractive. And if they are not tunable, then they are not so attractive. So why is it exactly that the manganese emission is not tunable? We also had this question in one of the talks earlier. So I would like to answer this in more detail. As already mentioned, the manganese emission is both spin forbidden and orbital forbidden. Why should it at all emit? So let me just say what happens. You have an electron which goes to higher excited state. Now this electron has to manganese for some reason is extremely, it's not only more efficient, it's very, very efficient in capturing that electron. Although it is spin forbidden, because what I'm talking of is actually inverting the spin from this at the cost of de-excitation of this electron. And that should not be very happy, but it is a happy scenario. And you see the manganese emission, once it gets stuck there, it has to emit out. But where are the rainbow colors? The interest is in the rainbow colors. So what we did notice is if we can understand the mechanism of manganese emission, then it becomes so much more easier to tune the emission, or if it is at all possible to tune the emission. So let me understand what is happening here. So coming back to my selection rules for these transitions, you see that delta L is equal to 0. It's not an allowed transition. What does happen is manganese excitation can happen through OJ excitation, which is like a energy transfer. These two recombine. At the cost of that, this manganese can get excited. One idea is that, okay, the overall selection rules has to be conserved. For example, spin of these two electron and the hole plus the spin of the manganese has to be conserved. So since manganese itself is not conserved, it has to be compensated by these spins. And if you take in the absence of any magnetic field, this is possible, but various results have shown that in presence of manganese, this is not indeed true. So this spin conservation through these does not essentially work. So what did happen is that we started looking that is it really a spin energy transfer or a charge transfer, and that can really tell us how to go about doing it. And we showed in our data that along with many others, actually, we were not the first ones to show this, that you can see here that manganese, which is this red one, the excitation or the time that it is in that excited state is extremely small, much faster than the undoped case, which is much longer, as shown in the black spectrum here. So you see that manganese is actually very efficient in capturing that electron. How did it, which was basically forbidden emission, become so efficient? And as Didi already pointed out, you can also see that it is tunable. Previously, people thought it's not tunable, but Didi has already pointed out that it is tunable, and it's actually a convolution of all of these. And additionally, there was this rule of crystal structure. You can actually change the crystal structure, and that you can tune the property. So which means like manganese is not acting on its own. Manganese is not staying by itself as 6A1G and 4T2 transition, because these are the atomic like transitions. But manganese is no longer, it's in the crystal structure. There is a role of the crystal structure. It's no longer being very atomic. Then there is a huge lot of things that are unstudied: crystal structure, dimension, surface distortion, hot carrier thermalization, downhill electron transfer. You talk of it and it is all there. So basically what we suggested in our work is that instead of doing that, let's look at how we can excite this. And we're talking of less than 100 femtoseconds because it's extremely fast in capturing. What does end up happening is the hole is passivated by one of the electrons from the manganese, and this now becomes transiently Mn3 plus. And because of which now it is an allowed transition to go to 5T2 state. And this captures the excited electron in 300 to 800 picosecond time scale, and then you invert it. And of course, you do have this manganese transition. So this thermal back transfer can happen, and this shows us basically so what we did show in our work is that this actually can also happen by this transition Mn3 plus, and if it is in a very short time scale, we can see the Mn3 plus transiently through transient absorption. But all of this, now we believe that it is a charge transfer, and this is what happens. But all of this is not going to tell me how to actually tune the band gap. My aim is to tune the band gap. So what did I do next? I said, okay, let me now decide that, okay, these CD, ZNSC are very good in transferring, but there are some other materials which have come about which are probably better in transferring. So let me look at the perovskites. So first thing we did here is we look at the gated photoluminescence. What I do mean by gated PL is that I don't collect any data for a particular time period. And since manganese is very long-lived, I just want to collect data from the excited manganese states only. And I collect that data, and I see that the manganese is very much alive. But what is also alive is this 2.5 EV peak here, which has no business to be here, but it is there. And that is what we tried to figure out what it was. And when we see the PLE also, for spectra which you have like very high band gap, then of course you need the band gap to excite the manganese. But for cases where the band gap is there, much lesser, band gap is only 2.2 EV, but you do not observe a PLE before 2.5 EV, which means that 2.5 EV is necessary to excite the manganese emission. This is from the manganese emission. And you can see very clearly the band gap is here, the PL emission is here, but gated PLE, which is responsible for exciting the manganese, is much higher at 2.5 EV. So the minimum energy required to excite a manganese species is 2.5 EV, such as a transient species. And then we show some transient absorption data as well. And you can see here that originally in the undoped case, you had only one peak, which is the excitonic peak, which just decays. However, as soon as you dope, this manganese, the excitonic peak decays at the cost of growing another peak, which is again at 2.5 EV, and that is much faster. You can see that the growth of this 2.5, which I am calling as PBB bond, peak, this is actually growing at the cost of the decay of this. So suggesting that there is a transient species, and that transient species is probably Mn3 plus. If it's not Mn3 plus, I do not have a data because it's a very short-lived species and I have no means of actually doing that, categorizing. This is where my perovskite halides came into my help in actually, now that I know how this is happening, if I can tune it in some way and actually couple it with the host, which was what I found, we found in this perovskite halides, that it is so much better to couple it with the host. So let's a brief preview of manganese doping in perovskites. You see that in manganese doped systems and undoped systems, this is the band gap, as you can see. When I say P0, it means 0% bromine, and when I say P100, it means 100% bromine. So I'm just varying the halides from chloride to bromide. And if I say MP1, then it means with manganese. So very interestingly, literature showed us that there's a very good manganese emission peak, which is at 2.15 EV here. And as you keep growing, becoming more and more bromide-ish, you don't see that peak anymore. And people just categorized it saying that, no, this is actually undopable. And that's why you don't see it. But if we actually look at the gated emission, which has been my standard go-to, I see that there is a difference in the emission. And not only that, you see that the band edge, which was otherwise otherwise not there, you can see that the band edge has started becoming much longer lived than undoped cases, which was very interesting. So I went ahead and looked at, we went with Shobana Narasimhan, and she did the calculation for the band structure studies. And we see very interestingly that due to spin-orbit coupling, which was previously not considered in earlier calculations, we see that the manganese, usually the manganese levels in all of those 2,6 semiconductors will be here. If this is the conduction band minimum, they'll be here. But you see here, it is way buried deep down. And this was also there in the absence of spin-orbit coupling, but in presence of spin-orbit coupling, it is buried deep down here. So which means manganese is actually interacting heavily with the conduction band. And we wanted to take advantage of this. And if you actually look at the phonon band structure of these things, and I want you to look at only the gamma points, and these are all color coded, you should see that when I go to the chloride, it's largely blue. What does blue means? Blue means it's largely chloride. But when I look at the bromide in the gamma point here, you can see that I have all different colors along with blue, suggesting that there is an interaction of green means lead, red means manganese, and anything in between means a mixture. Like, for example, this is mixture of manganese and lead and bromine, suggesting that there is a lot of vibronic coupling that's happening in this manganese doped cesium lead bromide, and a weak coupling. You can see some just small lighter blue here for the manganese doped cesium lead chloride. So both of them are gamma points. So you can look at it on either side. So what we propose is that there is basically vibrationally assisted delayed fluorescence in these systems. So which means when I look at the manganese emission, and I look at the, when I say manganese emission, I only look at the gated emission, because everything else can be contaminated by the excitonic excitation. So you see that in the chloride, there is nothing. There is only manganese emission. And as I keep increasing, going more towards the bromide, you start seeing a peak from the excitonic peak, which in itself has no business to be there. Remember, this is a gated PL, which means I have rejected everything up to 100 microseconds. Excitonic PL is very fast decaying, so it should not be alive at this high lifetime. The only reason it can be there is if it's being re-excited by something, which is not my light. It has to be something internal, and that internal thing is manganese. Manganese is actually providing the electron back to the host. And because of this, there is a strong coupling. And in these cases where there is no coupling, in the chloride-rich cases, you see that there is no excitonic PL. So when we looked at the Raman, we got before looking at the Raman, we looked at also the temperature variation, because this is a back transfer. So we are looking at temperature specific electronic state with activation barriers. So we see that for the chloride, you start seeing a excitonic peak at around 100 Kelvin. Whereas for the bromide, you already see it at room temperature. This is only 60% bromide. After that, we could not do this measurement because it was anyway always there. So we didn't have a zero line. And then we also looked at the Raman spectrum, and at exactly those temperatures, we started seeing the occurrence of a new phonon-assisted peak, which started popping up at these temperatures. So basically what we are proposing here is that normally this is the pathway where you have, in undoped cases, you have a radiative pathway and you have a non-radiative pathway. Now I am providing manganese as a storehouse of electrons. This manganese is extremely efficient in capturing these electrons, which I have already shown in the 2,6 semiconductors as well as in the perovskite. It will capture this. And in the 2,6 semiconductors, in the lack of any other pathway, it will give you a manganese emission. But in these perovskites, what I would do is that instead of giving this emission through the manganese, which is not tunable, I will couple it with only the radiative pathway of the excitonic pathway. It is not coupling with the non-radiative pathways. All the surface states, etc., doesn't matter for me. The only thing that matters is that manganese is in there and it's able to capture these electrons from the excited state, hold it there like a tank, and drip feed it. I call it the drip feeding mechanism because as and when it decays, only one electron. If there are too many electrons, then you can have self-absorption, you can have this, that, etc., etc. So I do not want to have the too many electrons. The too many electrons are held by manganese, but manganese being so long-lived, it can actually hold it for a long enough time. And as and when it decays, it will start giving one electron to the radiative pathways, and because of which the radiative lifetime will increase. Irrespective of what happens to your surface, irrespective of what happens to your non-radiative pathways, you can have a lot of non-radiative pathways, but manganese only couples to the radiative pathways. Like what was discussed earlier, the pathway, once it comes there, it has to go through the paths that is available for it. And the path that is available for this is only the radiative pathway. So if that is true, then the manganese doped nanocrystal should show a higher quantum yield than the undoped cases, and which we see very clearly in that with increasing percentage of bromine, that manganese had a particular quantum yield and manganese emission almost is zero, but the undoped, but the excitonic emission has actually started going higher in quantum yield. I have had many questions here saying that it is going higher in your quantum yield because your materials were bad to start with, because they're well known that they're 80%, 90% quantum yield and you are starting with only 40%. That is not true. We are starting with 40% because we also, if they, most of these are not corrected for instrumental artifacts. If you do not correct it for instrumental artifacts, these fellows will give me something like 150, 160% quantum yield, which cannot be true. So in order to accommodate that, I have to go to the actual quantum yield, which is after correcting with instrumental. So even this, which looks like 40% without instrumental artifact corrections, will be around 80-90%, and these will be like 150%. Now with all the corrections, it comes down to 40 and 60, which is more realistic. So this is basically a clear demonstration of the back transfer of the to the excitonic states in presence of manganese and corresponding increase in the quantum yield. So basically what I'm talking of is an electron back transfer from the manganese to the host in manganese nanocrystals through vibrational assisted delayed flows. This is actually coined by us for the first time. We are talking of it similar to the molecular counterpart of thermally assisted delayed fluorescence, but here it is not thermally assisted, it is vibrationally assisted. The advantage of this is that it retains the advantages of doped quantum dots. Tunability and sharpness of the excitonic emission is an added advantage because, as you have all seen, manganese has this wide, broad range, and it manganese acts as an electron storehouse and enhances the radiative decay, which means I don't have to really worry about all the surface states and all the other non-radiative pathways which would compete otherwise, and removing all the competition pathways. So basically, band gap tunability is achieved by halide composition, and size composition, we have also looked at that and seeing whether irrespective of the host, this is only, it doesn't matter as a function of size, it doesn't change that much. The back transfer is very particular. It is actually the electronic coupling, and so we can, it's not about the size or the band gap, it is the actual composition that matters. I'm sorry, this should have, this is now published in ACS Energy Letters. I forgot to change this. And we have shown that VADF is independent of the host band gap with size modulation, but it's only dependent on the host itself. And this is some of the data from that. So basically what I have shown is that this clearly says that this is a charge transfer. You do have a back transfer to the excitonic state, and spin memory in nanocrystals can also be retained because it is coming from the manganese. Manganese is known to retain the spin, so we can also retain the spin. And so it can make very good materials for spintronic applications as well. And manganese emission driven by energy transfer from the transient species, but the transient species is formed due to charge transfer. With this, I would like to, and we can show that post-electronic structure is driven by tunable emission and advantages of dopant emission, as well as tunability and sharpness of the excitonic emissions are simultaneously retained through this mechanism. I would like to acknowledge the people who are involved in this, the students who did all the job, and also the funding agencies and wonderful collaborators who did get this. I'm only the person who is presenting it here. With this, I would like to thank you for your attention.
Thank you so much, Professor Vishnathas. Such an informative and elaborate talk that definitely it will be helpful all the students and many of us who do not know much about the doping things. Thank you so much once again. There are few questions, many more questions has been posted on related to manganese doping, but we'd like to take at least a couple of them. The first question was asked that if the delocalizations of the electron in host PNC or QDs are somehow restricted in their conduction band, do you expect the more electron transfer probability to manganese, which subsequently lead to emissions?
So I do not understand what exactly they mean, but manganese is definitely delocalized in the I would say the excited state. I wouldn't say the conduction band or the valence band. Conduction band, valence band is a ground state phenomena, and to extrapolate it to excited state. What is the excited state and what is the conduction band in the excited state is very different. So I would just say that manganese is delocalized and it interacts. It's not an atomic-like state, as was previously believed. It does interact with the host. Whether it is the conduction band or the valence band, and that is very specific to the host itself because it depends on the relative positioning of the manganese levels with respect to the host and all of that. But if you have a better overlap, what I can say is if you have a better overlap, then yes, you can see that manganese will capture it better and that there could be a coupling. So I'm talking of two things here. There is one is overlap leading to capture of electrons, and second is a vibrational coupling leading to handing over that electron only to the radiators.
Yeah, thank you. So there's one more questions for red color emissions. I think it talks about in halide perovskite, red color emissions. Can you use Mn4 plus doping in halides, as Mn4 plus gives red color in few inorganic host? And so, then the follow. Yeah, go ahead.
You can continue.
The same thing that is asked as Neeraj, what are the factors to select the dopant for the halides? But the first part is red color emissions in the halide perovskite Mn4 plus.
So, okay, red color emission, manganese can actually give rise to red color emission, but that we're not talking of manganese 4 plus direct excitation here. We're talking of excitation of manganese through the host. So just because you want red color emission, you cannot use any other manganese host. But if you are, I cannot answer this for sure, but I would believe that in this perovskite, for example, if your host is in the little is capable of exciting the manganese and recapturing the manganese, and that it emits in the red, then you can use manganese as a pathway, like I discussed in the perovskites, to increase the quantum yield of your existing excitonic host. But just because manganese 4 plus in some host can, or in some compound, remember we are using manganese as a dopant and not as a host, not as a compound in itself. we are using manganese to actually just channel it through the host. And that channeling through the host is, first of all, it's not possible to put manganese even 3+. Manganese 3+ is so unstable. You saw in the transient absorption data that manganese 3+ is so unstable that you can only retain it for a few femtoseconds because of these are all 2+. You're replacing in place of Pb2+ or Cd2+. So even manganese 3+ is not stable, let alone 4+.
Right, right.
And
Thanks.
coming to the factors for dopant selection, if you want a back transfer, one of the main thing is the long-lived lifetime. Because long-lived lifetime determines how long it can store the electron. So, for example, we have also done it for nickel, and we see that nickel also back transfers, but it back transfers for a like nickel lifetime is typically of the order of 1,200 nanoseconds, few microseconds, tens of microseconds. So it is holding it only for that. And the second thing that you need to look at is the relative positioning of the dopant levels with respect to the host. If it is somewhere deep in the conduction band or deep in the valence band, then it's of no use. These are the two factors that you have to look at for choosing the dopants.
Thank you. One last question. Why vibronic coupling is higher in case of cesium-lead bromide? Is there any electronic origin of it?
Yeah, so vibronic coupling, I do not have a full answer to it. Why is vibronic coupling happening only in perovskite? I do not have a full answer, but the partial answer is that yes, the dopant levels are better aligned in the bromide compared to the chloride and compared definitely to the 2,6 semiconductors, that it can actually mix well. And second thing is the spin orbit coupling. Bromide has because bromide is a much bigger atom, heavier atom, it has a higher spin orbit coupling. So which allows it to couple better with the spin forbidden states of manganese. And thirdly, these spin forbidden states of manganese, actually, when you have there is an electronic origin per se, but you have to actually see the coupling at, let's say, 2,6 semiconductors. 2,6 semiconductors have the levels, for example, these manganese levels are not very important. They are, see, cadmium has spin orbit coupling, but it's not important because cadmium is a valence band. Cadmium S forms the valence band, and the valence band is not very important in my transient state, or the cadmium S is not very important in my transient state. What is important is the excited state and the conduction band, and those are actually in the perovskite. You see that lead 6p is the most critical level, and that is also contributing to spin orbit coupling, and that's why in lead cases this makes much difference. Whereas in the 2,6 semiconductors, although you have cadmium, which can actually cause spin orbit coupling, they're not in the relevant states. Which are the relevant states?
Thank you. Thank you so much. Thank you so much, Professor Vishwanatha, for your elaborate discussions and your nice talk. And like that, with that, we conclude this morning sessions of
and
this
thank
symposium.
you, Nimai, for this wonderful session. And I hope the students are picking up some things this very interesting session.
Right. So that's how we celebrate the Nobel Prize in Colloidal Quantum Dots for 2023 in chemistry. And the morning session, we like to end with a thanking note to all the speakers, Professor D.D. Sharma, and then Professor Prasun K. Mondal, Professor Somish Chopra, and the last but not least, Professor Rajni Vishwanatha. Also like to thank our Honorable Vice Chancellor to his presence, Professor Pandit sir, and our Director, Professor Bhagya sir. So with this, we conclude, and I do request all the participants, please come back at 2 p.m. after lunch. We have exciting talks lined up. Professor Narayan Pradhan going to give us a talk on quantum dots and from reactions flux to to seeing under electron microscope. Then Professor Angshuman Nag from ISAT Pune also going to talk about on perovskite nanocrystals of electronics. I will share some of our own research, and then Professor Aninda Datta from IIT Bombay going to talk about exciton dynamics in water-soluble QDs. And at the end, there are some panel discussions with Professor Sain Bhattacharya from IISER Kolkata, Professor Bholanath Tham from IIT BSU, where we can going to take up the questions from the students, general questions. There are some general questions are posted. We didn't, take up all those things because we take all those general questions at the panel discussion. So please come back. And again, once again, on the behalf of Institute of Chemical Technology, Mumbai, Bhubaneswar, I'd like to thank all the speakers for your valuable times and do agree on very short notice. And the last, not least request, let's turn on our videos and maybe in Dusman can have a screenshots that we had celebrated these wonderful moments of Nobel Prize of QDs. And Professor Nag is also here, so I can see, Professor Mandal, if you can turn, on your video. Yeah, and I think Professor D.D. Sharma has left. He was informed me he's supposed to fly tomorrow to Korea, so he has something to do. I think Devasis, can you take a screenshot? Yeah. Yes. If you are done, let me know. Yeah, you make it screen and then, yeah, request everyone, if possible, turn on your video and then, yes. Hello, Devasis or Dusman, are you done?
Yes, sir.
Okay, have it taken. Okay. So once again, thank you so much. Thank you so much. I request to everyone again, come back after lunch, 2 p.m. As I said, exciting talks are line up. And again, once again, thanks to so much, Prashunda, Samirda, Rajni, thanks to all of you for your time. I'm looking forward to hearing from Anshubanda and Narayan sir, Anindya sir. Okay, then we like to conclude in the morning. Thank you.
Bye,
Bye.
Nimai.
Bye. This month is going to close, end it, and I'm going to start it. Am I right?
Yes, sir.
No, means it will be like that. It will be still on, right? Continue. Am I right? Are you going to end the meeting or what shall I do?
No, sir. Continue, sir.
Okay. Okay. Then we'll go for lunch. Okay. Thanks, Dusman, for your help. Thank you.
রেকর্ডিং কোথায় কি করবো এটা? হ্যালো হ্যালো হ্যালো
Yes, yes. Pradhan sir.
yeah. So I was just testing my system because my
Okay,
my
sir.
my office renovation is going on. So
Okay, sir. Okay, sir.
I have to make a different computer setup.
Okay, sir. You have time. We are going to start at 2 p.m. Okay, sir.
Okay.
Oh,
So
okay,
it is
sir.
now
Okay.
1:15, right?
No. It is 1:15 to go to 2 p.m. It is 12:45. Now
Oh, okay.
12:45, sir.
So 1 hour
Okay.
15 minutes is there.
Yes, sir. Yes, sir.
Okay.
Okay.
So
Okay.
just can I share something? Can you give me an option for test sharing?
Sure, sir. You can do it. I think you are host. Dusman, can you make him host? Professor Pradhan is here. Can you make him co-host? So he want to test. Dusman? I think I can make him also as a.
Okay. It's fine. It's fine. Not an issue. Not an
Let
issue.
me. No. I think I can't, sir. I think he went for lunch. Our technical assistant. Okay,
So
sir.
maybe 10 minutes before just knock. Okay, me?
Sure, definitely. We'll be there. Okay.
Okay.
We'll quickly go back for lunch and then we'll be there.
Sure.
Okay, sir. See you then.
Done. Nimai?
Yes, sir.
Okay, the video you have stopped it. Okay, so I'm unable to. Okay,
You can see me now? Oh, no. You can.
now it is coming.
Yes, yes.
It's coming.
Yeah.
Okay, good.
So how do you? When did you
Fine,
went?
fine.
You went Monday,
I went to
yesterday morning?
Bhubaneswar. I came back.
Yeah. Yeah.
So
Uh,
too much work now. You see now my office is renovation going on. I had to come out.
uh,
So,
Yeah, it was in weekends. Otherwise, we could have
uh,
visited.
sure.
You came in
Yes,
Saturday, I think.
I came in
Hmm?
Saturday and Monday morning I came out.
That's why I got to know Bamada and then others. They told me, and
Yeah.
uh, and I also went back to Bengal in Kali Puja. So was very much. Yeah.
Anyway, we will meet in December, no?
Yeah, we are meeting in December. Yes. The schedule is as you posted earlier, 21st
Right.
evening,
Evening,
and then and 1 o'clock
22,
will
22,
start after.
23.
Uh-huh.
23 around 5 o'clock it will be closed
Okay.
for,
Hmm.
for 4 to 5 o'clock. But so many speakers, how will you manage? Let me see it out.
Yeah. It's very difficult. So, so Liberato is coming. What is the finalized thing?
No, he didn't come. Yeah, now the
Okay.
Middle East war put many people, they are not coming. There is a visa issue. And his wife, he will come in June, he told. I have to arrange something else for him in June.
Oh, that will be good. Let us plan in well ahead. I will also want him to visit in Bhubaneswar if we can have some 1 day spare time. What we can do, we can also take him to the Puri temples to say, he will be exciting because he used to talk to me during my stay. Very much want to see Indian, all these ancient things. So,
He visited every year. He visited
uh,
Konark, Puri. Last time when he came, we took him
uh,
everything in Orissa, every places in Orissa.
oh, nice. So June you are then planning in ICS?
Yeah.
If June he comes.
Right. So what I need to let me see it out. How do I share the file?
You go to the share screen.
I don't see the share screen.
It should be
Applicants.
on.
Share screen. Okay. Share
Yeah.
screen. Then enter screen, right?
Yes.
Okay. Okay. So
Yes.
now it is visible. Okay.
Yeah, it's not yet.
Okay. You
Yes,
can see
can
now.
sir.
Okay.
Yeah.
Good.
Now.
Okay.
Yes.
No problem.
Yeah. So we'll wait for some more minutes, sir.
Sure.
Okay.
So let it be display. Not
Right. Let it be display. Sure.
okay.
Sir, Professor Prasant also coming or not?
Right. He's coming.
He's coming. Okay.
He's coming. Kovalenko is coming.
Oh, nice. Maxim is coming.
Kovalenko is coming.
Nice. Good.
Okay.
Okay, sir. I will take 3 4 more minutes. You can.
Yes.
Okay, sir.
Hello, Narayan.
Morning, sir. Good afternoon.
Good afternoon, Nimai. Good to see you.
Good to see you. You are back. Had some Viva, right? Done?
Yeah. There was a Viva in VRC. Hello, Anshuman.
Hi, hello, Nindada.
Today I have committed to too many things at the same time. I forgot to update my calendar.
Yeah. Yes. Yeah. Thank you. Still, you agreed.
No, it's a pleasure. Since you asked it, I would not say no.
Yeah.
Just want to say hello to everyone.
Hi, Professor Mal from Nicer.
Hey, Prasenjit, how are you?
Yeah, I'm fine. Anindada, so how things are now?
Is it good?
Yeah, I have another meeting that just after a few minutes, so I just wanted to stay here for sometimes. So, Ansuman, how is going on?
Going on fine. How are you, Prasenjit, after a long time?
Yeah, everything is going on now.
Now we actually mingle very often. We are in
Bhubaneswar.
Even day before yesterday, met Narayana in a conference here.
Yes.
Yeah, I missed that one. I was supposed to come.
Yeah, you were also supposed to come.
Yeah, something came up here, so I could not come.
I think we should start, but still waiting for 2 more minutes. I think, as you know, once you stop one session, sir, we can see your email. You can stop sharing. Pradam, sir. Yeah. Yes.
Okay, please continue.
Okay, then. You are going to leave? Yeah.
No,
now
I'm
it's
here.
fine.
I'll here for some time. Yeah.
Yes. So we'll wait 2 more minutes to start because there are quite a lot of participants but actually once you disconnected, it's difficult to bring back again. Yeah. So Pradhan sir, we're going to start. Yeah. So, very good afternoon, everyone. Once again, very warm welcome from behalf of Institute of Chemical Technology, Mumbai, Bhubaneswar campus, IC Bhubaneswar campus. As I mentioned in the morning that this one online symposium was, we have gathered here in order to celebrate this year Nobel Prize in Chemistry was given for the invention and discovery of colloidal quantum dots by the 3 pioneers in this field. And Professor Labrus from Columbia, Professor Munji Baundi from MIT, and Dr. Ekimov from Nanotech. So this conference where we try to gather all those experts across India, those has been working in the area of quantum dots. In morning, we have very fruitful discussions, scientific discussions, starting from Professor D.D. Sharma, Professor Prasunke Mandal, Professor Sapra, and Professor Vishwanatha. Now we are going to start the post-lunch sessions. Where again the opening of these sessions, we have another stalwart in this area, in India, Professor Narayan Pradhan, who is senior professor in Indian Association of Cultivation of Sciences, and where he is going to talk about the quantum dots from the reaction flux to seeing under electron microscope. So Pradhan sir, is over to you. You can share your screen. And again with you, I welcome all the other speakers for this session, Professor Nag, Professor Datta, and there are panel discussion, Professor Bhattacharya, Professor Pal. And also I like to mention your talk is supposed to be 25 minutes and there are 5 minutes question answer. So I'll give you a signage when you have 2 minutes left. So over to you, Pradhan sir. Kindly share and then you can start. No, we can see, I think, see your presentation. Yeah, you stop sharing. Yes, fine. Now you can go to the full screen. Yes. Perfect. We're not able to hear you. We're not able to hear you. No, your audio is not coming. It was coming, minutes back, but not now.
Hello.
Yes. Perfect now.
Okay.
Now we can share the screen.
Okay. Thank you. So as several talks already, you here in the morning, and there are several talks are also in the afternoon. So and like the quantum dots, which are synthesized beautiful colors. If you can put the quantum dots in the Google, also you could see it out. That several flags of beautiful colors coming, and there are many speakers, several speakers which are giving this talk on the quantum dots, which optical spectra, how they look like to the eyes, and the reaction flux you synthesize coming out under UV light. So that part, as several other speakers are talking, I just skipping those parts, but mostly coming out to the microscopy. So coming out to the microscopy, the talk today I'm going to talk with a single one concept. It will not even take 25 minutes, but I've decided to restrict of a single concept. For example, once you see a solution in the reaction flux, you cannot see in your eye, right? In reaction flux, you see the color. So in the reaction flux, you see color, and then you measure the absorption spectra and the SPL spectra and correlate their size by the Bruce equation. Or you can drop a solution in the TM grids, and then you go into the microscope, how they look like. Basically, is going on. But you see that once you see in the microscope, you see many things, right? It might be a teramera particles, it might be spherical particles, it might be a cubes, it might be a rods, it might be a disk. So the question arises that how come in such a small dimension, such a small in nano, you don't control it like a physically go and cut down. You control it by adding some reactions or doing something in the reaction flux, but under microscope, it's such a small dimension. How those looks like so much particular shape. So that makes quite amazing, but it's a fact, as they all know. But I'll show you one concept on that. So this is that things everyone have seen from the internet, that the start indium phosphide quantum dots, and under the light, this is the Samsung what it has been used for the quantum dots LEDs. So this is the normal light, and this is what it is. But once you take in particles from this, you could see that those are small particles dispersed in a colloidal solution. In 93, it came out as nemitol. 93, and this group in MIT, they have started this one. This is the method which has a breakthrough. So initially, they had used the dimethyl cadmium which is organometallics. Then Peng used simply any salt of cadmium to make it simpler going on. But in the what happened, these guys, Maxim and his group, they came out in a simple way in 2015, the perovskite quantum dots. So these are the small size of perovskite, and those, as you are in the field, you should know that these are the CSPB X3 particularly. That the first paper reported in the 2015. Okay, so these are also quantum dots, but in case of the CDAC, you have a wide tunable of the band gap because of the size. But here, mostly it's a very restricted area of the size tunability, because we don't have yet in the control of the size in the perovskite. We don't have a wide range of size tunability to tune just such a large lens like the CDAC in case of the perovskite. So people used to change the composition, chlorine, bromine, iodine composition, and get tune the color, and mixed composition in the intermediate colors, they get it out. But I just categorically place two here. One is the covalent crystal everything, but in case of the perovskite, it's only the lead part is the covalent bonding, but this halide part, sorry, the A side part, the cesium plus are the ionic. So I just label is an ionic crystal, because a partial ionic is also ionic. Ionic means, it's a very quickly, it's a very vulnerable for the polar solvent, like in water, in alcohol. So they disintegrate, they dissolve. So that makes quite difficult in one respect. But the stories, the science, the story, and particularly the synthesis is beautiful. You just mix everything in the test tube and shake it out. You get a beautiful colors with close to near unity quantum efficiency. You don't have to think about it. Just take any precursor, makes it so easy to synthesize. So there are three colors, as I was talking on the chlorine, bromine, and iodines, taking it out, three colors. So now what happens, even, for a decades of working in this field. So when I started to work on this, in these quantum dots, like I have no place. So, even, that time, like many people, including Angshuman, they are the pioneer in the beginning, from the beginning, and we learned a lot from them. So then when we started this, there is no door remain to, all doors are open that time. If you talk about spectroscopy, talk about the A plus side cations and all these things, people, particularly, I still say that there are a couple of JPC later papers of Angshuman which break the completely concept how this ammonium ion binds to this. So I take that concept that ammonium ion binds on the surfaces or the cesium sites. That is a key point of turning on the entire of my talk today. So when we are searching for the room, we find that one thing, that why these materials are forming cubes. Simple. Why these materials are forming cube. So the first two are the cubic phases, and the middle one, which is more stable, is orthorhombic phase. So still that is also cube. Orthorhombic phase still also cube. Cubic phase also cube. So the common idea, if I don't know even XRD or solid state chemistry, nothing. Cubic phase, I will say cubic phase means it's cube. Urdite phase, I will see that disk, rod, and all these things. Or A, B, and C. A, B are same and C is different. And I will also go for the cube means the cube, the three edges, three facets will be going on ABC direction. But in fact, that's correct. In case of the CSPB I3 and CSPB CL3, there's. But why they go for the cube? Why they cannot form? So that means this is the paper we published in 2019, which are around 4 years after the Maxim reported. But in the 4 years, there are thousands of papers came out. Everything in 1 TM. They study in the physics, they study physical properties. But 1 TM, you will find it out that is cube or platelet. The platelet are nothing but cutting down by slicing the cube. So that was that sourced in our mind that how to tune how to get something in the other than the cube. That's what the strategy was. Okay. And at that time also people are using PbBr2. PbBr2 means in the one precursor giving two sources, both lead and bromine. That was very difficult to decouple. So then what happens, that why a shape occurs? If you go to the crystal has, hello? So
no, nothing. someone's yeah, so continue.
So once you see the crystal, look at crystal tells you the shape. The crystal tells you the phase, and the phase tells you the shape. For example, A, B, C are equal, it's going to be cube. A, B, C are not equal, they can happen different ways. So that's the reason one cases the crystal, it is like you see the copper sulfide. Copper sulfide is getting out a spherical particle 5 to 10 nanometer difficult because the phase does not allow you to grow all three-dimensional equally. So this is what the main concept, though chemistry sometimes break it. Okay, so the reaction chemistry breaks it. So that's what going on. But all those, sure, here these are platonic crystals. These are all are like a 3D system. All are the 3D crystals. A, B, C are more or less same. All are but they are different facets. These are not anisotropic. These are not the rod or wire or platelet. These are all isotropic because A, B, C are same. But how to make that? How will come out from this cube? The window to open for the new materials. So this is the physical method, which is you can see in your eye, you can do as I was talking, but in the reaction flux, what you will do it out. So you will definitely do maximum, you will do it out by heat and trial. You are thinking, but you are not sure it will work or not. This is what it is. But there are concepts are there. This is the crystal. One thing, A, B reaction parameters, you have to put it out. How much you need, which precursor more, which is less. And the second thing, you need to find a ligands. And third, you have a knowledge about the solid state chemistry, how the crystal grows. And then you get these inorganic materials in colloidal on the solution. So all these parameters, you have to keep it in mind to understand how this has been changed. Okay. So that what happens, these are the couple of slides I had shown before. The ligands acts like, if you don't understand much, the ligands just acts like this. This is the format, you get a rectangular. This is the format, you get an hexagonal. So that if you find a template format that says say ligands, you can do it out. Even keeping the same phase of the materials, you don't have to disturb the material space, but you can do it out. So that's what putting out, that's easy for covalent crystal, because covalent crystal like CDS, CDAC, ZNS, ZNO, they give you time. They have patience. You have patience and they have patience. What they do, first nucleation, then slowly they start growing, create facets. But under this is the ionic part like halides. If you inject, it's finished. So there are some people slowing down, but most of the cases, if you inject, it is finished. So the kinetics is so fast, it's very difficult to decouple the nucleation and the growth. So that's the reason you have to have a secondary or vertical entry to tune all these things. So who are the ionic crystals? There are many ionic crystals we collected. Many. You could see it out, cesium, manganese, iron, all those things we have collected. Many. You can do anything in the nanoform. You don't know, many have a beautiful colors. We have no idea about it because these are bulk reported, not in nano. Okay, it's few more. For all the elements, we put it out, some 1200 we collected. And we are doing some, let us see. And this is what the lead series, what is coming it out with the beautiful lead series, what is going on, these perovskites. This is the chloride, bromide, and iodide mixed, all these things, different phase, but particularly this ABX3 are emitting. ABX3 type of the cesium lead halides are emitting. So this is what the paper came out in the Nanolator in 2015. Okay. So what is this actually? If you have no idea about the perovskites, so then it is just a lead halide. This is just an octahedra in chemistry. We know that, like everyone knows, even the class 9. This is a simple octahedra symmetry. That is what is the ML6. So if this is what ML6, so keep on putting everywhere in the 3-dimensional, you get a structure. To bring the stability, you have to put a charge stability is A+, which is ionic sites here. And it should be size, because this is taking the cesium plus, which is the highest size in the periodic table. It fits there. So if you reduce the size, like your systems get destabilized. This is the way the structure goes. This I'm skipping it out. So let's go for a cubic system. Simple. Now my talk started. It will just end at another 10 minutes. So why this is cube? So I go for a cubic system. Very easy cubic system. So I started with 100. 100 means how much I am getting? 100, 010, 001 minus 10. Total number of sites are 6. What you see in the cube hedge. So basically, once it is a cube, so these are the facets you will see. Suppose you have given a glass plate, n number of glass plate. You say make a cube. because the glass plate should be or a 2D sheet you are given. You make a structure where the facets will have similar size, similar shape, similar energy. So you will come out with that, with the cube. But if you go for 110, which is coming to the edge of the cube, so it's coming to how much? 110, 1 minus 10, minus 110. All those possible way are 12. So because here A, B, C are same, so all those alternatives coming out. So if you make it out this table, you get this structure. By default, you will get this structure because you cannot say that one facet I will. It cannot be 11, it cannot be 13. It has to be 12 because 12s are the equal energy. All the equal energy facet has to be there. So that's a by default. You cannot make it 10, 11 or 13. Go for 110. So if you go for 110, it is coming out like this 8. Total combination of 8 plus 111 minus 1 minus 1. So if you target this facet, so you have to have a 8 means either 4 or 8. A 4 or 8 means tetrahedron or octahedron. So if you see that octahedrons of a cubic shape means it has to be 1110 exposed facet. So facet means the atomic arrangements are different. Simple idea. But each facet has a atomic arrangements different. So atomic arrangement difference means you have a different ligands will stabilize. Just choose the ligands. If you choose 3 different ligands, you get three different. Okay, but all are 0D, so it is not bypassing the phase of the materials. Then what happens? You can truncate it. The corners you truncate, you reduce the ligands, heat it out, so it will dissolve in the truncation. So you get many more platonic crystals. Okay, so look out this paper. It was coming out. How much citations and how much the articles view? You could look at it out. From the day it is published in Nano Letter till now, #1 most downloaded article in every month. It is coming it out. Such a beautiful article. But it is coming orthorhombic. I'm not going to details in the orthorhombic, but in case of orthorhombic, as we know that A, B, C are not equal. But in particular CSPB BR3, what happens? A, B are very closer. C is different. Okay. So I will tell later after 5-6 slides that why it gives a cube even orthorhombic phase moving out to later. But now what happens? You see, let's go it out to look out the JCPDS data. This is the XRD and this is the JCPDS data. Okay, the values are from JCPDS. It has nothing to do with my nanocrystal from literature, right? So that's what Prashanjit Mal was talking. I need to clarify that in the Bhubaneswar he was asking. We have taken this one, not this nanocrystal. It's taken from the literature. So then we looked it out. 2R 0.58, because I saw that there are ABR closure. So 2R 0.58, 0.58. So 0.5, 0.002, 110. Let's come to here 002. So C is different. A or B are not equal but close to equal. So the total is coming to be 002 means 002, 00 minus 2. It cannot extend to 200 because 200 is a different spacing. So then 110 is coming to out 4. So total is how much coming out? 6. So once it is coming to 6, by default you get a cube. So once you have a cube means you have these two facets 002, 00 minus 2, 110, 1 minus 10, minus 110, minus 1 minus 10. By default you get it out. That's what everything is coming out in the in the orthorhombic phase. But cubic phase is easy, as I told for chloride and iodide, it's easy going on. So you get a cube. Now what happens? You choose the another 2 which is closure 0.41, 0.413, 410. They are closure. That if that was the closure, it is coming. I circle 020112. If that is the cases, 112, how much is coming? 8 numbers are coming 112, and the other one is 200. How much coming? 4. So total are coming 12. Okay. So it cannot be 13 or 11. It has to be 12 to stabilize this facet because they have equal energy. They have equal spacing. This spacing is nothing but the space between the two planes. So 12 means this is the shape dodecahedron. It can be regular dodecahedron or rhombic dodecahedron. Okay, because of orthorhombic, it is coming rhombic dodecahedron. If you go for the cubic, it's a normal dodecahedron. The 3 shape I saw, they are in the different view only. They are same. Okay, that's what. So if I target this facet, I can break the ice going from cube to dodecahedron. Okay, that's what the story is. So then what happens? Another one is 0.67. and there is only one. So 0.67 is 101. 101, yeah, my permutation combination says the total number of planes is 8. If it is 8, it has to be tetrahedral 4 or octahedral. This, if I can stabilize this one particularly 001, the HKL values 0.67, I should get the octahedral. Okay. But then I can have a combined, a truncation. I can have combined these two. 6 plus 8, 14. These are the 14 shapes. Okay. So this is 14 shape. I can have a combination of these two, 6 and 12. So which can be this shape. So no doubt, it's all by default it is coming. I can have a combination of these three, all these three. Then I have a 26 facet total. I can have a this type of shape. Okay. These are the whole stories. It all depends on what ligands you do, how to modulate. That's what the one I took a CSPB BR3 because field is hot, but this can be implemented for any quantum dots, either a covalent or ionic. The principle remains same. This is a school chemistry. So basically, I need to have a 3 step and 3 ligands. I have to choose what they are. So then while at that time I put a perspectives and saying that how this will happen. Surface has a different ligand, surface has different atoms and different size also in between the lead octahedra where cesium sits out. So I need to put a ammonium ion, changing the size of the ammonium ion to stabilize these facets. Okay. So this is what the primary ammonium ion, as I talk about from the Angshuman's paper. So then I'm trunking out rather than primary, I want to change it to secondary or tertiary. This is what going on. Okay. And all those cubes reported till date are nothing but the primary ammonium ion. There are many cases people say carboxylic acid, some extent this, that, but still now to my knowledge, this is the primary ammonium ion who exclusively dominates the entire cube says, or thousands of paper came out in the first 3 to 4 years of his discovery. So then I was talking about that decoupling lead and bromine. Lead and bromine, if you increase the precursor, lead increases, bromine increases. So you cannot make a system with excess of bromine. Excess of bromine is needed for bringing the high quantum efficiency. So that is the reason. This is the paper Libretto Mana they published using the benzoyl bromide as a source. So that what happened, this is the first paper again after like couple of years, after 5 years it came out again as just this reagent, simple because they could decouple from lead bromide. So while we try to reproduce this, we found surprisingly another reagent with one more CH2 group, that's a phenycyl bromide. So once we put a phenycyl bromide, it standard will go to SN2 reaction. Then what happens? This gives a ligands, which is a secondary ammonium ion. Sorry, tertiary ammonium ion. Two primary. That's what this Suman has did, and he did the NMR mass everything, and we found it out. This is the structures coming out. So we label as a B. Let's take this B instead of A. Take this B. Once you take this B, what is predicted? You get a dodecahedron shape. So dodecahedron shape means this is the as we are talking about 200 or 200 facet or 112, which is the planes having 0.41. So exactly you could see the dodecahedron shape. Okay, this is what it is going it out. So that indicates that soft ionic crystal can also form the ligand chemistry. Now you can have a beautiful self assembly, and this is the structure it is coming. This is a little bit the early stages which you see are a little bit spherical, but these are not spherical. These are all dodecahedron shape, and neither you compromise your quantum efficiency. Okay, so that's what it is coming it out as a new ligands coming out as a B ligands. I put it out. So now what happens? The cube which has just 6 facets, but now I can go is out to the cube I cut down. Cube has a 8 of vertex and of the 14 8 facets. So the 12 edges. So all the edges and vertex, if I changes to the facet, I'm going to turn out to the 26 facet. Same here, dodecahedron, all the 14 vertex, I make it a truncation. I'm going to have a rhombicubohedron or 26 faceted nanocrystal, which is a mixture of both primary and tertiary ammonium. So that's what the structures came out like this by heating those. If you heat to high temperature, the ligands come out. The vertex are dissolved, making a facet. Nimai, you have to inform me for 5 minutes before, okay?
Sure. Mm-hmm.
So this is what you see it out. But these are larger crystal. Don't worry about it. These are larger crystal. Still, it is a near-unity quantum efficiency because the trough state does not interfere much here. And this is the truncation process. It is going it out how the truncation goes on. Okay. So this what happens. The A site ligands what Maxims and others did it out. What the B site ligands what we found it out. And the third structure I'm showing it out, which are A-B mixture. So basically, what will happen? A is transferring to B then. So that is what is going on. Let's see this 26 faceted. And you could see A where I have written A, that is the ammonia primary amine, where I have written B, which is the tertiary ammonia amine. I intentionally put excess of primary ammonia amine are A. So that what will happen that it will remove the B side because they don't like to be their side. B are minimum, it will be getting out. So this is the what I'm expecting. Okay, all the B sides are got out, all the A sides remaining. Exactly what you see the structure sheet coming out. So basically the concept what we produced that select a ligands which can hold a particular facet behind there, that worked. Okay, you could see it out here. This is the way the structure coming out. So it
Sir,
can
you have 5 minutes more. You have 5 minutes.
Okay, no, it's no problem. So that is what it is going out. You can have a staircase type of things if you control it in the same way it is going it out. And that also increases the photoluminescence quantum field from one transferring to one to others, because the first one, which is a 26 faceted, that has a primary ammonia, tertiary ammonia ion. There's a ligand has an issue, but when you put a lot of primary ammonia ion or a ligand, that's turning out to be hex support structures. Then if you do this, you have to check these ligand impacts. If you talk something like that, the heterostructures are forming. Forget about what is that. That's actually platinum. But then I'm adding more of A ligands. So I'm expecting the structures to come out like this. One which is connected along the facet of B ligand that will retain. The other one is turning out to be this one. Again, I'm just putting out. You could see it out. These two. And you see the structures initially after the primary one, exactly it is coming in the same way. So the entire ligand chemistry, it works. Okay. So then what we have talked out, so that many cases of we are coming it out, many cases. So, but before I talking out this one, I missed something to tell it out. So if I go out to the main structure, to the main structure in case of the here, if I go here, that why it is coming, just remember why it is coming a pseudo cube. So if you look at it out the atomic parameters, if you look at out the atomic parameters, these are pseudo cube. Why it is pseudo cube? Because the direction of A, B, C, the cubes, they don't have that. But I don't have that slides here. But to inform you, it's not happening. So what is the atomic parameters of A, which is equal to B? So if you go to the find out the kernel of that A and B, no, what is the rectangular kernel of that, which is coming to be a right angle, kernel. That means root over of A square plus B square. So root over of A square plus B square, which is coming to exactly C. So root over of A square B square, which is coming to AB plane, and that become to equal to C. So now you got a 3 planes, which is the equivalent of equal D spacing. So it is coming equal D spacing in the 3. So that is what that also come a cube. Okay. So in the more opportunity, I didn't have prepared those slides, but this is why it is also even orthorhombic. It is coming. The beauty is that it has an A, B, C. A is equal to B, and A square plus B square or root over is coming to the C. Okay. So now I'm end of the talk here as I was talking. So on the same concept, we have several articles which are not going to talk on this one. And finally, I would say that quantum dot safe, crystal phase matters. So sometimes it's a nature, right? You cannot disturb it. You cannot forcefully. What you do within keeping the crystal phase, crystal arrangement, you have to do your chemistry, particularly choosing a ligand. So ligands matters, crystal phase matters, and then finally what happens if you make your reaction chemistry to be method, then the safe can be designed. Okay, that's what I talk about regarding the taking from the nanocrystal reaction solutions from the nanocrystals, looking the microscope how the safe, and so and discussed one of the narrated one of the concept how cube or non-cube steps are forming. Okay, so I'm done.
Sure. Thank you. Thank you so much. It's always pleasure to see for all of us your such a uniform, beautiful TM images, and on the underlying mechanism, try to explain to all of us all those facets.
Okay.
Yeah. Thank you so much. Open for questions. There are some questions posted already. Take now one. Can flexibility or bulkiness of any ligand correlated to the number of facets, which is the more dominant atom or cube facet and rhombohedron facets? So this is a question posted by Saurabh.
Particular ligands has an affinity to particular facet, because you need to the ligand end side of the ligand, it has to coordinate or take part. In case of here, particularly in perovskites, it take parts there. There are some concept coming out surface remaining. In case of, if you go for CDAC, what happens? Most of the ligands are amine, carboxylate ion, thiol, which are the ligands which are negatively charged, having lone pair, coordinate to the metal sites. This is the primarily more sites. Then what happens? Some anion sites ligands, also thiolapine, and they have developed, or they can also coordinate to the anion sites. But typically more predominant is the ligands having negatively charges. But here what happens? The ligands are mostly positive charge we propose. So that means it has to be coordinate on the surface. So that indicates that in particular ligands exclusively, there is no mixture of ligands. It should come out to be one particular facet, one particular cell.
Thank you. I have a questions. Like you have played with different kind of ammonium ions, primary, secondary. So do you found that phosphonic acid that's going to play for conventional quantum dot in order to change their facets, like nanorod, tetrapod? Does the phosphonic acids can have a role here also?
No. The concept is different here. Phosphonic acid binds to the cadmium side.
Yes.
Okay.
Yes.
Binds to the cadmium side. But here the binding ability is different. But phosphonate ion negatively charges. But we talk about ammonium ions, which is positively charges.
Those bind to the halides.
Correct.
So there's something called halide-rich facets, and cesium is a cation-rich facets. So same thing on the same line, right? These are
a little bit same. It is a little bit same, but I cannot say exactly, because both cases the ammonium ions are stabilizing. Look, in case of the phosphonic acid, what it does, you have a small zinc blend size, right? In case of the small zinc blends, from the zinc blend side, only one facet, only one facets are active. And what phosphonic acid does, one facet, all the positive sides it attack. Once it attack on the positive sides, one side where the cadmium are there, but the tellurium side is open. So it goes in one arm. So there is a total 8 facets, 4 are blocked by phosphonic acid and 4 allowed. But this is something we came out in a different way. First you made, then you dissolve, came out to the hexapod.
Right. Thank you. One more question, so the last one. Sudipta Aich has asked, why the first peak of orthorhombic phase is splitted? Fundamental
these are the splitting of orthorhombic phase is a material's own property.
Signature.
Okay, it's a material signature because they are close to the d spacing. The d value by AB parameter, the atomic parameter which is governed by A, B, C. A is very close to B, but they are not equal. Okay, so they have to have a 2 signatures. They have to have a 2 signatures. So in case of the smaller size, you cannot see it. In the Maxim paper, you see it out, this nanoliter paper, they see 1 peak. But with the course of time, people find it out that there is a splitting. Actually, it is not 1 peak, 2 peak. This is a material signature. It has nothing to do with us.
Okay.
So
with this, again, we'd like to thank you, Professor Pradhan, for your exciting talk and very fundamental explanations. It will be helpful for many of us in order to engineering the facets in perovskite nanocrystals. Thank you so much.
No problem.
Thank you so much. And now we move on to our second talk in the afternoon. Our second speaker in the afternoon is Professor Angshuman Nag from Indian Institute of Science, Education and Research, ISAR, Pune. And Professor Nag, going to talk about perovskite semiconductor nanocrystal for optoelectronics and maybe their applications. So is over to you, Professor Nag. And as we mentioned, you have 25 minutes to speak, followed by some question answer. We can see your slides.
Can you see the slides, Nimai?
Yes. We can see your slides. You are audible also. You can make full screen. Yeah. You have 20 minutes to speak and then some question answer.
Okay. Yeah. So first of all, I thank Nimai for having this meeting together. And from the morning, I've been attending the talks and everything's are going very nice. And the number of participants in an online meeting post-COVID situation, I see more than in the morning, it was more than 200 and still the numbers are very high. It looks like you have done a tremendous effort, Nimai. Congratulations for that. Yeah. And thank you for inviting me. Yeah, thank you for inviting me for this presentation.
Go ahead.
We are celebrating the Nobel Prize in Quantum Dots. And so before coming to my technical talk, let me just go to this photograph that you can see here. So this photograph is taken in 2014. It was in Paris. And there was a conference called 30 Years of Colloidal Quantum Dots. And that conference was there to celebrate the discovery of colloidal quantum dots. And I have highlighted 3 names who were considered as who did the discovery of colloidal semiconductor, which turned out to be quantum dots, named as a quantum dots later. So there are 3 plenary talks in the 3 days of this conference. One was by Louis Bruce. You can see him here. Then Ekimov, this is the gentleman, and then Afros, you can see them. So after that, many things else has happened. And then when the Nobel Prize was announced, you see that it is for the discovery and synthesis of quantum dots. So this term synthesis came in between. So in the list of Nobel laureate, we see a new name that is Monji Bayandi, and Professor Narayan Pradhan was showing that paper of 1993 that was a game changer in synthesizing colloidal quantum dots. And perhaps you can see the co-authors also of that paper, Norris here, Chris Murray, and there are many people who are there. So finally, the Nobel Prize was given to the discovery of quantum dots, and these 2 gentlemen were taken for that. And for synthesizing, we see Monji Bayandi. And it's interestingly, if we look at Monji Bayandi's career, he did his PhD in theory. We know him as an exceptional spectroscopist, but he got Nobel Prize for the synthesis of colloidal quantum dots. And if you look closely, you will see that there is another known face somewhere here, because I was also attending the conference, and I was just 1.5 years old in ISAR Pune at that time, but I presented some of the work that we did in ISAR Pune in a short 20-minute talk in that conference. It was really an inspiring conference to attend. So with this, now if we move to the talk, so the title of my talk is Perovskite Semiconductor Nanocrystals for Optoelectronics. Now, one thing that I often see that, say, if I go to undergraduate class, and if I ask, what is a semiconductor? Very rarely you will get a clear answer of what is a semiconductor. Many people try to say that it is defined solely based on band gap, which is not true. So that's why I thought to say a little bit about semiconductor optoelectronics, and keeping in mind that this is an online conference with students participating from diverse backgrounds. So I'll give a strong or rather elaborative introduction to semiconductors and optoelectronics, and then I'll touch upon what we call as a perovskite semiconductor, and finally some of the early work that we did on perovskite semiconductor nanocrystals. I'll just highlight those. So if we look at the semiconductor research, probably 1930s, 40s, people started working on that sort of not just as a working incidentally, but sort of people started realizing there is a possibility of semiconductor thing. And at the same time, you'll see quotes like this, a very strong quotes by Wolfgang Pauli, that one should not work on semiconductors. That is a filthy mess. Who knows whether any semiconductors exist? And now we know that today the situation has completely changed. In the last 60, 70 years, probably semiconductors have emerged out as one of the most important material. And right now I am able to give this online talk because of semiconductors. So this is a very important aspect. What is the material that made that revolution, the semiconductor revolution? And we know that that material is silicon. Now silicon, now people can make silicon extremely pure. You can see something like 99.999%. So essentially 9 nines are there. And this kind of grade of silicon is called 9N. And this is the kind of grade of silicon that is used in chips and the semiconductor devices that you see. So essentially you get, in a very stringent condition, you get this kind of silicon single crystals. And from potato, you get potato wafers. From this kind of silicon, single crystal, you can get silicon wafers, which are used in chips. If you're talking about solar cell, etc., then the purity can be reduced somewhat. You can go to 7 nines, 6 nines, still solar cell is okay, but chips required further higher purity of the silicon. Now, if you look at the electronic band structure, just a schematic of it, silicon has an indirect band gap, meaning it means that the conduction band that you have, and this is the conduction band minimum and the valence band maximum, they are at a different momentum level, different K values. Because of that, the optical transitions between the band gap at the band gap is forbidden. So it doesn't absorb enough light. Now, when I say that silicon doesn't absorb enough light, the next statement is one of the best known solar cell is silicon. Now, how both the thing can become correct, that it is a poor light absorber, but it's the best solar cell. Now, that becomes possible because of the extraordinary charge transport property. What I mean by that you have a silicon, it doesn't absorb enough light, that's okay, but you make very thick silicon. So even if it is absorbing poorly, if you make thick enough silicon, by the time the light passes through a thick piece of silicon, almost all the necessary lights will get absorbed. Now, when light got absorbed, it will create electrons and holes in the excited state. I'm not showing the holes here. And then this electron that has been created needs to travel through the entire material and reach the electrode. If it doesn't go through that process, you don't get any current out of it. So silicon has this extraordinary property that in silicon, the excited electron can go through more than hundreds of micrometers and reach the electrode before it recombines. And therefore, silicon, in spite of being poor light absorber, can work as a good solar cell, good photodetectors. But always you'll find that those silicon devices are very thick. So if you go for perovskite solar cells, it will be 100 times thinner. Now, silicon is doing wonderfully well. So do we have any scope beyond silicon? Now, in this regard, I find this particular decade, 1980 to 1990, is a very special one. It is the same decade where you have seen the discovery of quantum dot happens, for which we are celebrating today. It is the same decade where the hybrid halide perovskites were studied extensively as a semiconductor, as a photodetector, etc. that time, not really solar cell. It is the same decade where we have seen dye-sensitized solar cell, thin film solar cell, organic electronics. So what is common in all this thing? The common thing in my understanding is that solution processability. Now, prior to 1980s, the semiconductor research was mainly driven by physicists, engineers, and chemists did not have that big role to play. But when the chemists started to make semiconductors through solution, immediately the chemist became the king of material design, because in solution, chemist can do wonders. And we have seen plenty of huge number of semiconductor materials that came out in a very short period of time, in 10, 20 years. And as a result of it, it was not only limited to the research lab. You see that many of the things that we experience in our daily life, whether the display, like when I was in school, the display used to look in a very different way, whether it is TV or computer. The display technology has completely changed. The lighting industry, the LED lights, flexible electronics, all these things that we are now experiencing in real life is because of this exploration of solution processed or other kind of quantum dots or other semiconductors that one can make in solution. Not only this, if you're looking for optoelectronics in infrared range, X-ray, gamma ray region, in all those cases, you need new materials. And silicon will not be able to do none of the things that I'm showing in this slide. So there is absolutely no doubt that still the discovery of new semiconductor has a long way to go, and we'll see many new materials and properties in the coming years and decades. Now, how to think of a new semiconductor? Now, when I go to a lab, I want to make a new semiconductor. What are my criteria? One of the things, as I mentioned also, that I need this kind of band alignment. One need to understand the energy versus momentum, the electronic band structure, to think of a good semiconductor. So this is a semiconductor that is a direct band gap semiconductor. So optical absorption, emission, etc. can happen well. And if you look at the curvature of this band, the higher the curvature near the valence band maximum or near the conduction band minimum, it implies that they have a lower effective mass of electron, which implies that they have a higher carrier mobility. So that's a good for charge transport. So this is the ideal situation. Then you look for then you see the other kind of semiconductor that we mentioned already. This is the case of silicon, where charge transport is good, but optical transition is not that good. Then you have this kind of flat bands. You see, this is a direct band gap. Optical transition is allowed, but it's like almost like a molecular state. It's no longer a band. It's and the width of the band is very narrow. As a result, here you'll see again the charge transport is very poor. So you need something like this in an ideal situation. But then that's theoretically it's fine. But the moment you look at making it experimentally, or because you'll do it at a temperature more than 0 Kelvin, and at that temperature, thermodynamics tell that you have this entropy term, that is the configurational entropy, and a defect in the crystal will increase this configurational entropy, and as a result, you'll get a free energy minimization. So all crystal at a temperature greater than 0 Kelvin will have defects. You cannot get rid of it. And often the defects have this kind of states in the mid gap, and that can trap your charge carriers, and that again spoils your semiconductor. So you need direct band gap, high band curvature, and also less defects. Now, how do I get this thing in a material when I'm thinking of a new material to design? Now, some intuitive thing, probably if I just look from chemical bonding, one of my first criterion is a chemical bond should be a covalent one. So why I need a covalent bond? You think of this kind of semiconductors, that's a silicon. You have the silicon-silicon bond. It's a purely covalent bond. Now, when you have a covalent bond, the orbitals are overlapped very strongly. And because of strong overlap, the band curvature that I was showing, it will increase, essentially increasing the carrier mobility. Even through your chemistry common sense, if you look at it, if I have a covalent bond, the electron needs to travel through this bond. In a semiconductor, the electron needs to travel through this bond. So if there's a covalent bond, electron can move easily. In contrast, when you have an ionic bond, like sodium chloride, you see that an electron will be always be kind of closely bound towards the chlorine, and it will find it difficult to move towards the sodium side, and therefore the electron will be finding it difficult to move. So that's one of the reasons why I need a good covalent bond. And with this very simplistic model, if you look at some of the semiconductors that have been discussed so very rigorously, and I've just taken some of the examples, you look at them, and you look at the carrier mobility. By the way, carrier mobility or diffusion length, what I believe is one of the most important criteria to define a semiconductor, not necessarily the band gap. Band gap, you can see a huge variation of band gap. So you'll see very good carrier mobility, and the samples that show good carrier mobility, whether silicon or in compound semiconductor, you'll see indium arsenide, gallium arsenide, etc. You see the percentage of covalency, it's very high. So covalent bond is necessary. It is sort of a first requirement, but that covalent bond has to have a strong network in the three-dimensional thing. So you also need the structure, not only a single bond, but the chemical bond has to have a structure, a network of covalent bonds that you need in 3 dimensions to get a good semiconductor. And also, if you have a strong covalent bond, then there is a chances of making these defects is difficult in a strong covalent bond. Okay, so with this, I move to the perovskite semiconductors. And if you look at this perovskite structure has been discussed, and calcium titanate, for example, has been one of the important oxide-based perovskite material based on which the structure was named after that. Structure was initially the perovskite structure was associated with the calcium titanate, and then it was generalized to other systems. So if you look at perovskite, you see titanium and oxygen, this octahedral network, the chemical bonds that are there through which the electron will move. The electronegativity is very high, and that's why oxide perovskites are not good semiconductor. The percentage of covalency is poor. On the other hand, if you take lead iodide, as Dr. Pradhan was mentioning, the lead iodide bond is more of a covalent bond, and the electron can move through this covalent bond. The ionic part that is there, the cesium or methylammonium, that is not participating in the charge transport. So you get a better charge transport with halide perovskite, and that's why halide perovskites are good semiconductor, but oxide perovskites are not good, not well known as a semiconductors. And then in halide perovskite, for some reasons, I'm not going to the details, they have defects, but the defects are very shallow in nature, and therefore you can make those perovskites, halide perovskites, at a low temperature synthesis, and in spite of having defect, they show good optoelectronic properties. So this is the paper of Maxim Kovalenko that Dr. Pradhan was showing, and this is the cesium-lead halide nanocrystal. It was published in 2015. It came out in February. And during that time, we were also working on hybrid. We are trying to working on halide nanocrystals of hybrid perovskite, that is, it's an organic part instead of cesium here. But we were not that successful that time, and then we saw that this paper came, and then we immediately adopted that synthesis process, and we could reproduce the work. And then we started to look at some of the aspects of structure and optical aspect of cesium-lead bromide. And as Narayan Pradhan was mentioning, that in the initial paper of Maxim Kovalenko, these crystals were assigned as a cubic phase, not the shape, but the crystal phase was assigned to cubic. But in this paper, which came out only 4 or 5 months after the Maxim Kovalenko's paper in 2015, this paper was the first one to show that these are not really cubic, and you have an orthorhombic phase. Even if you cannot see the peak separation here, you can see these new peaks here, where I'm showing these tiny ones. If you have orthorhombic crystal, you will have here 4 peaks. If you have a cubic crystal, you will have only 1 peak, and that can be distinguished. The same thing we see with DSC data also. You can see the phase transition at different temperature from orthorhombic to tetragonal to cubic, and cubic phase becomes stable only at 130 degrees Celsius or so. If you look at their optical properties, and note that today I'm presenting mainly old work of 2015-16. So many things have changed right now. So essentially, I'm presenting one of the early situation of the halide perovskite nanocrystal case. And so that's why some of those studies are very relevant that time. Now, it might not be that relevant because a lot of advancement has been already made. So what you see is that this is an organic dye, rhodamine 6G, and then you have nanocrystals like cat selenide, cat sulfide, etc. And then cesium-lead bromide nanocrystal, you see the bandwidth. The bandwidth is very narrow, and this kind of bandwidths are required for high definition display. And when the Nobel Prize was announced, they also mentioned about this quantum dot TV, which was, this is 2013 Nature highlight. And in this kind of displays, if I'm not correct, now I think industry uses mainly the indium phosphide based system. And compared to that, the halide perovskite has further narrower bandwidth, and they are a good potential candidate for display technology, high definition display, although there are issues like stability, toxicity, etc. one need to look into. So after looking at their ensemble properties in terms of photoluminescence or structure properties, we went to our collaborator Arindam Chaudhary from IIT Bombay, and he did the single nanocrystals, photoluminescence at the single nanocrystal level. And again, I'll like to mention here that this is the first study of single nanocrystals, photoluminescence or blinking study on any cesium-lead halide nanocrystal sample. And this study again showed that you see 30%, 26%, 60%, about 90% of the nanocrystal remained mostly in the emitting state, and they did not come to the dark state, that is the non-emitting state. Only few of them came to this non-emitting state. And this is again a stark contrast compared to the prior experience with nanocrystals like cadmium selenide, where a large amount of nanocrystals or essentially spending time in the bright state, dark state, and without any capping or not capping, without making any inorganic shell, this cesium-lead bromide nanocrystal remained emissive in most of the time at the single nanocrystal level. We went to another collaborator, Pankaj Mandal from my same institute, IISER Pune, and what he did some terahertz spectroscopy. So through terahertz spectroscopy, without putting any electrical contact, he made, he could measure the photoconductivity, and from there the carrier mobility. And what he sees is that from cesium-lead bromide nanocrystal, it's very good carrier mobility of something like 4,000 centimeters square per volt per second. Now, if you go and make a film out of it and put electrical contact and try to measure mobility, it will be terribly different than this, because there you will be depending upon how the electron is moving from, or hopping from one nanocrystal to another nanocrystals and things like that. But in this kind of non-contact board measurement, it is not done in that way, and it is the intrinsic property of the nanocrystals. So this kind of high carrier mobility is another example, an extraordinary, say if you compare the similar technique, terahertz spectroscopy, cadmium selenide nanocrystal, when people measure, people get typically less than 100. So again, it shows that without surface or without making core shell, etc., the defects are not playing a crucial role, and you get a good semiconducting properties. One can tune the color of the emission or band gap of the emission by changing the halide ions, and that was again was discussed previously also in this meeting. Now, what we did that time, we also calculated the molar extinction coefficient. So when you're looking at the absorption, and per mole here reflects the per mole of nanocrystal. So you take different nanocrystals of cesium-lead halide and then compare with cadmium selenide based on their emission wavelength. So what we see that if it is emitting green or something, then compared to cad selenide, it has a much higher, the perovskite has a much higher absorption coefficient. But this one has to keep it in mind that here the size of the perovskites are maybe 10-15 nanometer, and cad selenides are only 3 nanometers. So larger size is essentially the reason for increase in the extinction coefficient. But nevertheless, if you're looking for single nanocrystal based applications, then it looks like the perovskites will be significantly much brighter, not only because of their fluorescence efficiency, but also because of their strong absorption coefficient. So by that time already, so by 2016, and within 1.5 years of research on the field of cesium-lead bromide or halide nanocrystals, some of the very interesting and unique aspects came out, like photoluminescence quantum yield going to about 90%, very high absorption coefficient, blinking got suppressed, high carrier mobility, long carrier diffusion length. All these are extraordinary semiconductor property. And till today, apart from cesium-lead halide nanocrystals, you take any other nanocrystal, I'm not aware of any other nanocrystal that can have this kind of combination of properties. So that's why I tell that this is a sort of a paradigm shift from semiconductor nanocrystals, starting from the quantum dots that typically we knew about cadmium selenide type to perovskite nanocrystals. And so that's why that's a big change happened after that, and a huge amount of work started to be continued on this direction of perovskite nanocrystals. So we were interested at that time to see that, okay, perovskite structures, defect tolerance fine, but when I have a nanocrystal, there will be defects on the surface. And then that prompted us to look at the surface ligand interaction. And that time we looked at with using different kind of NMR, XPS, HRTM all together, and we came to a conclusion that time that typically in a nanocrystal, you see the ligand comes and bind to the surface, kind of addition kind of reaction. But here in this system, it was like oleoammonium was coming and binding to the cesium side, replacing the cesium side, something like substitution kind of stuff. And of course, after that, a lot of things has changed in terms of ligand chemistry. Professor Narayan Pradhan was presenting some of those, and I'm sure Nimai will be discussing about those ligand chemistry after in the next talk as well.
So, Professor Nag, you have 2 more minutes.
Yeah. So with this, I will also say that some group, not ours, did the electronic band structure calculation with the defect of the surface ligand chemistry that we proposed, and in that case they could see that they did not get enough trap state in the middle because of the surface termination, and that again agrees with the extraordinary property, optical properties of those cesium lead bromide or halide nanocrystals shows. So with this I come to the conclusion. So essentially, I gave a brief introduction, not brief, rather elaborated introduction. Hopefully, some students it will become beneficial for some of the students. And then I emphasize in today's talk the fact that the halide perovskite nanocrystals are sort of a different class of nanocrystals compared to the previously discovered Nobel-winning quantum dots like cadmium selenide, and that's a big shift in the semiconductor nanocrystal research. And you want to know more and get updated, because I was showing data only till 2016. You may have a look at this review article. It's a big 250-page, I think, review article, and that title is State of the Art and Prospects for Halide Perovskite Nanocrystals. And with this, I come to the acknowledgement, and since this is an old photograph of my group, maybe 2017 or sometime, so most of the work that I talked about today is done by Abhishek here, and then this is the present group that is there, and with this I acknowledge ICER Pune and SERB DST for generous funding, and thank you all for your attention.
Thank you so much, Professor Nag. Wonderful talk. Wonderful talk. So much things that we all of us, at least the students who are starting in this area, able to understand. So thank you so much. I really enjoyed. So there are many questions already posted. We'd like to take a couple of those. The first question from NVS Praneeth. Yeah, wonderful talk, Professor Nag. Basic questions with oleolamine and oleic acids. How good will be the charge transfer? And with charge mobility, do you mean charge generated in one crystals moving from bulk to its surface?
So if you have oleolamine, oleic acid capped nanocrystals, the charge transport, there will not be any charge hopping from one nanocrystal to another nanocrystal, because between the two nanocrystals, you have the insulating organic ligands. If you want to make them somewhat charge transport, that's what we did with our collaborators in a couple of papers that I have not showed today. When we made LEDs or photodetector, we washed the surface and remove some of those ligands, and as a result, the charge transport can improve. Now, by charge transport, if you have essentially, the transport should take the charge to the electrode. So if I have a big crystal and if I have an electrode on a single crystal, then yes, charge transport means only the transport through the crystal. But if my electrode is 100 nanocrystal apart, then by charge transport, I mean that the electron travels through all the 100 nanocrystal and reaches the electrode, because otherwise I will not be able to collect the charge and my device or optoelectronic properties will not work.
Thank you. The second question is from Sudipta Aich. For photocatalysis, are indirect bandgap semiconductor better as they can reduce the electron hole recombinations?
So here there is a trick. The trick is that yes, if you just look at theoretically, then yes, indirect bandgap semiconductor might be better because it will reduce the electron hole recombination. Now the first part, if you look at it, another thing that you need, electron hole recombination, it will reduce provided you have a silicon-like pure thing. If there are defects, then electron hole recombination will happen through the defects. But even before that, you have to also think of a photocatalysis meant you are thinking of something that is driven by the absorption of photon. So if you have an indirect bandgap semiconductor, then it will reduce the absorption of the photon also. So silicon works in both. This question is pertinent for both photocatalysis and photovoltaics. Now, in the case of silicon, it works because silicon, the diffusion length, the electron diffusion length in a silicon crystal can go about 100 micrometer. Let me just give you a number. If you take a typical other not that good semiconductor or some other material, the diffusion length will be maybe 100 nanometer, 10 nanometer, 5 nanometer. So that's how the difference, 3-4 orders of magnitude difference that I'm talking about. Yeah.
Thank you. One last question. Does perovskite, asked by Saurabh, perovskite doesn't possess mid bandgap trap state, but trap can be there inside the bands. This trap can hinder the carrier transport as well. Then how high carrier mobility be explained?
Yeah. So if I have what I mean by trap? By trap, I mean there's a state. So I don't know if you can see my fingers. Then there's a state here. If the electron comes here, it cannot jump back to the conduction band minimum. But remember that by band, we mean a delocalized state. That electron can travel throughout the crystal. So if a defect state is not in the mid gap, it is on the inside the band, inside the conduction band, then electron from this defect can very easily come to a nearby conduction band state, and therefore electron can be taken back to the delocalized state. So by trap, we mean localized state, and by band or conduction band, valence band, we mean delocalized state. So if the defect is not energetically far from a delocalized state, if the defect is close to a delocalized state energetically, then electron that occupied in the defect can easily come to a delocalized state and therefore can contribute to the charge transport.
Thank you so much. Such a nice discussion we had. Thank you. Thank you so much for your time, Professor Nag. We all enjoyed.
Thank you. Thank you, Nimai, for having this conference, and good luck for your presentation.
Yeah, it's our pleasure. Hope to meet all of you soon. Whenever you, as I told Professor Pradhan and to you and Professor Datta, and whenever you come to this site, please visit us in Bhubaneswar. We are now in Bhubaneswar. We're happy to host you in person.
Yeah. Same to you. Whenever you come to Pune, just visit us.
Sure. Okay, so let me go ahead. Next will be myself. Let's see how it is. Okay. I asked my student to track the time, so I'll be also try to be on time. So let me do the phone's full screen. I think you have the pointer. Yes. Okay. So I think I can, all of you can see my slides, and I'm audible also. So, again, good afternoon, everyone. Now it's my turn to discuss some of our research in this exciting symposium that we are gathered here in order to celebrate this year Nobel Prize, which is given for the discovery and synthesis of quantum dot, that Professor Nag mentioned. So, as Professor Nag rightly mentioned, there is a paradigm shift after 2015 when Maxim has developed that nanolayer, showcased in this nanolayer paper, how these nanocrystals, which in perovskite nanocrystals, can be synthesized at a simple way. So that has been complete shift, as he also rightly mentioned, the properties, how they are exciting and very ideal for different applications. But as we are celebrating the Nobel Prize in quantum dots, I rather try to keep my slides today's discussion on the conventional quantum dot. The perovskite nanocrystals are quantum dot, but I'm going to talk about some of the work that my group we have been started after I started my independent career in India, and then we have done some of the core cell graded alloy giant quantum dots. So I'm currently associated in Department of Chemistry in the Institute of Chemical Technology, Mumbai, and IOC Bhubaneswar campus. So but before we go to our today's topic, which is graded alloy core cell giant quantum dot. So these are some other activities that, as Professor Nag has mentioned, that we have been also playing with different kind of surface ligands, different kind of approaches, new approaches, and post-treatment techniques in order to make this material quite stable, and with all having a fundamental goal to improve the stability either in ambient conditions in the long term, to use this material for real optoelectronic devices. So these are some efforts we have been doing. The pictures was taken from my colleagues, Quintin's paper in Nanolater, where he shows with Liberato's paper that do simple anion exchange, they're able to tune their optical properties. This paper also just came out after a couple of months after Maxim has reported in the Nanolater. So we have done some significant kind of effort in our group, and these are some representative publications that we have done in the area of perovskite nanocrystals, where our focus on in order to make them quite stable, and for that we have taken two approaches: either in situ synthesis, changing the in situ process, and also either post-treatment process. And there is some effort in our group also in this nanoscale paper. We have been focusing on using materials for photocatalytic reduction of nitrate to ammonia. So there's some electrocatalytic effort going on also. So in today's talk, as I mentioned in the title, it's a graded alloy core cell giant quantum dot. So I think the speakers, starting from the Professor D.D. Sharma and all others, Professor Pradhan and Professor Nag, and even also Professor Vishwanatha and Prashun Mandal, everyone has explained very well about the basic fundamentals of quantum dots. But still, for the sake of the students, these are very tiny semiconductors, a very tiny material. You can see they are sub 10 nanometer size. The schematic shows, so this is the orange ball is semiconductor nanocrystal, one single crystals, and they're surrounded by flexible surface ligands. And these are the real TM images. And those shows, you can see they're highly crystalline when you pop up one of those CDSC quantum dot. And all these things, the buzz, and so much of the research has been going on because of their quantum confined effect, which leads to tunable optical properties. And because of that, this material has been found in several applications, and Professor Nag have shown the display applications, televisions, and all those things. And because of that, the Nobel Prize was given in this year chemistry Nobel Prize. So if you try to understand the unique optical property, you can see here this material has very unique broad absorbance. So the solid lines are showing the broad absorbance. On the contrary, they have a very narrow efficient emission. So that makes this material quite unique compared to other semiconductor. Other means the organic semiconductors. And the reason behind, which is also very thoroughly explained by my other speakers, that the excitons and due to the quantum confinement. And you can see when the bulk material goes to the nanoscale regime, there's a discretization of the energy levels. And thus, due to discretization, the element opens up and is actually, and Professor Sharma also mentioned, the energy is inversely proportional to the length square. And thus, you can simply, if you tune the shape or size of the particle, we can able to tune the band gap. The same material, that's the beauty of this semiconductor material, and to be in quantum confinement region, the same CDSC quantum dot, you can see they can either emit in the blue region all the way to the red, so they can cover a whole visible spectrum. So these are basics of quantum dots, and then this material over the years, as started in 1980s early work, and then 1990s the pioneer work in the chemical approach synthesis, as he mentioned, Professor Nag has mentioned the boundaries work. That actually changed the whole scenario. That in the chemist who can make all these semiconductor nanocrystals in kgs, and in the bulk batches, and we can able to control the shape and size with these unique properties. And that's how the whole ball game started. And because of these interesting properties, these particles are found to be can be applications in several areas: single electron transistors, solar cells, LEDs, laser, quantum computing, in imaging, diagnosis, all those things that have been used. So because of these unique properties, but there are actually quite a lot of challenges people have been found even until 2010 or 2012. the reason you can see here, we have showcased one of the bare quantum dots. Bare quantum means there is, let's say, assume there's a cadmium selenide quantum dot. The bare quantum dots actually suffers of photodegradation. What does it mean? If you keep the cadmium selenide quantum dot as it is synthesized in the lab, after certain time or certain days or months, the quantum yield, the photoluminescence quantum yield goes down. The reason behind the oxidation of the surface. And also you can put them either ambient light or some harsh conditions, there will be degradation of photoluminescence quantum yield, again due to the oxidations. So that makes kind of difficult the use of this material in bare conditions for these practical applications. So this is due to surface oxidation, and that hinders all those real possibilities for different kind of applications. So that's the challenge people have been faced, almost like a decade ago. And then there's a concept came, the core cell quantum dot. Again, I think Professor Dr. Heinz was working with Munji's lab, Boundy's lab. They have first synthesized a core cell giant quantum dot. Later on, several other groups has contributed of core cell giant quantum dot. And there we can able to solve or mitigate some of those problems that I've just described here, surface oxidations and reductions of photoluminescence quantum yield over the time. So you can see from the simple schematic picture, you have a bare quantum dot, the red colored balls, and in the green colored one, we have putting a cell on it. The cell, in most of the cases, is a high bandgap material. So for sake of understanding, we can assume this would be a cadmium selenide, and then the cell could be zinc sulfide. So that's often we call cadmium selenide zinc sulfide. So these core cell structure actually able to mitigate the surface oxidation problem, and we can able to see the quantum yield rises up to near unity. That has been reported. Again, the Boundy's paper in Nature Material paper, my friend Wu Chen has reported CDS core cell quantum dot that goes to near unity, and they've utilized for bioimaging stuffs. So, but still, make this material, once you put a cell, there are several applications which have become handy. First of all, biolabeling, light emitting devices, lasers, all those things become very prominent after putting a cell. But still, there are some limitations was still there. The limitation there, even though we put a cell here, there are people, those are interested, they want to see the particles in single particle level. I think Professor Anindya Dutt is going to talk about it in the morning. Professor Pasunken Mandal had discussed about the fluorescent intermittency. Also, Professor Nag has shown some of the fluorescence intermittency or blinking studies of perovskite nanocrystal. So the fundamentally, even you put a core cell structure until I think early 2010 and so, and still this material, I think the 2008, there's still this material showing prominent blinking. Okay, and that's restrict its applications for LEDs and displays where you need completely blinking free. Now, for understanding of the blinking, there are students, so I like to give you an idea. The blinking is a phenomena, where you can see a fluctuation between on state to off state. It's something similar. You can correlate with our eyelid. We often closes our eyes through the eyelid and opens up. So it's something. These are fluorescent semiconductor nanocrystals. When you see them in a vials, there are millions of nanoparticles. So we see them, they're glowing, right? So, but if you see them at a single nanoparticle level, there are, in a particular moment, there may not be all nanoparticles are giving light out. So, and again, this because of their surface defects, that has been discussed from the morning. There are defects, there are traps. So those things are responsible for this, blinking phenomena. And then even though people try to remove the surface defects, they're putting a secondary cell in this core cell structure, but still they are not able to overcome this issue, how to make completely blinking free quantum dot that could be ideal for these display applications. Whatever the Samsung and LG, the television has been made out, they need a quantum dot that should be completely blinking free in order to have a high efficiency display, display applications. So what to wafer out, I have just now given a hint. We have discussed about the quantum dot, bare quantum dot. Then you want to make a cell because you want to make them highly stable, improve the photoluminescence quantum yield. So that's a core cell quantum dot comes into this picture in 2006 or 2007. And then even the core cell structure cannot make it completely blinking free. And then there's things came giant quantum dot. So giant means it's not very big. In terms of quantum dot, is typically 2 to 3 nanometer in size, but typically the giant quantum dots are 15 to 20 nanometer size, little bigger, and that's why it's called giant. We had many times people confuse, you mean giant means quite big, it's a micrometer scale? No, it's still nanoscale material, but the cell we put it here is quite thick. So you can see from this, the left panel picture, which some of the first blinking suppression studies are done by postdoc supervisor Jennifer Hollingsworth in Los Alamos lab, the Chen et al., this paper in JAX in 2008, the first attempt to how to mitigate the blinking. So they have found it out is not only the core cell or where the cell could be few monolayers or few nanometer thick, but rather you should go and continue to keep thicker cell, much thicker cell, something like 10 nanometer thick, so you can able to completely suppress the blinking. So that's how it is that giant quantum dots comes, and she actually labeled it, Jennifer labeled it, it's called giant quantum dot, and that's how she able to mitigate the issue, that problem of suppression of blinking. Okay. So again, because we're able to suppress the blinking, there are a plethora of applications have been popping up. Those are not actually so much promising before that. The single photon source, molecular probes for single particle tracking, active emitter as a low threshold lasers, of course, robust solid state lighting. So these are the applications makes able to do it once we have a completely blinking free after 2008. But again, there is a but. So there's still some limitations with the core cell giant quantum dot. So far until 2000, almost like 2012, 14, whatever, we have core cell giant quantum dot, we are able to get that red emitting giant quantum dot. The core cell quantum dot, whatever we have in the literature until now, until 2012 and 13, the emission eventually above 600 nanometer. So that means we have giant quantum dot, we have blinking free quantum dot, but those are emitting only in the red region. Okay, so that's the problem. The reason behind in a core cell giant quantum dot is again a very simple, and everyone is aware of it. The hole is restricted to the core. Again, I'm taking example of cadmium selenide as a core and cadmium or zinc sulfide as a cell, or cadmium sulfide as a cell. But the hole is confined to the core, but the electron wave function actually extended to the cell, and that's why there is a huge redshift occur. So then there's still some challenges and limitations. How can I obtain the core cell giant quantum dot? With the one hand, it will be completely blinking free, and the second hand, I should have a blue emitting giant quantum dot. I have a green emitting giant quantum dot, and I already have it in red emitting giant quantum dot, so people can make a white LEDs out of this material. So those are the things that's make us think in these directions. And again, I will try to give you some of the fundamentals here, how this core cell giant quantum dots people have been working on through Jennifer Dubretet group and many other groups, even in a Bounties group, and many other, even Professor Pradhan has worked at it, Professor Sharma has worked on these directions. Just for the sake of students, you can see this is cadmium selenide core, and there is a synthetic approach we follow that's called successive ionic layer adsorption reactions. Through that, we can put a secondary cell, in this case, cadmium selenide core and cadmium sulfide cell. This is some of the real team, images of this after putting 15 to 20 monolayers of cadmium sulfide cell of our papers from Jennifer Hollingsworth group. You can see there are quite big nanoparticle. And now the implication of in thick cell, there is a huge Stokes tip. So that's one thing is good, as Professor Sharma was talking in the morning, the cell absorbance and being one of the biggest challenge of this material when you put in films. If you are at least less than 1% is coming out, because there is there's a very less Stokes tip. The whatever emission is going on, again, the same material is absorbing, which is able to solve by this material, the core cell's giant quantum dot, that the Stokes tip is quite huge. So that is one of the main advantage. But the challenges was how you can make emission or restrict the emission in the blue region, in the green region. So that's how it is. People have invented, and a pioneer work done by Wong K.V. from the Korea, and along with some of our work also, then Lee in Korea, and some of our work in Jennifer's group, that we are able to synthesize and through a graded alloy synthesis approach, okay, and through a composition gradient method. So this is something in the schematic you can able to understand that it is not a two-part synthesis. So far, the people have been synthesizing the core cell material. It is called two-part synthesis. Those are familiar in quantum dot synthesis, they might know. But still, two-part means you first synthesize the CDSE core, and then you clean it up, and then you again put it in a secondary reaction vessel and putting a secondary cell. cell. So like that. But in this case, we're doing everything on a single part. So you have a injection of all the precursors stepping in a time-to-time manner in order to, and with the growth time, and we're able to do a composition gradient cell. And due to composition gradient cell and also initial concentration of the precursor, we can able to restrict the band gap, and slowly you're increasing the band gap, and eventually we end up with a very high band gap cell material. So like with this, with the composition gradient, people have shown, and along with some of our work, that we can able to restrict the emission. So you can see that with this composition gradient, if you grow the nanoparticles for starting injection, that is called 0 minute, and goes out to 60 minutes, you can able to restrict, and as they've been able to do the blue shift of this emission, the emission goes almost like 520. So this is the first time, not first time, the one we have sourced it, and we have tried to adapt it with some modifications. We have synthesized this core cell giant quantum dot, and have tried to see how the distributions of different kind of atoms. So these materials are eventually made of, it is a ternary material made of cadmium, zinc, sulfur, and selenium. Through EDS mapping, we want to understand how the distribution. You can clearly see from this picture, the cadmium certainly confined in the core region. So that shows that the cadmium is mainly on the core, and as you grow the crystals, basically those are zinc and sulfur, but that some traces of selenium also can be found. And this not only the synthesis in the paper I'm not discussed, because main fundamental of this paper that with Jennifer we have published try to understand the blinking phenomena, and indeed all others report as previously that if you make a thick cell, if you're able to make completely blinking free quantum dots. So this is the first report that in a green emitting giant quantum dot which has completely blinking suppressions, and that opens up the use of this material for LED applications. So we in our group here, and we are able to synthesize different kind of these core cell materials through graded approach. This is a routine slide, characterization slide. I can say that absorbance and PLs, as well as the transmission electron microscope. If you grow bigger and bigger, the particles some sort of looks cranky, not in a perfect spherical shape, but they retain their optical properties quite well. Do analyze through their crystallographic XRD analysis to see crystal phases. Mostly they are predominantly zinc sulfide, because the surface, the cells are predominantly zinc sulfide, so they matches with zinc sulfides. So that's not the main things we are trying to look into it. Our idea was to, as we first try to understand that, green emitting core cell giant quantum dot, we made blinking free quantum dot. Later on, we want to see that how this shape and cell thickness are affecting in terms of their stability. Okay, so before that, you can see there are some optical studies and composition study you have done, and over the period of time, if you put more thicker cell, that blue shifting occurs, and this blue shifting happen eventually due to the interdiffusion of zinc to the core. If you let it grow at 300-degree temperature over the period of 60 minutes, the zinc from the cell goes and interdiffuse to the core, and if you have zinc interdiffused to the CDSE core, the band gap pops up, and that's how it is more shifting to the blue region. Has been also supported and understanding from the PL decay, and the quantum eventually, if you grow thicker cells, it goes up, but after certain thickness is again coming down, because there are again we are generating number of cracks and all. So, but our idea here to understand how the cell thickness has an effect in terms of stability in different kind of conditions. So rather we want to see the stability under harsh conditions, our continuous like UV radiations, and we put this all four different thickness dependence giant quantum dot of green emitting, and we put them in under UV light, and we see that when you have very thin cell, that actually the emissions completely quench. So these studies were supported from steady state PL on the top panel and the down panel from the lifetime studies. You can see the thicker cells, and even actually not the thickest one, the sample 3, which is the optimum one, is retention of the PL is the most. So that's we also go further to understand their stability under different kind of environment. One of those how they are behaving if you try to heat them in different temperature, and actually it goes along our understanding the sample 3, which is the optimum size that gives the maximum stability. So in this paper in 2001 in Nanoscale Advances, my students Rahul, they have shows that a certain cell thickness, which is sample 3 around 10 nanometer size, which is good enough, quite stable, optically stable, blinking suppressed, and at the same time, they're quite stable under UV radiation and different temperatures. So we try to figure it out. Maybe this could be the good size for the using applications, LEDs, and so on. So to move on, we further shows, as I mentioned, that our sample 3, which is around 10 nanometer size, the quantum yield is not very exciting. So we got quantum yield around 60%. But when you're thinking about using this material for display applications, eventually by now, by 2010, 20 and now 23, there are almost many people have been reporting material of near unity quantum yield. And near unity quantum yield will be desirable if you want to use this material for LEDs. So you can see that our goal was to make blinking free quantum dot. Our goal was to make blinking free green emitting giant quantum dot, and same time then our goal was blinking free green emission and high quantum yield, near unity quantum yield giant quantum dot. So here in this work, continuation of the work where Rahul did, that we try to adapt some of the analogy that people have been working in other our 2-6 chalconicate quantum dot, that I try to people use different kind of ligands, and to be specific here, people have been used the G-type ligands in order to passivate the surface traps to improve the photoluminescence quantum yield. Well, for that, we have used the metal halides, where metals are having empty orbitals, so that can use in order to satisfy the valencies and in order to remove the defects. So we thought about that it could be possible. There are some theoretical studies, and there are papers in Jackson on Indian phosphites. On that basis, we thought about it, and indeed we had a different kind of metal halide treatment of our green emitting giant quantum dot. And there are some, these are some routine characterizations we want to show that before treatment and after treatment, there's no visible changes, not in shape and size, not in absorbance. And definitely then the striking change come from this PL data. You can see there is a huge enhancement in the PL intensity. And eventually from this PL KOI and with the different kind of salts, you can see that we're able to close to almost more than 95% of quantum yield. So thus with this, we're able to find it out a solution that on a giant quantum dot, it could be blinking free. At the same time, it could have a very, very high quantum yield. So that could be a very ideal material for display applications. We got further in order to other understanding on the same, the G-type ligand treated giant quantum dot, like we have seen their stability under UV light or a different kind of temperature. And then finally, we also fabricated a down conversion LEDs. You want to see their electroluminescence behavior, and you can see from these LEDs, and in this is from the CI plot, they're very highly color pure, but these are down conversion LEDs. Our future goal could be use of this material to fabricate the real LEDs, to understand how the charge transfer occurs and actually how this material behaves, or how the stability of this material behave if you put it in the layer by layer structure. So this is something we're looking ahead. So in this work was also a continuation of Rahul's work. In this, in this paper, we have shown that how a simple G-type ligand treatments we can use and make this material highly fluorescent, and making them two things, like completely blinking free, and then almost near unity quantum yield. And then this is almost very end of my talk. We also want to understand, as I've been talking about, using this material either for LEDs, either for solar cells, and then photocatalysis. Eventually, we are trying to go further in the photocatalysis directions. Then the first thing comes into mind, then you need a robust materials. So that's why you need a thicker cell. But at the same time, if you make a thicker cell, you're going to restrict your charge transport. So that's something, tug of war, how to overcome these problems. To understand how the cell thickness behave in order to transfer the charges, again, we adopted a simple techniques that many people have been using. They have taken a standard electron and hole acceptors in order to understand. So here you can see in these studies, again, we have taken help from steady state PL as well as lifetime studies. We have sequentially added with the same concentration of 4 different sizes of giant quantum dot, and we have added the electron acceptor and as well hole acceptor, and we have found, yes, indeed, the cell thickness played a major role, where the thinner cell, they have a fast charge transfer properties, which is found in both in electron as well as hole. So in this also further to understand through the Stahlbommer plot, the sample 1 sample 1, which is have a higher charge transfer rate, both in hole and electron, but it has the thinner cells. So that's the contradicting that if you put a thicker cells, you are going to restrict the charge transfer, but if you put a thinner cell, you're going to how to make it stable, photostable. So there's something optimum size. You have to go ahead with this. So with this paper in inorganic chemistry, we try to understand how the cell thickness matters in order to have efficient charge transfer. But we found that around 7 nanometer size, where we have the core could be around 2 nanometers. So total 7 nanometer size of core cell graded alloy giant quantum dot could be ideal in order to, if you want to use this material for applications where charge transports are very important, like solar cells, catalysis, or photodetector. So not only giant green emitting giant quantum dot, our effort has been also there in the blue emitting graded alloy giant quantum dot, where we're able to synthesize different size, highly spherical, very high quantum field samples, and we have been investigating their properties and directions. I'm not going to able to share all those things in this talk. So now like to before the technology, I'd like to conclude what we try to convey here, that starting from 90s, the quantum dot field that started Munji's work in colloidal synthesis, where have a CDSA quantum dot, they have very good optical properties, quantum confinement effect, but photoluminescence was very poor, around 10 to 15%. And then they goes on finding the way how to make it further high. Then there's things called core cell structure. In the core cell structure, you can see they able to improve the photonic quantum yield, but some hurdle was still there, how to make them blinking free. Then the Jennifer's goal and Dubrett's goals came forward in 2008 and 10, that if you make a thicker cell and then you're able to reduce all those defects, OJ process, blinking free. So, and then there's a problem how to make green and blue emitting giant quantum dot with blinking suppression. So then we have adopted, and with some modifications, about the composition gradient method, and we try to understand the blinking phenomena. Thereafter, improving the photoluminescence properties, charge transfer altogether. And this is something we like to share with all of you. At the end, I'd like to thank all these people. These all people, only one person is with me right now. All of them are away. The pictures would circle Rahul, who has done all the work, because in the lab, all people are mostly focused on in perovskite as a paradigm shift, as Professor Nag says, that after 2015, we almost shifted to perovskite nanocrystals. But Rahul has been was working with on this direction. He's now graduated. He's in Japan, in Riken, doing his postdoc. And then this is a very kind of old picture. We have some new people in our group has to take this. Let's see. I'd like to thank from the funding. This project was funded from the SARF DST for the giant blinking properties of blue and green emitting giant quantum dot, and also generous funding from an SRMFP. Before moving to ICT Mumbai, I was in SRMFP as a assistant professor, almost like close to 5 years. So the almost all the work what I've shown in the giant quantum dot has been done there. So thanks to the support from SRMFP, and also like to thank my current Institute of Chemical Technology, Mumbai. We are setting up lab here. People, students have been started working. Hopefully, we meet again in the near future. We try to show some of the work we have done here. Thank you so much for your time. I'll be happy to have questions. Thank you.
May I ask a question, Nimai?
Yes.
For the quantum dots that don't blink, how do you ensure that they are actually single quantum dots?
So again, I think this question was asked before to Professor Prasun K. Mondal. I think the majority technique, again, I'm not the spectroscopist. When we have been working in Jennifer's lab, that we have a side-by-side lab with Professor Hatun. So I was closely seeing how they do. Basically, what I understood, and I have also done a few times, it is the G2 measurement. From the G2 measurement is to confirm, if G2 values are less than 1, they is to confirm, and those are kind of a single nanoparticle. I think
less than 0.5.
Less than 0.5.
So I think it is better to do those measurements.
Sure. Actually,
because
sir, in the JCP paper, we have those measurements. I didn't show
I see.
We have those papers.
Then it's fine. That's great. Thanks.
Any more questions? If not, I think I need to move to the last speaker. Then we have a panel discussion. So let me stop sharing. Okay, so the last talk of these exciting sessions we had from the morning, again repeating, we have been saying that we are celebrating the Nobel Prize of Chemistry that has given for the invention and synthesis of quantum dot. The quantum dot, so-called quantum dot community has gathered today. Though we have missed few people, I have reached out also some of them, but it's very difficult to get all people together on the same time, but still we have a very good, renowned people. Those are pioneers of quantum dot research in India. We are able to bring them together. And then the last talk of the day by Professor Aninda Datta. He is, a very renowned spectroscopist, has done lots of work in the area of spectroscopy studies of quantum dot. And Professor Datta from Department of Chemistry, IIT Bombay, going to talk about exciton dynamics in water-soluble quantum dots. Sir, now is over to you. You will 25 minutes to speak, and there are 5 minutes to question answer. I remind you in 2 minutes advance. Yeah.
Thank you very much, Nimai. Yeah. Thanks for the invitation. It is indeed a matter of great happiness and joy for us that the Nobel Prize this year has gone to the field of quantum dots. Our group is really a very late entrant in the field, and even though my age is more than people like Nimai and Anshuman and others, for us, they are actually our teachers. We have learned a lot from the work of all the people you have heard today from the morning. And that is how we have taken a few baby steps in this direction. The reason why we got interested in the first place is that, as Nimai has said, we are spectroscopists. And for the last 20 years, we have read many, many papers in which we see that the kind of things that happen in quantum dots is absolutely intriguing and astounding. There's so many things that can happen. You promote an electron to a conduction band, fine. But then there can be a recombination, a straightforward recombination, and you get light out of it. Or maybe you don't get light out of it. But there's so many other things that can happen. Electrons can get trapped. Holes can get trapped. There can be more than one exciton per quantum dot. There can be what are called Auger processes. And I believe we have heard about all of these throughout the day today. And that's another advantage of being the last speaker of the day. Whatever could have been said has been said already. So all we have to do is present our result. But what I'm saying is that this is the reason why we got interested in this field in the first place, because there's so many fascinating phenomena that happen post-excitation. I seem to have a problem. Oh, now it's working. You can still see my slide, right?
Yes, we can see your slide.
Oh, great. So, for the last 21 years or so, our group in IIT Bombay has worked mainly in time-resolved spectroscopy of organic molecules, by and large. Of late, we have been interested in fluorogenic molecules, molecules that are not fluorescent per se in solutions, but you can make them fluorescent by providing specific inputs. And using these molecules and also conventional fluorophores, our main activity has been to look at complex microenvironments. Since 2014 or so, we decided to get into this field of photoluminescent semiconductor nanocrystals, essentially because we wanted to understand what all is going on. 2014 is fairly late. As Narayan said, when he entered the field, all the doors were open. When we entered the field, all the doors and windows and all other points of entry were practically closed. So we were thinking where to begin. And there, we started working with a system in which Nimai has done some very significant work when he was in Singapore. We worked with nanotetrapods. We looked at these, we'll come to that, but before that, let me speak a little bit about the techniques. In the morning, you've heard from Proshun about time-resolved spectroscopy, mainly transient absorption. We use transient absorption as well as time-resolved photoluminescence from femtosecond to nanosecond time scale to look at the dynamics. We have started working in single particle, like what you heard from Proshun or from Nimai. But what I'm going to talk about today really is quantum dots that are mobile, that are in solution. To look at them, we use something called fluorescence correlation spectroscopy. So what happens in this technique is that you take a drop of liquid, drop of solution, and put it on the slide and focus your light onto it. And then look at the fluorescence signal from the focal point. You do a confocal detection. Now, if you have a molecule or a particle that is in solution, it is not going to remain stationary, right? It's going to diffuse in and it's going to diffuse out. So as it diffuses in to the central part of the beam, the fluorescence intensity or PL intensity is going to be maximum. As it diffuses out, it's going to fall. And that's going to keep happening as long as you watch. So the signal that you get is something like this. And for the uninitiated, this signal would actually look like noise. But it is not noise. It is definitely correlated signal because it arises out of diffusion at the moment. We'll add on something else in a few moments. So if you only consider diffusion, what happens is you can actually try to see whether it's correlated or not by constructing what's called a correlation function. And the correlation function falls off with time. The reason why it looks like this and not an exponential decay is it is still something like a multi-exponential decay, but the x-axis here is logarithmic because in this experiment, you can actually look at many different time regimes at the same time. So if there's only diffusion, then this is the kind of equation that one uses and one worries about what is the diffusion time. And from that, you can find out the diffusion constant. That is conventional chemistry. The other quantity that I'd like to draw your attention to is 1 by n, where n is the average number of bright molecules or bright particles in the confocal volumes. This, interestingly, is reciprocal of the time zero signal. So here we have an experiment where if the sample is more photoluminescent, then the time zero signal actually decreases. So for that reason and for others, you want to use as dilute a sample as you possibly can. Now, this is the scenario if there is only diffusion. But then more often than not, you have other things happen. If you have processes that take these molecules or particles from bright state to dark state and back from dark states to bright states a few times while the particles are in the confocal volume, then this autocorrelation function gets modulated by those fluctuations as well. And that is one of the things that can show up here is blinking. A few moments ago, we heard from Nimai how they have prepared quantum dots that don't blink. But then that is interesting because quantum dots usually blink. And if blinking is there, then you have many blinking processes for each run through of the particle for the confocal volume. And that is when it gets modulated. I'll show you later how it gets modulated. But then the point is you can look at not only diffusion, but also excited state dynamics using FCS. So that is a small introduction I thought I'll provide. Using these techniques, in 2014, we decided to enter the fascinating world of the ultra small, which has been ultra big for a long, long time. And the Nobel Prize of this year, I'm sure, is sort of the first of many that are going to come. I do not need to spend time on this slide. You know already the diverse applications that one can devise of quantum dots. As I said, the first system that we worked with were cadmium selenide nanotetrapods because there was still some scope of looking at exciton dynamics there. And that is, nanotetrapods is the reason why Nimai and I got to exchange our first few messages, you might remember. Now, we learned how to make nanotetrapods, and to our dismay, we found that they're hardly photoluminescent. The quantum yield is, I don't even want to say what it is. It's written here, 1.7%. Now, that is laughable. From Nimai, you heard that people talk about quantum yields of unity, 100%. And there, if you say we have a quantum dot with a quantum yield of 1.7%, what sense does it make? For us, it did make some sense because they provided us with the platform that we required to learn how to handle these quantum dots and how to make sense of the transient absorption data of these quantum dots. But then we also wanted to increase the quantum yield by some mechanism. This morning, you have heard Professor Ranjani Vishwanatha. She is an expert and she's done phenomenal seminal work in doped quantum dots. We decided to tread that path and we decided to dope our nanotetrapods with copper plus. Why copper plus? We'll come to that in a moment. But let me just say that upon doping with copper plus, the quantum yield increases from 1.7% to 38%. Well, even 38% is much less than 100%, but it is much, much more than 1.7%. More interestingly, the lifetime becomes something like 500 nanoseconds. And now it is time to say why. The reason why this happens is that, remember, we are doping with copper plus. So copper plus is a good hole capturing agent. So the moment we produce the exciton, copper plus can actually extract the hole. And now, if there's no copper plus, what happens is that the electron wave function and the hole wave function are delocalized over the entire quantum dot. In the presence of copper plus, the electron wave function is still delocalized, but the hole wave function is confined on that one copper plus ion that is there in the quantum dot. It is sort of analogous to what you heard from Nimai about the core shell quantum dots and from Amshar. So the point is, since the spatial overlap of the electron and hole wave functions is disrupted to a very, very large extent, the recombination is no longer easy. So recombination time increases. How much? This much. Actually, even this 5 nanosecond is a hopeful statement. As you see here, the PL of the undoped quantum dot actually is practically over in matters of tens of picosecond. However, upon doping, we get a 500 nanosecond component. And since the lifetime increases so much, that is what is the driving force for the quantum yield to increase as well. So this is what we learned. We also doped our tetrapods with silver plus, but the results there are not half as interesting. Copper plus is really our champion quantum dot. But we are not happy completely because all that happens with tetrapods is in toluene. We want to work with water-soluble quantum dots because we are starting some collaborations in which our collaborators like Professor Devabrata Maiti are interested in photocatalysis in water. Shayan, who is going to conduct the next session, is also a co-author in that. I'm not a co-author, but my student is there, Shucheta Banerjee. Right. And also, we are interested in bioimaging. For that, you better have a quantum dot that is soluble in water. So, to cut a long story short, we learned how to make aqueous cadmium sulfide nanocrystals. These are PEI coated. The synthesis is not new. We took a method from literature, but then we modified it a little bit, and we got a reasonably good quantum yield for these as well. Not only that, using transient absorption, we could work out the exciton dynamics completely. And then we also tried to see whether we can devise a model application. And what we found was that for this particular cadmium sulfide nanocrystals, the PL is quenched significantly and specifically by lead, which is kind of good because you want to detect lead. But more importantly, the questions that we could ask given the scenario is that why lead and what is the mechanism? Again, to cut a long story short, we learned that the quenching is specific to lead because for all the other metal ions that we studied, we looked at about 25, PEI can trap them very nicely. So they don't get to reach the surface of the quantum dot. Lead and PEI don't get along well together. So lead can actually reach the surface. And generally, in a situation like this, the usual suspect would be photoinduced electron transfer. We could also establish that it is not just electron transfer, a hole transfer is also involved. And more recently, we have worked with copper indium sulfide nanocrystals specifically because we wanted to avoid the heavy ions. I suspect I'll not be able to get to copper indium sulfide today. It's not a new material. A lot of work has happened there. But again, what we saw is that we could see that by putting a zinc sulfide coat on copper indium sulfide nanocrystals, we could make them significantly more photoluminescent than what they are without the shell. And using FCS, or rather fluorescence lifetime correlation spectroscopy, FLCS, we could understand the mechanism goes way beyond simple protection from water and simple stoppage of the quenching by water molecules. But I don't think I have time to get there today. It's already 13 minutes, 48 seconds. So let me talk about the other system, I told you that we could get a reasonably good photoluminescence from copper-doped cadmium selenide nanocrystals in toluene. Now, then we thought, can we use the same strategy? And can we dope cadmium nanocrystals in aqueous medium with copper plus? Again, using a literature method. None of the synthesis is ours, but what we have understood is that whenever we do synthesis, we have to modify the literature procedure a little bit, otherwise it doesn't work. So we could prepare cadmium sulfide nanocrystals that are copper doped to different extents, and we found the doping levels from ICP-AES to be 0.2, 0.3, and 0.7%, corresponding to, and this is an important number, I'll tell you why in a moment, corresponding to 0.74, 1.1 to 2.55 copper atoms per quantum dot on the average. All right. So with this, what we see is the immediate effect of copper doping is that the photoluminescent quantum yield increases significantly, and the lifetime increases even more significantly. Once again, we get a lifetime of about 530 nanoseconds, and we've already discussed why that would happen. We could find out the spectrum of the spectrum involving the trapped hole, but let's not get into that for the moment. Let's get to the FCS. Now, when we look at FCS of nanocrystals, this is not the only thing that's happening. As we said, it's not just diffusion. There is blinking, and because of blinking, we need another factor, a modulating factor for this G of tau, the correlation function. Oops, sorry. And this is what it is. Once again, not our discovery. This is very well known. In fact, this was worked out for molecules to start with. This T that you see, the dark fraction, is reminiscent of what was done for the molecules, T for triplet. All right. So the moment we try to do this kind of analysis of our FCS data, we get insight into not only the average number of molecules in the confocal volume, but also the dark fraction, the blinking time, and this beta is something that tells you about how heterogeneous the system is. If beta is equal to 1, then you get a simple exponential decay. If beta decreases from the value of 1, it means an increasing extent of heterogeneity in the system or in the choice of recombination processes that are available. This is what we get. Upon increasing the doping level, we get an increase in the number of bright particles in the confocal volume and decrease in the dark fraction. We also get an increase in beta. Beta tends to go towards 1, which means that upon doping, the recombination pathways, for the recombination pathway, there's a narrower choice because the recombination would now preferably involve the captured holes, trapped holes. But then what we see is that we see an increase in N, fine, but there's a limit. After this doping level of 0.3%, it turns around. We see an increase in beta, yes, but up to a doping level of 0.3%. Then it turns around. And this is where those numbers become important. You remember, 0.3% corresponds to an average of about 1 dopant ion per quantum dot. The next one has an average of more than 2 per quantum dot. I mean, we'd have loved to do many more in between, but we don't really have that kind of synthetic control. So what we learn from here is that too good is no good. You cannot keep on increasing the doping level. If the doping level is beyond a certain limit, then the dopant ions talk among themselves. And they are no longer as good dopants as they were when there was only 1 dopant ion per quantum dot. That's what we learned from our FCS. Then we go to a different question. You heard about, again, from Nimai's talk, you heard about photoinduced electron transfer to substrates, and that's very interesting because that is the starting point of many photocatalytic processes that one can devise using quantum dots. So we did something that is very well established for photochemists. We used methyl viologen as a model electron acceptor. And the question here is this. All right. If you take any quantum dot, the electron is in the conduction band and it can be donated to methylphthalein. That is what your PET process is. If you take a doped quantum dot, then the hole is trapped by the dopant. Hole is captured by the dopant. I had a student who was very unhappy whenever I said the hole is trapped by the dopant. So, out of respect for him, let me say the hole is captured by the dopant. Then the electron is sort of set free. Remember, the electron wave function is still delocalized over the entire quantum dot, and it should be easier to donate this electron to methylphthalein. And this has been reported for other systems as well. So here we see that actually happens. If you titrate the doped cadmium sulfide or undoped cadmium sulfide quantum dots, you do get quenching, PL quenching by methylphthalein. The extent of quenching is definitely more in the doped quantum dots. The circles are PL intensities. The rhombuses or rhombi, what are they called? I don't remember. They are the PL lifetimes. Now, if you remember the Standard plots that Nimai showed, they were nice and straight. We don't get nice and straight curves. From here, what we can say very clearly is that doped quantum dots are more efficient electron donors. That's fine. But why is there an upward curvature in the Standard plot? This is an ubiquitous observation in the field of quantum dots, and there have been many attempts to provide an explanation. Many different models have been used, and there have been a lot of heated debate, especially in the community of conventional photochemists who have forayed into nanomaterials. Generally, whenever you see an upward curvature, the textbook answer is there is static plus dynamic quenching. The problem here is that if you look at the Standard constants constructed using lifetimes, they are horizontal. So that does not quite hold ground. So what it is? Is the quenching static or is the quenching dynamic? One thing that we should remember here is that what is static quenching, what is dynamic quenching? Dynamic quenching by IUPAC definition is quenching that involves an excited state process. We'll come back to that. The other thing we want to say is that we believe very strongly that methylphthalein should actually stick to the surface of these quantum dots because the capping agents are there, right? They're going to attract. So now, okay, this is a little bit of a spoiler, but I'll pretend to have not shown it to you already. Let me just say this. In a situation like this, one can construct Langmuir adsorption isotherm. Weiss and co-workers have done it. We did that. And there we get this kind of a situation where we get two different kinds of dots. You can calculate the association constants. We get association constants of the order of 10 to the power 4 per molar for doped as well as undoped CDS. But then it's 3.4 10 to the power 4, 5.3 into 10 to the power 4. Are they really different or are they within the error limit? It does not look that they are within the error limit because the curves are very different. Then the question is, why are they different? I mean, we have one dopant ion per quantum dot. Is that enough to change the surface so much that the association constant would be different? To answer that, we also did FCS. We're not entirely convinced with the result that we get from here at the moment, but once again, we get a K of about 10 to the power 4. Then we did transient absorption. You heard about transient absorption from Kushun in the morning. And now we see that we get an association constant of 1.2 into 10 to the power 4 for cadmium sulfide, 1.4 into 10 to the power 4 for the doped cadmium sulfide, practically the same. If you look at the electron transfer rate constants, it's about 3-4 times more for the doped ones. So two things that we learned from here are, first of all, yes, the electron transfer is more facile. We'd have been happier if instead of 4 times, it would have been 40 times, but then the electron transfer is already very fast. 5 into 10 to the power 10 is fast. And we also learned from the transient absorption data that the Ks are actually the same. So now we are thinking, is there a glitch in determination of Ks using PL data? As of now, we don't know the answer. We're trying to find out. I'll not talk about copper indium sulfide. I'll just get forward. I have only about 1.5 minutes left. So let me get to the conclusion. So what do we learn about the copper doped cadmium sulfide? There's hole trapping, which gives us strong photoluminescence, long lifetime. The doped quantum dots do exhibit faster electron transfer to methyl halogen. And now we come to the question that we posed: is it static quenching, dynamic quenching? We think very strongly, because you see that if the association constant is so high, so methyl halogen is already sitting on the surface of the quantum dot. It is dynamic quenching. Photoinduced electron transfer is dynamic quenching. But you do not see it in the time-resolved PL data because it is not diffusion controlled. It is the slowest step that determines the rate of a process, right? That is why one can see the signature of electron transfer in PL, in time-resolved PL data. We don't see it here because our quencher is already sitting on the surface of the quantum dot. No diffusion control. Why is there an upward curvature then? There's an upward curvature because the number of methyl halogen molecules per quantum dot increases as we go ahead with the titration. So initially, you have many blank quantum dots. Whatever quantum dot has a methyl halogen statistically would have one. Then, beyond a certain concentration of analytical concentration of methyl halogen, all quantum dots have, on the average, one methyl halogen. If you increase the concentration further, each quantum dot is going to have more than one methyl halogen sitting on it. And that is going to lead to a more efficient quenching. That is why the slope of the Stern-Warmer plot essentially tells us how efficient the quenching process is. The efficiency itself increases as a function of quencher concentration. And as of now, we believe transient absorption gives us a better idea of binding as well as kinetics of electron transfer. Where we want to go from here, I've exceeded the time by 43 seconds already. Sorry, Nimai, but I'll finish in maybe 15 seconds.
No problem.
So the next step is obvious. Since we're looking at electron transfer, that is the primary process in devising photocatalytic applications. So that is what we are trying to do in collaboration with some of our colleagues. Let me thank all these people. Sharmishta and Shomodipto were the key players in our field. And though the work started with Sucheta, she also did a lot of good work. And then many in the group got interested, and each of them have brought in their own particular contribution. And that's how we are slowly learning how to make sense of the spectroscopic data that we get in this nano world. I'm grateful to SERB, CSIR, and our institute for funding. Thank you very much for your patience.
Thank you so much. Thank you so much, sir. Really, amazing to learn all those spectroscopy things. I think it will be really beneficial for all students. He explained such a elementary level. Thank you. Now it's time for us to taking some questions. There's some questions already. I think Subarna has asked how hole trapping is increasing the PL quantum yield. Can you shed some light on electronic origin of it?
Yes. So of course, and this is not our discovery, as I said. This is something that was known already. What we understand is this, and I'll just repeat what I said. See, when you create an exciton by photoexcitation, you have an electron in the conduction band, you have a hole in the valence band, right? And both electron and hole have associated wave functions that are delocalized completely over the entire quantum dot. Now, entire quantum dot is a very small particle, but we are talking about the nano world anyway. If there is a hole, if there's something like copper plus that traps the hole, then what happens? It is as if there is this entire whole wave function gets sucked into that copper plus ion. That is one ion in the entire quantum dot. So now the electron wave function is still delocalized over the entire nanoparticle. The whole wave function is confined to that one atom, one ion. So spatial overlap is very small now. Earlier it was like this, now it's like this. Yeah. So it is not so easy for it to recombine. So it takes longer. And since it takes longer, your excited state lifetime increases, and you saw how much it increases from tens of picosecond to 530 nanosecond. And as you would know, PL quantum yield is directly proportional to PL lifetime. Quantum yield is equal to radiative rate constant multiplied by lifetime. That is right.
Thank you. Thank you so much. There are one more questions. Is there any spectral change in TA data when you change the concentration of methyl hydrogen MV to class?
Yes, I rushed through it. So if you look at the TA spectra here, and here we are lucky because we are working with cadmium chalcogenide. In cadmium chalcogenide, it is well known that this negative signal that you get, ground state bleach, that is the time evolution of it gives you an idea about electron dynamics. And this almost invisible signal that you see here, its time evolution gives you an idea about hole dynamics, right? So when you add methyl halogen, in addition to this feature, this small little thing here, that is for bi-exciton. Once again, none of this is our discovery, it was known. But when you add methyl halogen, and if methyl halogen forms a radical cation, then this here, this sort of positive spectrum that you see at 600 nanometer, that is the signature of the methyl halogen radical cation. So if we look at how much time it takes for that signal to appear, that also gives us an idea about the electron transfer time. That's how we got these KPETs. So yes, these are the spectral changes that you see upon addition of methyl halogen.
Can I just ask?
Sure.
Not a question, but first of all, thank you, Anindada, for the wonderful talk. Learned a lot. And then one comment that I don't think you are too late to enter in the quantum dot thing, because the entire world or technology, quantum dots has not been yet explored for quantum technology. So
True.
That is completely open.
So that is something that we are seriously thinking about. And if we can get into it, it will be very nice.
Thank you.
Thank you, Anshuman.
Thank you. This is thanks our last speaker, Professor Anindya Datta, for his wonderful talk. Thank you so much, sir. Okay, I hope, I think all of you will be around. I think I request if you have time, Professor Datta, Professor Nag, just be around. And I think,
we are here.
Yeah, and Professor, I think Pradhan sir is there also, maybe. I can see Professor Mandal also is there. So we are now moving to Professor Shabra also is here. Yeah, Shamita is also here. Very good. So moving to the last session. So this is basically done for interactive sessions for the students. There are many general questions has been asked. We know they're coming. So we got two experts for that. So last sessions we name it panel discussions. For that we have Professor Sayan Bhattacharya from ISAR Kolkata and Department of Chemistry, and then we have Professor Bholanath Pal from Department of Material Science and Engineering from IIT VHU. So we'll go forward such a way. We try to here I can request all the participants, they can unmute yourselves. We can ask questions directly. Where the panelists are Professor Bhattacharya and Professor Pal, but we do have other experts. They can also supplement. We welcome their participation also. For the next 30 minutes or so, we welcome everyone, where we can discuss what could be the future prospect and challenges in the area of quantum dot as we are celebrating. Generally, the Nobel Prize, when given, that means the field has been achieved saturations in every aspect. So, but there are many people across India, across the globe, still are very much energetically working in this direction. So the young researcher, PhD students, they would like to know, so what is the future scope? Just now, Professor Nag has mentioned one scope, quantum computing, which was also mentioned by our Vice Chancellor, Preeti Sharma said. So let us discuss that how this field can move forward, what still things can be done, what could be the challenges. So I warmly welcome both the panelists, Professor Bhattacharya and Professor Pal, on this session. So first, I request Professor Bhattacharya briefly, in 2 to 3 minutes, you can describe the research activities you do in your lab. Then I come to Professor Pal also for the same. Professor Bhattacharya.
Can you hear me?
Yeah, Professor Bhattacharya.
Yeah. So thank you, Nimai, for this kind invitation. And I can see many known names here, although the videos are off. So all the friends. So what we work on, basically, we traveled a bit with quantum dots, or rather I should say nanocrystals, because whenever we say quantum dot, there is a quantum, this confinement thing that is always questioned. So nanocrystal is a much safer term, I must say. So in that respect, we started with the quantum dot sensitized solar cell. So I'm saying that what we started at ICER. So here we were doping the systems like the 2,6 semiconductors and the 136 semiconductors, and making them in the form of nanocrystals, and then applying them to the solar cells. Okay, so here there are two things. One was the doping with the transition metal ions, and the doping concentrations used to be very low, else the quality of the quantum dots used to suffer a lot. The second, what we used to do is we used to make core shell structures from type 1 to quasi type 1 to type 2, and see how the charges are actually localized either in the core or shell. We did something, and then this perovskite started, and we moved on to the perovskites. And what we realized there, that the perovskite solar cells that everybody was making was mostly based on the bulk systems, the bulk, this MAPBI3 mostly. Of course, because of the trap states of this, the nanocubes of these perovskite systems, although they were all inorganic systems, but the solar cell, these efficiencies were pretty low. So we actually started working in this area. So we worked a bit on the solar cells for these perovskite nanocrystals or quantum dots, as you said. And now we are looking into the structure mostly, and looking into the band gaps, and what is the reason for the better optoelectronic properties. So we are actually studying the electronic and the structural, this this correlation between these two factors, and that's how we are moving on. So to keep it short, I think this is the introduction that I can give.
Thank you so much. Thank you so much. Now we'll come back to you with the questions. So let me, invite Professor Bholanath Pal from IIT BHU. Professor Pal, if you can explain in a couple of minutes, what is your area of experts and current focus and research?
So, am I audible?
Yes, you are.
So, first of all, I would like to thank Nimai for organizing such a nice presentation. Many of my lab members are attending this seminar. It's very wonderful talk, and of course, you gather many of our known persons. Regarding our research activity, first of all, we are thin film device person, mostly work on solution process thin film for different type of device application. Particularly, we use nanocrystal material for photo detection application like phototransistor, photodiode, etc. Sometimes also we use for light emitting device as well. So that is our main activity regarding nanocrystal. Of course, beyond this nanocrystal, we do lots of work on metal oxide semiconductor for different applications. So thank you, Nimai. So we just go ahead for panel discussion, and definitely you will.
Sure. Professor Pal also worked with Victor Klimov, one of the pioneers also in this area. So that's how we know each other in Los Alamos lab.
Yeah, maybe I can add a couple of lines from that days. Actually, when I joined in Dr. Victor Klimov group, by that time my job was to develop quantum dot based solar cell. So quantum dot started its journey particularly in electronics application for solar cell. Eventually, that solar cell part saturated with 10% efficiency, and that didn't move much. Eventually, light emitting device advanced a lot. That is at the level of application, particularly for quantum dot LED application. It is equivalent to that organic pi conjugated material. So organic also started its journey with as a solar cell, organic solar cell, but eventually OLED commercialized first. So it's very much similar to organic world. Right. So maybe we can continue.
Thank you so much. I'll again come back to you. Now, my questions to Professor Bhattacharya means before that, I request all the students and not only students, all the colleagues who are here, if you have questions, you can unmute yourselves and you can ask directly. As I said, there are panelists here, and apart from panelists, our expert speakers, so everyone can supplement. So this is something general discussion. So as you go. Subarna, you want to ask something?
Actually, I have a question.
Maybe there is some feedback is coming from your friends.
Yeah.
Actually, I have a question.
I mean, need to stop other instruments.
Sure. I think there are multiple students. They have been listening together side by side. Okay, so I think Subarna, you come back. You log into device in mobile and go out, and you can talk. Meanwhile, any more questions? Let me see in other questions. So others like students, faculty, they can cut. Okay, raise hands. Let me see. There are some basic question has been asked in the beginning. Also, we can take up those questions. The first questions. There is one is Professor Bhattacharya for you. What is the practical applications of quantum dots in biomedical research?
Yeah, so that's a pretty important question. The applications that has been shown till date for quantum dots is mostly in the mice model and in vitro, right? Because we can target the specific cells. We can basically transfer means attoliter volume of these quantum dots, the solution at the target locations. This can be used for cancer treatment, for drug delivery, and so on. So you can basically, cap those quantum dots to make them water soluble. That is an important thing by different inorganic shells and also micelles, etc. Now, having said that, we still do not know how these quantum dots behave with the bloodstream. That is one thing. The second thing is that how we can basically excrete them out of the body. So in vitro, there are a lot of applications that has been shown, yet to test them in the the human body. That is one thing that I think the community who are working in this field, they're looking after this. So that much I can say. Mostly under the microscope, that things are taking place at this point of time.
Thank you so much. Anyone want to add any supplement to Professor Bhattacharya, Professor Nag, Professor Sapra? Any other addition? Professor Pal? No? Good, fine. Okay. So Professor Pal, to you, in your understanding, what you can see the future of quantum dots based devices, where we are heading towards. I mean, as you know that so far that LG, Samsung has been put those in televisions. Those are in market right now. So is there anything like we're going to get the solar cells right there in the market, or any other stretchable wearable electronics devices? What is your thoughts on that?
Okay, so regarding microelectronics application, probably we can split application area into different part. One is transport part, another is the optoelectronics part. Transport part, people try to make good quality transistor. So many quantum dots are good p-type material, and in oxide semiconductor there is very there is real shortage of good quality p-type semiconductor. That's why probably people thought we can make solution process high quality p-type transistor, but that is not very much successful so far with respect to application, I can say. And if we move to optoelectronics application, there are mainly three different type of application: photodetector, solar cell, and light emitting device. In solar cell, I think so far whatever people work understand there is real limitation with quantum dot, because in solar cell application we need real thick quantum dot film, something like 100 nanometer. Although it's a lead sulfide mostly People work mostly on lead sulfide, lead selenide type of material, mostly lead sulfide, I can say. Lead sulfide, if I talk about lead sulfide material, it's a, direct bandgap semiconductor. Still, we need 100 nanometer, more than 100 nanometer. In some cases, maybe 200 nanometer thickness. In this 200 nanometer thickness, if we talk about, think about how many layers of quantum dot is required, that is kind of 15 layer, 15, 16 layers, so 15 to 20 layers. So within that 15, 20 layers, so when charge will transport through that, there is a significant chance of recombination. So that recombination, of course, people did lots of work, ligand exchange and other things, but that recombination we cannot reduce that much so that it can be commercialized. So, if I compare with commercial silicon is indirect bandgap semiconductor. We deposit something like 500 micrometer silicon, but recombination rate is extremely small. So, and that's the biggest advantage of silicon. And compared to that, with just 150 nanometer quantum dot, we have very significant charge recombination. So that makes that limits its performance within 10%. It's really impossible to go beyond 10%. But if we talk about photo detectors, so quantum dot has a advantage, particularly lead sulfide, lead selenide type of material. We can tune its bandgap towards NIR, IR region. So when we move towards NIR, IR region, usually, when we reduce bandgap, material in general become unstable. But advantage of lead sulfide material or lead selenide type of material, it's better, much better than organic counterpart. Organic is more sensitive, more unstable. So with respect to that, photo detector can be definitely one route where we can apply quantum dot, and I believe several companies are working to make a high performance photo detector using lead sulfide type of material. So it can be quite close, but application point of view, definitely it's not that large area with respect to solar cell and other things. And if we talk about this light emitting device is very successful, close to application, right? Question is why, that trap state and other things issue are still exist in light emitting device. Then why this light emitting device is so successful? So answer is, in case of light emitting device, we don't need first of all very thick layer. Just in principle, if it is a single monolayer, quantum dot inherently it has a features that it can self-assemble. Easily it can self-assemble. If we make a spin coating, it self-assemble very nicely. And we also see in TM picture, so it's very nicely self-assemble film and so on, right? So if we have a perfect single monolayer of quantum dot, that also can emit, give electroluminescence very efficiently. Of course, to make a very perfect film, very pinhole film, we sometimes deposit 2 layer, 3 layer maximum, not more than that. And within that 2 layer, 3 layer film, charge tapping issue is not that big issue. And on the other hand, if we think about, when we talk about real application, so we need to think about other things like stability, its, other quenching factors and other things. Lead sulfide, cadmium sulfide, zinc sulfide, or cadmium sulfide, cadmium selenide combination, those quantum dots are extremely stable, environmental stable. We need not to do much. Unlike perovskite dot, we need not to make very critical things to make it stable. Just make a core cell structure. If you have some minimum amount of ligand, so that can be good enough for stability. And just couple of monolayer. So if you have a very good thin layer, monolayer of quantum dot, and charge transport, whole transport layer, electron transport layer, that's good enough. And that makes it very close to real application. So these are the current status of 3 different type of optoelectronics device. So I don't know, maybe in future we can move towards single lot based electronics in some cases, but that needs some special type of definitely fabrication technique.
Right. So as for you, as for all of us know, it is the display where these KDs are really leading there in the market.
Also, I should add one more thing. So whatever the QD display we are seeing in market, those are basically phosphor type of material. So basically we are using gallium nitride LED, and those gallium nitride LED we are just coating with different color dot, and that makes three different color primary color pixel, and essentially we are using. We are selling those QD display in market, but still that makes a big achievement with respect to its color saturation and other things. But real goal is to make quantum dot based LED and use that LED, replace that gallium nitride by that quantum dot LED. So QD, need not to be confused about QD LED display means it's essentially we are using quantum dot as a primary component or active component of that LED. Okay.
As a down conversion one, right? So that's what you're saying.
Down conversion.
Thank you. So move to over to you, Professor Bhattacharya. So there's a question. So I think Praneeth, can you unmute yourself and ask directly? Praneeth, are you available? You posted here. It's good. You can unmute yourselves and ask directly. Hello. Yeah, okay, I can't hear you, but okay, Paneet is from IIT Gandhinagar, I know. So he's asked that even though QD and perovskite solar cell efficiency has saturated, what are the prospects of tandem solar cells? Since Professor Bhattacharya works on solar cells, so you could be the right person to give some lights on that. His question is, even though QD and perovskite solar cell efficiency has saturated, I don't know about the perovskite solar cell has been saturated or not, but QDs are right. What are the prospects of tandem solar cells?
Tandem solar cell means that you absorb the entire, the visible range of light from red to blue. That is what is the concept of the tandem. Perovskite solar cell, even if you make a tandem, it's not going to improve. The reason being that the recombination factors. So each layer of quantum dot is something that you need to prevent or minimize the recombination. What we get these hot electrons, the fraction of it is very minimal. So be it the trap states or the surface traps, whatever you call it, be it the donor sites, vacancy sites inside, the cation vacancies, the anion vacancies, and so on. So recombination is huge. Unless we prevent that, we cannot really go ahead. The second factor is, of course, to make the quantum dots, we protect them with a surface ligand. So it is organic ligand, which is mostly insulating. So we can wash the surface by some methyl acetate or something, and basically we can expose the surface. So once we separately make the quantum dot by this the hot injection method that Bhavandy has shown us in 1993, if I remember. So that Jack's paper, so we still use it. So for that, we have a lot of surface ligands. Now, there is a method called like the sealer. Sealer is successive ionic adsorption and desorption of the layers. So there, you cannot control the size of the quantum dots, but you can have a better coating. The gaps between the quantum dots will be much less. I think that is more important. Professor Kamath has shown that the sealer method works better as compared to the ex situ deposition of the quantum dots. So that is one thing. The tandem solar cell comes if each layer we can control this, the recombination and the surface, chemistry. Then only we need different band gaps of the semiconductor, this quantum dot composition, such that we can trap each light from red to blue. Unless we do that, making a tandem actually will not help in a big way. That's what my view is.
Sure. That's really
Can I just add into it?
Sure, Professor Nag, continue.
Yeah. So this is regarding the the point of saturation that we are telling that, okay, say perovskite solar cell has achieved 26% solar cell efficiency equivalent to silicon. But I think here we need to be a bit careful in interpreting that data, because those solar cells are 0.2 centimeter square, 0.4 centimeter square. These are the size of the solar cell. The same thing when you take to a solar panel level, the efficiency will drop down to 5-6% probably. And it is not only the problem of getting another bigger setup and you'll do, it's not like that, because right now the way we are doing spin coating, the solvent, probably many of those things will not work for a larger area solar cell. So still there's an enormous amount of scope for research, and I don't think it is saturated in that way.
No.
Not number of efficiency, but if you're looking for a real solar cell, it's a huge scope of research.
Yeah, and to add to Anshuman's point here, I can say something from our research. As Ms. Anshuman said, it is 0.2 by 0.2. So the area comes to 0.04 centimeter square. So from there, we made some solar cells of 20% efficiency and showed the stability for a very long time. In the same work, we have shown that 1 by 1 centimeter by 1 centimeter, so it is 1 centimeter square. The moment we did that, the 20% dropped down to 12%. Okay, and the stability was much less. So now there are many techniques have come up, like this, that roll-to-roll processing and so on. But this is a big challenging, this area when we talk about these numbers. It means efficiency of a small area solar cell actually good for academic purpose, not for the real purpose. Because silicon, you have those panels, right? Huge panel. Perovskite has not to come to that stage to actually compete. To withstand the heat and water, the moisture is very difficult. Although we will totally and cover the entire solar cell, but still, it's a far way that we need to achieve.
Thank you. Really good. We have good discussions by Professor Pal, Professor Nag, and Professor. For this topic, Professor Bhattacharya and Professor Nag.
Probably, I can add a few more things. So one difficulty what I feel among different thin film, unconventional thin film solar cells, those are mostly 200 nanometer, maximum 300 nanometer film thickness, right? So electrode separation, if we talk about the separation between cathode and anode, so that is of the order of 300, 400 nanometer. So when we use some device of that low separation electrode, means there is a strong shear effect. Capacitance multiplied by resistance effect, and that shear effect really have a strong effect on this efficiency reduction. So as soon we increase the area, that capacitance, overall capacitance increase a lot, proportionally increases. So that really reduce that efficiency. So, not only this is a problem of quantum dot based, solar cell, it's a problem of most of the direct band gap thin film solar cell problem. So number one. And second thing, regarding scope, when people work on organic solar cell, so long time it's stuck at 10%, just like current situation of quantum dot solar cell. But when non-Fullerene based material develops, so after that it jumped to 16-17%. Now it is probably 18%. People can make 18% organic solar cell very easily, and that is because of the discovery of non-Fullerene based N-type material, right? So so far whatever the development in solar cells, quantum dot solar cell, that is mostly lead sulfide based. So maybe tomorrow we can have new material, and that can give such kind of jump to above 50. Industries are looking for more than 15% efficiency solar cell, and that is mainly, that efficiency game is particularly for the cost of TiO2, right? Transparent electrode. So if we don't increase efficiency, we'll increase cost because of TiO2. TiO2 cost is more than 50% of the total cost of fabrication, right? So that's why above 50% is kind of marking. we need for large area solar cell fabrication. And maybe in place of lead sulfide, if you have a new material tomorrow, and that stability can be equivalent to lead sulfide, can give a shift from this 10% to 15%, 16%, and that may be visible for realistic application. So scope is not ended, but it's kind of saturated, looks saturated.
Yeah, thank you.
I just wanted to add to that, as somebody had asked it. While the perovskite theoretical limit is already achieved, other than the devices, as Anshuman has correctly pointed out, practical devices still need to be researched on a lot more. But the theoretical limit is already there, right? But for the quantum dots, you never know. As Professor Pal was saying, you can have many more new materials that are yet to be discovered. So quantum dots, I cannot say that there's a limited or there's a capping over there, which we've already reached. There's a lot of scope, I believe, personally. Lead sulfide is the leading material, as you've said, right? But at the same time, Sayan, I think the tandem solar cells are pretty promising, but when everybody is reporting with silicon perovskite.
Yeah, correct. That is this perovskite silicon tandem.
Perovskite
That's
silicon.
what is, yeah. So not the quantum dot. I mean, the question was about the quantum dot. Yeah.
We do consider perovskites also under quantum dots, isn't it?
Which is wrong.
No. Those are the bulk films. Those are not quantum
dots.
Yeah.
Even the I think it's better to call them perovskite nanocrystals rather than perovskite quantum.
Than quantum dots.
Yeah.
So, Anshuman has some say on that.
Yes.
You're body shaming perovskite nanocrystals.
Yeah, perfect. So we have some more questions, and then we're going to wind up in next couple of minutes. Amrita asks, I think this question's to Professor Pal. I'm expecting there will be a deviation in properties in flame and bulk QDs. What do you mean by bulk? I think in solution, maybe she has mean. Are there new characterizations method that QD field is developing to address this issue?
Somehow this question is not that clear.
Okay. Question asking, is there any deviation in the properties if you put in the flames or in this ensemble solution could be?
Yes, of course. We've seen it many times. In fact, I mean, whenever we make a film, we find lots of shift. First of all, if it is a light emitting dot core cell type of dot, we've seen lots of quenching during making film. I mean, let's say I use some 70% core cell quantum yield dot, and I make a film. And if I want to measure the quantum yield of that film, I commonly seen there is a lots of reduction. Let's say from 70% to it can easily quench to 40%. And that, I mean, question was, when I was postdoc in Victor's lab, I mean, it was a big question why there is a big such a big drop of that PL quantum yield. One answer, whatever the statement they gave, and that is because of the strong interaction of quantum dot to quantum dot. So, and that reduced the quantum field. But I don't know. A long time, I'm slowly moving from quantum dot area. Probably I don't know what's the latest development. Maybe people found some better answer than that.
Sure. Fine. Now, next questions to Professor Bhattacharya. So there's a question. So there are some surface capping ligands like hexyl phosphonate or hexyl phosphonic acid, I believe, or TOP. I mean, phosphine-based ligands. Are there that forms multifaceted PNC? I think he was referring to Professor Pradhan's work on multifaceted PNC, where lifetime is quite large compared to oleic acid polylamine capped system, but its PL-quiz is low compared to the amine capped one. How to rationalize that? So I think
this is a very specific question concerned with a particular work.
Yeah. No, but if you take it generalized, maybe the question is, if the phosphonic acid-based ligand, the lifetime means particle size goes up and lifetime increases, but quantum yield is still low compared to the conventional oleic acid oleolamine one? I think any one of you can also then Professor Nag, Safra, if you can complement. I think the question is.
This is observation we have seen not only for quantum dots but also for the nanosheets So when we use the famous the couple, the oleic acid and oleolamine. So this is basically I'll just divert a bit. So it is about the 2D perovskite. So this oleolamine goes as the spacer and oleic acid sits on the surface. But then we get a quantum yield which is lower. But the moment we added the TOP on with it, and we synthesize the the 2D shades with TOP, we saw that the quantum yield rose up to close to 100%. So it was 99 or something. So what we envisage from there is that the surface passivation was there by the TOP more than this oleic acid, and whatever the dangling bonds which were there, those were actually bound by this group, this functional group, this these phosphine groups. Yeah, so that's what our observation is till date.
Fine. Any compliments to that, Professor Nag, on that, Professor Sabra? I mean, phosphonic base acids has larger particles, longer lifetime, but on the other hand, amine acid, oleic acid, oleolamine are it goes in the same line as Professor Bhattacharya described. I think Professor Nag is not there. It's fine. I think we to move to other. I think there's a comment from Dr. Professor Raja Mallis. He's from I think ISC. She is commenting. I think operational lifetime of both LEDs and solar cell are still challenging. Both operational lifetime, both LEDs and solar cell, QD based LEDs and solar cell are still challenging. Any comment, Professor Pal, on that? And others also.
I think quantum dot LED, I mean, lifetime is quite good enough for practical application.
Okay.
So it's not a big issue. Even lead sulfide based solar cell has quite good. I mean, with respect to perovskite, definitely it's quite good. Its stability, but stability is not good enough. I mean, first of all, its efficiency is the primary thing, what I already mentioned because of ITO issue. And second thing is certainly lead is a big concern. So more than stability in solar cell, I mean, in light emitting device, stability is not issue. Stability is level of commercialization. But in solar cell part, stability even can be level of application, but other issues are more important. I mean, efficiency
right.
Particular bigger concern.
Sure, thanks. I think the one more questions. It is Professor Bhattacharya. So the Habib has mentioned that in recent time, lead-based perovskites are being explored for catalysis of chemical reactions. Again, this is general question related to toxicity. So see, he has pointed out, but lead is a toxic. So how to look forward, with this toxic material in case of catalysis? This is a common question with people often.
So to say this again, photocatalysis is something more of academic interest because in terms of industry, these requirements, photocatalysis has actually not come up so much. It's been several, like the decades now. Photocatalysis, I don't see much promise as till date. Maybe something will come up, but about the toxicity thing, let me tell you that there are several other perovskite systems which have been used and are still being used for photocatalysis. Of course, they are not as defect tolerant as compared to the lead-based systems, but there are tin-based systems also, SN2+, and there are other forms of these perovskites like the double or the double perovskite or this HLDP, this hybrid layered perovskite, and so on. So many, these bismuth-based systems are there, Bi3+. So other than lead, this has been used a lot. Now, your concern is very valid. Now, I just move from the photocatalysis to the TV, this OLED, right? Sorry, not the OLED, this the QLED. So QLED TVs. The problem is that most of them use this cadmium because none other metal actually is good as compared to CD. So CD-based systems, they are also toxic, and there are countries who don't want to sell those kind of the sets, the TV sets, to the homes which contain cadmium. So Samsung could not find a replacement to these cadmium-based quantum dots. So it is still a challenge, but when we consider photocatalysis, we have many other systems as compared to the lead-based. It's not that we always use the lead-based. The lead-based systems are best for the solar cells, etc. When the mobility is concerned, but here many other systems are there.
Thank you. I think there are many questions are popping up, but let us wind up here. Let us stop here. I think before we close the sessions, we'd like to thank both of you as a panelist. You have enlightened our audience with your valuable thoughts and your experience. And I request all the now participants with the speakers, let's turn on your video with the panelists. Let's have a picture that we can make it an online picture to memorize this. Maybe while we're growing old, we are already old, growing more old, we'll thought that we have celebrated the Nobel Prize winning in 2023. So I request everyone to turn on, and then maybe, this month, can you take a picture, whole screen? This month? Angshumanda, are you there? You can make a screen, huh? Right? Or Devasis, are you there? Yeah. Is any students can help us to make a, I think I know, maybe this, just once and give me a minute. Let me call this, I can call this month. Or you can, I think I don't never do it in a, so just one second, just a minute, this month. You can? Yes. So I think, can you make a screen? Yeah. So almost now we can do it. Make a change, everyone. So that's how it is. Yeah. Thank you. Happy to have all of you on board.
Thank you.
And in the afternoon sessions, I thank all the speakers for sharing on your valuable times.